Hello. The true sign of intelligence is not knowledge, but imagination. Honored dignitaries, HOIs, HODs, faculty members, and dear students, a very good morning and a very warm welcome to you all to the second day of the 4th National Conference on Multifunctional Advanced Materials, MAM2023. We are extremely honored to have amongst us our esteemed guests, Dr. Sanjeev Verma, Scientist E, TVRL Chandigarh, Dr. Pankaj Thakur, Special Center for Nanoscience, Jawaharlal Nehru University, Dr. Ashish Sani, Scientist F and Divisional Head, Advanced Fuse Development Division, TVRL Chandigarh, and Professor A.S. Rao, Head, Department of Applied Physics, Delhi Technological University. It is indeed a pleasure to have you all here today, sir. We start with the first technical session of the day. This session will be chaired by Professor A.S. Rao. It is my honor to invite our first speaker of this session, Dr. Sanjeev Verma, Scientist E at TVRL Chandigarh, to please enlighten us with his thoughts on non-Newtonian fluids and its application in personal protective systems. So please.
Thank you, madam. Good morning. I am Dr. Sanjeev Verma. I'm working as scientist and I'm the part of the DRDO. I will give my presentation on the non-Newtonian fluids and its application in personal protective systems. I will start what basically a protective system is. Basically, a protective system is something that protect you from the external attacks, any kind of the external attacks. Likely, imagine that you are moving in a plane, right? The first line of protection is that nobody is able to see the plane, or nobody is able to see in which the carrier you are moving. This kind of protection is called as the soft kills. That basically is to protect from the soft kill. The next is somebody has seen you. The next, what should be the protection? Then the next protection will be that you cannot be detected accurately, right? Somebody has seen you, but you cannot be detected. The second, again, the protection is, it is in the category of the soft kills protections, where somebody has seen you, but he's not able to detect you. The third line is somebody has seen you, detected you, now he's going to hit you. In this case, when a soldier is already being detected, what I need to protect that person is in the category of a personal protective system. Likely, you all have heard about the bulletproof vehicles, right? Somebody has seen that a soldier is moving in this vehicle. He's already seen, he's detected, and somebody is hitting over the person. Now, this category where a person after this has to be protected is called as the personal protective systems. If I will say that personal protective systems are of number of kinds, it can be a bulletproof jacket, it can be a bulletproof vehicle, glass, or the helmet. All are in the category of the personal protective systems. If I will go back to the history, then the personal protective system is not new to the world. आपने सभी ने बाहुबली मूवी देखी है? बाहुबली मूवी में एक कटप्पा त्रिशूल रचना लगाता था, राइट? उसमें कंडीशन में क्या था कि somebody is putting the armor systems, जहां से कोई अगर हिट करेगा तो पर्सन पर हिट नहीं होगा, right? That is the category of a personal protective system, and it is back to the history. After this, a number of new systems arrive in the world. Have you heard? जैसे कई number of times we came to know कि हमारे soldiers थे, उनका जो protective system था, उन्होंने बहुत ही मोटी steel की protective system मिलते हैं हमारे को in Maharashtra, in Punjab. That is again the second class of the protective gears developed in the history. But after this, whenever the threat level are going to increase, we need the protective system that should be lighter in weight. And in this category, the first is you have seen in the flexible armor, that is the Japanese. Japanese were the first to invent it. It is made of some silk kind of the materials that are lighter in weight, and it can give you protection from the arrows, sword, and etc. With this, a new science came where people were looking to develop a protective system that must be lighter in nature. But actually, if I talk in terms of the scientist or scientific world, the first time when the people are thinking about the system that are lighter in nature, a bulletproof jacket that is lighter in nature, that can give you protection from a bullet, started nearly about the Second World War. In the Second World War, if you look at in the perspective of the defense industries, most of the valuable addition or the research happened during the World War I and the World War II. And during the World War II, a new material is discovered known as the Kevlar, right? Kevlar is a material, it is very strong in nature, and its strength is around 12 times higher than the stainless steel. With this, a new science came where people were looking that my protective system is not now made of the steel that is heavier in nature. It is made of very soft material that is flexible in nature. It is very light in weight. And with this, a new science came where people or the world, scientists worldwide are looking for new materials. That is starting with the Kevlar. With this, a number of new materials was discovered in the worldwide. And among them are like the ultra high molecular weight polyethylene. This is the strongest known material to the human being, and its strength is around 18 times higher than the stainless steel. For example, if you are wearing a jacket, okay, and the jacket weight of this with this material is 1 kg. If I remove all this discovery after the Second World War and I came to the age of the steel, the weight of the jacket will increase around 18 kg, of 1 kg to the 18 kg. And this is just about how basically a bullet is stopped by a armor system. When a bullet hit a armor system, basically what happens is bullet is going to be braked, and at the same time the armor is also going to be failed. And during this process, most of the energy of the bullet is getting absorbed. And this is one of the way. And these are the, when I am saying something is a bulletproof jacket, right? Basically, a bulletproof material is different when it is for a civilian person, when it is for a police person, and when it is for the army person. आपने पुलिस वालों की प्रोटेक्ट, एक पुलिस वाले को या आपको एज ए स्टूडेंट अगर मान लीजिए कि बुलेटप्रूफ जैकेट लेनी होती है, तो आपको मैक्सिमम थ्रेट किससे होगा? किसको आप इमेजिन करोगे कि आपको यूनिवर्सिटी में कोई आएगा और गोली मार सकता है? मोस्ट ऑफ द टाइम पिस्टल और रिवॉल्वर, राइट? यू कैन थिंक ऑफ इट कि एक कोई भी पर्सन पिस्टल या रिवॉल्वर से ही मुझे थ्रेट क्रिएट करेगा. बट व्हेनेवर इट इज विद द सोल्जर, बट he has a threat of the AK-47. In that case, the jacket is different. Similarly, we differentiate the jacket on the basis of their energies or the kind of the threats. Some are for the civilian application, where you have a threat from the pistol and the revolvers, and other on the category where you need the protection from the assault rifles like the AK-47. These are the category of the ammunition as well as the jackets or the protective gears. If you look at system right now, if you are a police person or a civilian person, the weight of the jacket that you are wearing right now is not more than the 1.5 kg. And the same time, if you are in an army person, the weight of the jacket is around 10 kg, right? If I see how much a soldier is carrying weight over him, imagine that a soldier is moving, he has a lot of things to carry. He has his weapon, ammunition, and at the same time, he has something to feed if it is required. In that case, if he is wearing a jacket of 10 kg, his body weight load is very high. In this case, we are, as a system, we always open for a new materials, or we are working to develop or the or to discover new materials which are better than the existing material. And the target is always to reduce the weight, and target is always to increase the flexibility. In this case, if I go with the literature, whenever some peoples are working to develop new materials, most of the time they are motivated from the natural sources, right? This this is one of the material developed by the MIT US that is very lighter in nature. But it is, you heard about the spider silk. It is very light in weight, and at the same time it has very high strength. Likely, if I have to cover whole the earth with the spider silk, with the only half kg of the spider silk, you can cover full earth. So people are looking, is it possible to have some genetically modified spiders that can produce very large number of the silk, and it is possible to have some jackets or the protective gears made of these materials. People are also looking like the deep sea snail. The cover is very, very hard in nature. Is it possible to have a jacket that is made of the material with this of this specimen? Similarly, nanotechnology, you heard about the carbon nanotubes. People are looking that, is it possible to have a bulletproof jacket made of the carbon nanotubes? For this, I need the carbon nanotubes have one dimension in nano size, and length is very higher in nature. Similarly, people are looking for smart material, new smart materials. Is it possible to have a material which is liquid in nature, right? Is it possible to have a material that is liquid in nature, but when a projectile hit over here, it get converted into a solid, and the same time when the projectile is removed, it get again shifted to solid. Like this, you can see in this imagination, this is a liquid in which some particles are agglomerated or dispersed. A projectile is hitting over here. All the hard particles are localizing themselves at the site of the impact, and when the impact is removed, it is get again converted into a liquid. These kind of the fluids are basically non-Newtonian fluids. What basically is Newtonian fluids? Newtonian fluid is basically a fluid whose viscosity does not change with any kind of the shear properties. आपने टोमेटो सॉस देखी है? आप टोमेटो सॉस को जब प्लेट में डालते हो, आप शेक क्यों करते हो? You are shaking the tomato sauce because जब आप उस पर कोई शेकिंग कर रहे हो, उसकी विस्कोसिटी कम हो जाती है, and it will be, for you, it will be easy to disperse the sauce in the plate. This is the category is of shear thinning. In this case, the viscosity of the material is decreased when you applied some stress over here. पेंट करते हैं हम डोर्स, अगर आप पेंट करते हो तो बेसिकली आप क्या कर रहे हो? ब्रश के साथ में you are giving a force. Whenever you are giving a force, the viscosity of the paint is reduced, right? And you are able to coat the paint over the wall. In opposite to it, there are materials which start behaving different to each other, different to it. This kind of material shows the increase in the viscosity when you applied some shear stress over that. Sea beach पर अगर आप चलोगे, अगर आप नॉर्मल चलते हो तो आपको लगेगा कि आपका पांव फंस रहा है इसके नीचे, राइट? अगर आप स्पीड से मूव करोगे, देन व्हाट विल गोइंग टू हैपन कि आपको इजीली मूव कर सकते हो इसके अंदर से. एग्जैक्टली थर्ड एग्जांपल इज मड. अगर आप मड में कभी कोई पर्सन ट्रैप हो गया है और वो जोर जोर से उसके साथ मूवमेंट को स्टार्ट कर रहा है, व्हाट इज गोइंग टू हैपन? उसकी जितनी ज्यादा फोर्सेस से वो उसको इफेक्ट करेगा, उसकी विस्कोसिटी उतनी ही ज्यादा बढ़ती जाएगी, एंड द पर्सन इज नॉट एबल टू out of the mud. What if he is doing this slowly? It is possible that he may come out from it. This is a category of the shear thickening fluid in which the viscosity of the material increase when I apply some shear stress to it. The idea here is it possible to develop a protective gear that is liquid in nature, but in the same time it can give you protection from the bullet. It can give you protection from a number of things, like आप बाइक चला रहे हो, ओके, आपको नी प्रोटेक्शन करने के लिए आपने कोई लिक्विड डाल के रखा हुआ है. व्हेन देयर इज ए लिक्विड, इट इज कंफर्टेबल. आपकी बाइक गिरती है, आपका जो नी है वो नीचे स्ट्राइक करता है रोड से. द टाइम व्हेन इट स्ट्राइक टू द रोड, it get converted into a solid and give you protection, and the same time when you are coming out of it, it will again converted into a liquid. This kind of the system are basically called as a liquid armor. It is a liquid as well as a armor, right? And this is the category of the non-Newtonian fluid. And in the non-Newtonian fluid, it is a category of the shear thickening fluid, in which the viscosity of the material increased when you applied a shear stress over it. Basically, shear thickening fluids, what are these fluids basically? These are the dispersion of very hard nanoparticles in polymer matrix, right? Like in the given example, we have taken the silica as a nanoparticle and it is dispersed in a polyethylene glycol, right? What actually happening is, if you imagine a football goal post, right? जहां पर भी crossovers हैं goal के लिए, if I strike a metallic ball over there, जब भी बॉल टकराएगा तो आपको लगेगा कि समथिंग जो उसके बीच का स्पेस है वो रिमूव हो रहा है और जो बॉल्स है वो आपस में स्ट्राइक करेंगे एंड यू आर एबल टू हियर सम वॉइस. एग्जैक्टली इन अदर एग्जांपल, आपके पास बहुत बड़ा टब पड़ा है पानी के लिए, वाटर के लिए, एंड यू पुट सम बॉल ओवर हियर, you hit this with a stick, what is going to happen? The water is going to disperse and all the balls are coming together. This is a classical example of the shear thickening fluid, in which we have taken the silica and the PEG, and whenever you disperse, whenever you make a solution, the rule is like dissolve like. In this, if the silica has the OH groups, I need the polyethylene glycol that again have the OH group. I need the particle of the size that is should be in the nano size, or little bit higher than that, but not be maybe in the colloidal range, but not be in the form of the suspension. Either they will settle down after some time. Again, this is the example where the hard particles are surrounding by the soft polyethylene glycols or the polymer matrix, and it will give you a structure like this one, where there are hard segments that are the nanoparticles, and there is a matrix that is of the soft material. Finally, the material is soft because of the matrix, and it is armor because of the hard segments that are present in it. This is an example what actually is happening. You are moving a finger, the particles are going to agglomerate or the club together and gives a solid-like structure. If I look at the literature, number of kind of the shear thickening fluids are available. If you go at the Google, you will see the shear thickening fluid made of the cornstarch. They made a pool of the cornstarch, and somebody is behaving like he's moving on the water. Whenever I'm looking for an application, I need a material which is enough strong, commercially available, that can be considered for the commercial applications. I just narrated just before it. You have a number of applications. You have the gloves. Okay. This whenever you can imagine, whenever if you have a gloves in your hand and you are driving a bike, if the material is hard towards inside, you are not able to drive the bike. What if it is a liquid, and liquid of this kind of nature of very low thickness? What is going to happen? You have extreme high comfortability to drive the vehicle, and the same time, if there is any accident, it give you a protection like anything else. Similarly, for the helmets, it can be for the civilian application, like the cycle, bike kind of the helmets. I'm just in this, I am just narrating a case study that how basically DRDO is working and how we are little bit different when it is with the academician, because our interest is always to convert a research into a product to the end. And as a student, you can look at your scope in it. Are you able to contribute something else, something here? We have the options to have students for the trainings, scholars, etc. Like just before I narrated that our objective is to develop a shear thickening fluid, a liquid armor that is made of the silica particles, and it is dispersed in the polyethylene glycol. Here, the first step is always to develop a silica particles. Actually, what we actually do, we have some partners, research partners, academician basically. Their objective, we divided the objective in a way that the person who is best in it, he has to do that. He will do his research, he converted it into a product and transfer the research to the second person. Like in this case, in this project, the first part is the National Chemical Laboratory, that objective is to develop the silica particles. Whenever you are talking about the nanoparticles, you are talking in milligram or grams. Whenever I am talking about the nanoparticles, we are working in kgs. In this case, we develop the silica nanoparticles of my desired dimension with NCL Pune. With the industrial partners, we develop the silica nanoparticles to a very large size. And you can imagine this mono dispersed silica nanoparticles that were costing 25 lakh rupees per kg, it is shifted to the 20,000 per kg with this research and to have a commercial viable solution. Whenever the silica particle is developed, the next part is to develop the shear thickening fluids. Shear thickening fluid, I told you that in the method development, I need to disperse the particles in a polymer matrix. These are the workflow, how it is developed, the silica. We have to select the particles, solvents. If you look at the nanoparticles, it has the different sizes possible, different shape possible. In the same time, if I look at the polymer matrix, it may have the different molecular weights. It may have the different viscosities. We have to choose the combination that suit my best solution. And in this work, there are almost 7 to 8 organizations, different organizations were involved, like the IIT Delhi, Thapar universities, and the other university around the Chandigarh. And finally, a method is developed to synthesize the shear thickening fluid in the kg levels. I am again repeating the same thing. Whenever you are working to develop a research into a product, you cannot talk about in the milligram level. Our objective is to do the research, immediately convert into a product, and finally to lead in another direction. These are the way, whenever you develop the shear thickening fluid, see that you have a fluid that convert into a solid at the time of impact. But the velocity of bullet is very high. It may be possible that bullet hit over here, it passes from it, after that it gets converted into a solid. You have no application. Similarly, if I am working to develop for you like a student, I am developing a knee pad, I am developing some ankle sport or anything else. In this case, my response time is high. When it is about the bullet, the response time is slow. We need a range of the materials as per the application, where I need that whenever it is required, it is solid. And whenever it is not required, it has to be liquid. And on the basis, when I am saying it is a shear thickening fluid, it must be characterized in a way. And different agency again involved in the characterization of the materials. Whenever I characterize the material, I develop a shear thickening fluid. Now, what is the next part? The next part is to tune the property of this material. Again, number of students are involved in it. Somebody is taking the shear thickening fluid from the DRDO. He's adding some additives like the nanofibers, nanotubes. Somebody is adding some polymer matrix just to fine tune the material in a range where it has the application for the defense purpose, and the same time it has the application for the civilian purpose. These are the different additives people are working. When I'm saying the people, they are the partner of the DRDO in the project. People are working to define with what actually happening when I'm changing the particle size. Is it going to improve my property or not? Similarly, when somebody is working, a good quality of the research paper are published, and in this, the highest impact factor of the project is around 19 impact factor paper were published in it. These are again the fine tuning of the shear thickening fluids with the different material, like the changing the matrix or anything else. I'm not going to go in the detail of it. Likely, I need to increase its strength. We are incorporating the carbon nanotubes, graphene oxide in it. Is it improving the armor property and at the same time maintaining the flexibility? And finally, we come up with a solution. I'm just showing you a video. It may be interesting for you. You can see this. This is a viscous liquid. It's just like a honey. Are you able to see it? I need assistance. Yeah. Presentation. You can see that it is a liquid, sorry, it is a liquid, it is viscous like honey. If you move it, it will flow. Like knife, you will hit over, it is penetrated.
However, when it is infected with the velocity, it can improve solids. The liquid is called shaping fluid. Its viscosity rise when it is infected with the velocity.
ये देखने में एक लिक्विड लगेगा और इट इज द वीडियो दैट इज यू आर लुकिंग अबाउट इज द फर्स्ट जनरेशन ऑफ द shear thickening fluid. अभी जो shear thickening fluid है वो ऑलमोस्ट कुछ थिकनेस पर भी आपको इंपैक्ट नहीं होने देगा. When this shear thickening fluid is developed, the next part is to convert it into a product. Then the first question is it able to stop a bullet? The shear thickening fluid is encased in a cylinder and it is impacted with a bullet. And we measured how much is the reduction in the velocity of the bullet with how much of the thickness. It appeared that it is able to stop the bullet, but the weight of the jacket is very high. If I will make a jacket only out of this material. The second part is then what is the next? Then this material, that is a liquid material, it is encased between the existing armor systems like the Kevlar. And when it is impacted with the material, then what we find that it is able to stop bullet even in the given case. If somebody needs a jacket very thin in nature, likely you need a bulletproof jacket that is incorporated in your shirt, then this material in this form is applicable. What if I am looking for a commercial viable solution where the weight of the jacket must be lower than the existing jacket, I need to go in another direction. Again, this is how to use this material. The next part is with the IIT Delhi. This shear thickening fluid is coated over the existing Kevlar material that from where I had started my talk. That is this one of the strongest known material to the human being. This material is coated over here. It is again characterized by the different techniques. Its performance is checked. And finally, a bulletproof jacket is made of this material, in which this material is coated over the Kevlar fabric. And the weight reduction with this material is around 30%. Likely, if the earlier the jacket weight was 1 kg, with the application of this material, the weight of the jacket reduced to 700 grams. And I conclude my talk with this last slide. And I am authorized just to talk about up to it on it. Thank you. Anybody wanted to ask anything else? Any question? Thank you. Yes, ma'am. Carbon nanotubes when actually, when you see like dissolve like, carbon nanotubes are basically non-polar in nature, and the fluid here is the polar in nature. It increases the performance, in the same time it decreases the stability. After some time, there is an agglomeration when there is CNT inside the material. But we have silica coated titanium systems with me. Titanium diboride. It is coated with the silica particle over its surface. It is giving better performance in same time the stability. Exactly in the same way. When CNT is coated with the silica surface, it is giving the performance. When you likely, if you have to make some changes in the CNT, okay, you have to oxidize it. You have to make some changes in the graphene, you have to oxidize it. When you are going to oxidize this material, you are going to decrease the performance. When I am saying that I have to incorporate the silica on its surface, I need a very high control of very low grafting or the very low surface modification of the particle for the silica conversion. There is possibility that somebody can work on it, on the modification of the shear thickening fluids. We have the project regarding the same, like the material that we discuss about with yourself. Anything else from the student side? Thank you.
Thank you, sir, for your illuminating words and for motivating our students by sharing the working of DRDO for non-dispersed silica particles. Now I request Professor A.S. Rao and Dr. Atul Thakur to come on the stage and present a memento to Dr. Sanjeev Verma on behalf of MAM 2023. Sir, please. Thank you, sir. Dr. Pankaj Thakur works in nanomaterials and nanochemistry. In a career span of 13 years, he has 6 patents to his credit and has received several awards and recognition for his research work. I would like to invite Dr. Thakur to apprise us about morphological control of nanomaterials via simple methods. He will be joining us on online mode.
Thank you, ma'am. Can I start?
Yes, sir, you can start.
Thanks a lot, ma'am. I would like to thank the MIT University and of course, Professor Atul for inviting me to this a wonderful conference, Multifunctional Advanced Materials, MAM 2023. And I'm delighted to present on the platform of MIT University my talk on simple methods for morphological control of nanomaterials. So just to have a brief background, everyone nowadays is from research point of view working on nanomaterials. So as a researcher, my endeavors are to find economical and simple methods for growing nanoparticles. And basically by training, I am a chemist. So always I look for sustainable models for the synthesis of nanomaterials. And from nano point of view, the morphology is quite important. So we look to alter various morphologies by altering various parameters or kinetics of the processes. So I would like to share my so I hope it's visible to everyone.
Yes, sir, you can continue.
Okay. So again, I am reiterating my topic of today's uh, lecture, morphological control of nanomaterials by simple methods. Again, I am emphasizing that morphology is very, very important from application point of view, whether it's biological as well as non-biological applications. Like for drug delivery, we look for mostly spherical nanomaterials, while for some other applications also we look for cubical nanostructures. So what we our group work on nanomaterials by the use of some polymers, or precisely speaking surfactants. And the surfactants precisely we use are a typical surfactant look like this picture you can see on the slide. One part is hydrophilic, and which we call head part, and the carbon chain of plenty of carbon atoms is hydrophobic, we call it tail part. And they are composed of two parts basically. And what is unique about these surfactants is I always call they have a dual personality. One in solution, whether aqueous or non-aqueous, one part try to remain inside and another part try to come out of the one part try to come out of the solution. So surfactants, they have another unique property of getting into some micellar, some arrangement, morphological arrangement, which we call micelles. And micellization is a property of surfactant molecules above which they start forming these structures. And this particular concentration of the surfactant is called as CMC, critical micelle concentration. So basically what in nanotechnology, these surfactants, they act as templates. And next slide, we have another class of surfactants, Gemini surfactants. Like previous one, we had a single tail, single head group. Here we have two head groups and two tails, and they are connected by covalently bonded spacers, and they are much more hydrophobic in comparison to their single chain counterparts. And micelles, they undergo a lot of transitions: micelles, then rod shape, bomb like micelles, vesicles, multi-layer laminar structure. That's why to design various nanostructures of 0, 1, 2, 3 dimensional plates, wires, rods, etc., the surfactants are used. What these surfactants do, for example, in case of rod shaped nanoparticles of various metals or other materials, they block one side, and another side can be grown further to develop rod shaped nanoparticles, which I will present in a few next slides. So another slide present you typical Gemini surfactants again, how we name them 12 to 12 depending upon the carbon chain length. They are connected by a covalently bonded spacer of 2 carbon atoms. So this is how a typical Gemini surfactant look like, and they have very good water solubility. In fact, to increase the solubility of some materials while doing wet chemical synthesis of nanomaterials, we use Gemini surfactant. So now, just a minute. Yes, Ritesh. Ek minute, then I will look at it. Just wait. Sorry for the interruption. I was. I hope it's visible now.
It's visible, sir.
Sorry, extremely sorry. I will just go to next slide. Can you just let me know it's visible or not? Is it visible, ma'am?
Yes, sir, it's visible.
Next slide. Okay. So a typical, how this surfactant works for the growth of nanoparticles. This is very perfect example, was published long back in JPC.
Sir,
And,
sorry to interrupt. Can you please do the slideshow?
Yes, ma'am. Yes. And can you guide me through this from where I can?
Sir, let it be like that.
Mhm. Okay. Okay. So this is a typical Gemini twin-tail surfactant for which we used very low concentration, and the growth of nanoparticles of various shapes is changing with the change of concentration. And this reaction, typical reaction we carried out for the synthesis of lead sulfide nanoparticles, and they were capped by stabilized by 12012. Again, 12012, I am emphasizing that it is a 12 chain length carbon chain. And when we further increase the concentration of this surfactants, the morphology changes to cubical nanostructures. So next slide, I will. Again, we changed the surfactant to 12 to 12. It's a typical Gemini surfactant. And at very low concentration, the morphologies were star-like. And in the next slide, if I can show you, if we increase the concentration above 0.5 millimolar, the morphology changed dramatically, and the histogram showing the, and also the TEM images confirming the size of nanoparticles, these lead sulfide nanoparticles, was 50 nanometer. And again, further increasing the concentration of this surfactant, the morphology is like, truncated nanoparticles, which is kind of hexagonal arrangement. And this slide typically represent, how this time dependent shape evolution of lead sulfide nanocrystals at half an hour. What was the structure of nanoparticles, and after 1 hour we observed with the use of TEM, and after 2 hours and 4 hours. So this is a kind of shape evolution, time dependent shape evolution, and this graph showing, hydrophobicity parameter of various surfactants with the use of fluorescence, where we use pyrene as a fluorophore. This diagram summarizes all these results which I have shown in the previous slides. Of course, there are a lot of other results also which I am skipping, but this typical diagram is showing how changing hydrophobicity with the increase of surfactant concentration changes the shapes of nanoparticles. Of course, again, I'm emphasizing, which I spoke in the beginning, that morphology is very, very important from application point of view. So another example we did, this was published in Advanced Functional Materials, and we synthesized again lead sulfide nanocrystals with the use of a protein, which bio people may be knowing, that bovine serum albumin. It was this BSA, it is commercially available protein, and I think the molecular weight is 40,000 Daltons. So just my point of presenting this slide is to just present you how changing the concentration, the basic parameters, simple parameters, concentration as well as the temperature, it changes the morphology. If you can see some changes with the concentration and with the rising temperature. So on this right side of the this slide, this is the average size distribution histogram showing, and XRD confirming the growth of lead sulfide nanocrystals. And again, these lead sulfide nanomaterials, with the increase in concentration further to 5 × 10⁻⁴ gram per ml, and changing the this temperature, how it changes the morphology. In between, the arrows show, this protein has a unique property of denaturation. It starts denaturation. Its denaturation starts around 60 degrees centigrade. That's why this film of presented by arrow, it is shown there, and at 80 degrees centigrade there is no film of this BSA present, because the denaturation has been completed. So again, we are increasing the concentration, and this confirms the growth of lead sulfide nanocrystal with the use of XRD as well, and very small nanoparticles are prepared for this semiconductor lead sulfide of the order of 20 to 30 nanometers. And the close this HRTM image also confirmed the outside layer of this this bovine serum albumin present outside the lead sulfide nanoparticles. So this is typically, this study was done to confirm the charge as well as gel electrophoresis, protein assay, as well as the charge. Under the applied voltage, this travel towards a positive electrode in gel electrophoresis, signifying that it has a negative charge. So again, we use this method for, this is called a Bradford method, for the estimation of protein present in this material. So this is typically, again, summarizing these previous 3-4 slides, that changing just the temperature, how the morphology of nanomaterials changed. At 40 degree, there is no denaturation of this bovine serum albumin starting, and at 60, there is the denaturation starting, and 80 degree, the denaturation is almost complete. So this is another example of composites of lead sulfide gold with the use of this we call gold chloride, hydrogen tetrachloroaurate, and lead acetate and thiacetamide. for the preparation of composites of lead sulfide and gold. A lot of polymers are being used, and PVP, polyvinyl pyrrolidone, is also being used for the growth of nanomaterials. I will be skipping this. Just by changing the parameters of these concentration as well as temperature and time, just we get different nanostructures. See, it's not about we can get any kind of nanostructure. It's kind of hit and trial that once we try some system, we get this morphology just by changing some parameters like concentration, temperature, etc. We can try to get desired nanostructure depending upon our requirement from application point of view. So these are kind of long micro rods, I would say, which have morphologies of a kind of hollow nanotubes of lead sulfide. But the point is, again, the application point of view, these are quite from application point of view, the size of these nanorods is a little bit in the micro range. So as I spoke in the beginning, this is latest work, and we look for some sustainable models as well as some simple methodologies for the synthesis of nanomaterials. So a lot of people are using flowers, plant extract, etc., even various microorganisms for the growth of nanomaterials. And this from environmental aspect, these methods are quite important for future generations. So this is a typical representation of how the growth of metal nanoparticles can be carried out with the help of essential oils. This is the kind of review. We propose this kind of growth of nanomaterials, how reduction is taking place in the presence of essential oils and cluster formation. There is growth and stabilization by various phytochemicals present in plant extract or various parts of the plant, and nanoparticle growth happening. So most importantly, this is eco-friendly method, and from environmental point of view, sustainable models are always welcome as far as nanomaterials are concerned. So another example in the next slide, I will emphasize that organic nanomaterials nowadays, see, everyone look for organic methods and I would say organic materials. So हम लोग वैसे भी ऑर्गेनिक करते हैं कि ये सब्जी ऑर्गेनिक है etc. So that's why organic materials are very important. Like, you know, previously it was metal catalysis. Nowadays people are emphasizing organic catalysis. So that's why materials of nanomaterials of organic compounds are also very important. And this is a kind of self-assembly. It's not typical reaction. So again, sustainability is the forefront for as far as my group is concerned. So we just use some tri-block polymer to grow these kind of nanostructures. And you know, these kind of nanostructures, I would say nanoshells, are very important from drug delivery point of view. And most importantly, this self-assembly process was carried out. This was from one of my postdoc work, which is still unpublished. So this was done at room temperature, and we had remarkable results. We are trying to have a patent on this. So again, just by altering the time and the concentration of the species involved, we got various kind of nanostructures. And so from application point of view, these nanostructures are very, very important, as I told, to encapsulate drug inside. So this is a typical mechanism how when your polymer is hydrophobic, how the hydrophilic drug will be encapsulated. And in the next slide, how if the vice versa is the case, how hydrophobic drug will be encapsulated inside the shell, which is comprising of you know, this hydrophilic tri-block polymer or a simple polymer. So I hope I am finished with my slides. So again, I would like to thank MIT University and all the team of Professor Atul Thakur for inviting me for this lecture, and would be delighted to answer the few questions. If someone has questions, I'm ready to answer. Thank you. Thanks a lot.
Hello,
Yes.
am I
Sir.
audible? Am I
Yes. Sir.
audible?
Yes. Sir. Yes. Yes.
Sir, it's great talk, sir. Sir,
Thank
one
you.
question I would like to ask you, that
Yes.
you have explained that in the PBS nanoparticles, you have used a capping of bovine serum albumin.
Yes.
What is
Sir.
what is the purpose of using bovine serum albumin capping for this PBS nanoparticle?
Sir, just when we started this work, we just studied the bovine serum albumin, and there were various amino acids. I remember 600 types of amino acids are present. So just to study the capping ability, stabilizing ability of this bovine serum albumin, because the similarity between our surfactants, erstwhile surfactants, and bovine serum albumin were a little bit surprising for us, that it is a very good shape directing agent. And just the purpose was to change just the temperature and exploiting the denaturation of this denaturation characteristic of this BSA.
So I think, sir, if you will use any protein, you
Yes,
will
sir.
get same type of result. All protein have a denaturation at a specific temperature.
Yes,
Right?
yes, sir.
Right? If you will go beyond the 50 degrees centigrade, most of the protein will denature.
Yes, sir. Yes, sir. So people are using HSA also, sir. So it was, I think 5-7 years back, we did this work. So I saw people have used HSA also. So just the purpose was to stabilize the nanoparticles and look for some biological molecules.
Generally, most of the biological scientists work in a reverse field. They
Okay.
want to see the impact of nanoparticle on these proteins, because human serum albumin is mostly present in the blood in a
Yes, sir.
enormous amount.
Yes.
So when the nanoparticle enters as a biomedicine in the human body, then how it is affecting the protein structure? That's the major question for biological scientists. But you are just doing the reverse direction, use as a capping for this PBS nanoparticle.
Yes, sir. Just the purpose was to get well-defined morphologies from synthesis point of view. So that was the prime objective. So definitely all the mostly biological scientists, they are working in the reverse direction. Definitely.
Yeah. Okay. Thank you, sir.
Thank you.
Thank you.
Thank you.
Any other question?
Yes, I will be delighted to answer. Few students.
No question. Thank you for your enlightening words and discussing the amazing characteristics of several nanomaterials. Thank you, sir.
Thank you, ma'am. Thanks a lot. Thanks again.
It will be a privilege for me to invite Dr. Ashish Sani, Scientist F and Divisional Head of Advanced Fuse Development Division, TVRL, Chandigarh. Dr. Sani has over 24 years of work experience in fuse development and MEMS devices. He has received several accolades for his contribution to the design and development of advanced material. Sir, I request you to enlighten us with your thoughts on advanced materials and discuss the application and challenges in the domain. Welcome, sir.
Thank you, ma'am.
Once again, good morning to all of you. I am Ashish Saini, working in TBRL Chandigarh as a scientist. I kept my talk very general. So after a heavy technical talk, I kept my talk very general. What are the different advanced material required for defense? What are the challenges and what are the opportunities? Initially, I had taken a topic of applications of materials. But then I thought over 3 days, you will be hearing continuously different applications. So I just changed it to opportunities and challenge. What are the opportunities lies ahead? And what are the challenges associated in development of new materials faced by the Material Science Society researchers? So this is a simple periodic table, which shows all the current elements which are existing. If these elements doesn't react with each other, the life of material scientists would have been very easy. But the problem is that they react with each other, different compound in different proportion with different other elements. And that makes a life of a scientist or a material scientist very complicated and challenging. And moreover, this is the main reason for responsible for giving the birth of material science and material scientists. So for this reason, you all are here. So what is material? I had taken some general slides just for the sake of completeness. ताकि आप लोग जागते रहें और एकदम से बोरिंग टॉपिक पे आके सो ना जाएं. So what is material? Material is basically everything is made of something, and that shows the importance of material, and that something is material. So whatever you feel, whatever you see, that includes everything, and everything is made up of some material. So this is why the people are so much interested in developing new materials. So material is a substance, normally solid, but often condensed phase that is intended to be used for certain application. And the main classes that were initially classified as metals, semiconductors, ceramics, and polymers. And new and advanced material includes nanomaterial, biomaterial, and energy material, etc. So whole of the engineering material, this revolves around metal alloys, compositions, biomaterials, ceramics, semiconductors, and polymers. And the life of scientists is revolving around studying their structures, their performance, their properties, their processing parameters to get a particular character, what is desired and what is intended from that particular material. So after material comes material science. So basically it is a study of solid material and how these properties are determined by a material's composition and structure. So material science is an amalgam of different field of studies, that is physics, chemistry, biomedical, nanotechnology, mechanical engineering, electrical engineering, artificial intelligence nowadays, machine learning, and everything. That makes a part of material science development. And with basic understanding of the origin of properties, materials can be selected or designed for an enormous variety of application, ranging from very hard structural steels to a highly sophisticated electronic microchips. So these materials, they find application in almost all domains. For example, for electrical engineering in conductor, magnetic materials, insulators, in telecom, alumina, various type of ceramics, optical fibers, and other type of fibers. Energy conversion, main application is in solar cells, supercapacitors, batteries. These are some of the applications I try to list in different type of technology domains, but they're not restricted to this. In aerospace, it can be heat resistance material, composites, lightweight composites, heavy duty and high strength composites, nanoparticles. In nuclear engineering, development of different type of fuel with higher and more efficiencies, reactor materials so that the reaction can be taken at a faster pace, developing more and more energies. Instrumentation, development of various type of silicon materials, sensors, and biomedical, bioceramics, nanomaterials, electronics engineering, including semiconductor, flexible organic electronics, and so many applications. And when we come to defense, almost each of the engineering field or technology in standalone form or in integrated together are used in one or any other subsystems. So all the fields, including different type of material development, they are employed in the all defense systems. From material to material science to advanced material, which is one of the theme of this conference. So advanced materials, they are engineered material. Normal material can be developed with a simple process without doing any engineering, just mixing them and getting a material. Now we have includes an engineering approach to get certain property from those specific material. We call those advanced materials. And the properties can be totally new novel materials or improved properties to replace the existing one with a lighter weight, higher strength. They can be formed in any other shape, whatever is desired, have higher or better conductivity, and so many property. There can be many properties together in a single substance or material, or there can be single property existing in a particular material. Some example of these advanced materials are light materials, including titanium, magnesium, aluminum alloys. Composites includes carbon fiber, Kevlars, nanocomposites, metal laminates, steels, alloys of various other components, etc. So this picture shows application of advanced material in different defense systems. I think the picture is clearly indicating different type of systems like carriers for ammunition like guns, ships, naval ships, fighter aircrafts, electronic subsystems and electronic systems, ammunitions including bombs and shells, protective clothing on which Dr. Sanjeev has already given a very elaborate discussion, deep bunkers to protect humans and ammunitions, and explosive and propellant to increase the efficacy of any system. Why we require defense materials for defense? What is the importance for defense? So if we see by history, in the last 3,422 years, only 60 to 68 years were there where there was no conflict between any two countries all over the world. So this shows the importance of a defense force that every nation should have. And to be prepared for war is one of the most effectual means of preserving peace. It was said by George Washington, and that's true in current scenario also, why Russia has not attacked US and why it has attacked Ukraine only. So why it matters is because advanced material, they can shape the future warfare in any way that the human wants to shape it. Out of 118 elements that are existing in a periodic table as on date, only 39 are the identified elements which are in one form, in alloy form, or in mixed form. They are used for defense application. Rest, they are normally not used or doesn't find suitable for this particular application. So some includes metal, rare earth element, precious metal, and non-metals. And most of the research in material science revolves around these materials only. So in defense arena, what I had shown through picture, I'd tried to make it in word form that for platforms like tank, aircraft, naval ships, submarines, we require different material. For example, if we are going for a submarine, when it is going into deep dive in a sea, we require a very high strength of material which should be able to take those type of loads. Moreover, it should have a property of weldability so that a complete structure can be made through that material. If a material or a composite which has a very high strength, but it is not formable or weldable, is of no use for certain these applications. Similarly, for aircraft, which require a very light material with a high strength so that it carry more and more payloads under its belly and with a very high maneuverability. For support systems, we require for radars, communication systems, bulletproof jackets to protect humans, NBC suits. In ammunitions for propellant, explosive, so that the efficacy of a system can be increased with a slight less number of weapons, we can have more and more striking capabilities for weapons. For penetrators, like you should have a high strength steel, we should be able to penetrate and take up the penetrating load through its surface without affecting the performance. Similarly, for weapons like missiles, guns, torpedoes, lasers, microwave weapons, we require advanced and sophisticated of material to meet these certain requirement. Like for missile, if it is going into exothermic zone, the temperature at the nose is something around 2000 degrees centigrade. So the material should be light enough to be carried and should be heat resistant enough so that the internal systems, they are not get affected at all. So material technology basically underpins almost all defense systems and is a key enabler for significant improvement in performance. So starting from a raw material that can be any metal or any alloy like aluminum, titanium, which are used to through some processing, used to build some semi-finished material like different alloys. So based on these alloy, various components like wings or turbine or any other systems, their components are built. And integrating these components, we make different subsystems for different type of systems. Like for airframe, propulsion, turret, different component are combined. Then different subsystems makes a defense application or complete system like fighter aircraft or battle tank or any other system. And these systems comprises of a defense sector. So the foundation or a basic thing is a raw material and advanced material to build these different type of application components, subsystems, systems, and then different sectors. So these material for the particular defense application, they had a different type of requirement for different application. There can be certain smart material which are able to provide many qualities, or there can be integrated material which can be used for a single application and integrated with other materials. So physical, I think the slide is not visible. So physical requirement includes weight and quality characteristic. Requirement includes it should be able to sustain different type of environment like low temperature, high temperature, vibrations and all that. It should have a camouflage, concealment and deception requirement, resistance to flame and heat, specific battlefield requirement and economic consideration like it should be producible, it should be manufacturable, it should have low cost. So the material development has to take care of these different type of requirement, and more qualities or the capabilities has to be built in a single material, this giving rise to a development of various type of advanced materials. So we classify advanced material for defense application. Normally, they can be classified into two categories. One is structural material and another are functional material. So structural material are basically used to provide the strength to a particular subsystem or system, and functional material, they are responsible for carrying out certain functions which are intended to be carried out by that particular system. So structural material, they should be able to take the loads of the system without getting deformed. This includes steels, aluminum alloy, titanium alloy, nickel-based superalloy, copper, tungsten, neodymium alloys, polymers, matrix composites, ceramics. And functional material includes semiconductors, which are used in different electronic applications, magnetic materials like ferrites, high energy materials, which are capable of giving more and more explosive energy in the form of explosive as well as in propellant. Piezoelectric material, which are sensitive to different type of environment disturbance and able to derive a signal for electronics. Shape memory alloys, radar absorbing material, which are used on aircraft to protect or give their signature to enemy. Different type of coating for thermal as well as electromagnetic interference. Then for fuel cells, textile material, optical material. So these are the different functional material which are specifically developed with certain properties to deliver certain functions. So in the last 30 years, the use of composites in different type of structural material has increased manifold. Although in defense, we are still using most of the metal and metal alloys to provide high strength. Why I will explain in next slides. But in commercial sector, the use of composite has increased manifolds. Like for Boeing, almost in 30 years, where the use of composite was almost 1%, it has increased to 50%. And there are many good qualities of composite due to which these things, the percentage of contribution has increased in the aircraft. So if we see the ships, the requirement is a high strength steel with adequate ductility or elongation, excellent impact toughness at sub-zero temperatures, excellent weldability to build a big structure, and it should be good cohesion to water since it is immersed in water for many years. So different materials are already developed, and most of the development happens when we are not able to get the things from outside. Mostly after 1998, DRDO was not allowed to procure things from outside, or most of the country, they are not giving many things to India. So that time material development in DRDO has taken place at a very faster rate, and we are able to develop many steel and alloys material for different type of aircraft as well as ship applications. So next requirement is body armor protection. Since soldier is main workforce or main asset of any nation. So protect the soldiers, we use different type of protective clothing so that they should be durable, compact and lightweight. This figure shows a simple experiment which was carried out using a small bomb. If the soldier is not using any of the protective clothing, so there is a maximum damage. When you use a only helmet, the damage reduced to almost 20%. If he wear a armor, the damage reduced to 40%. And if you wear a complete body suit, including helmet and armor, the damage to a particular soldier reduces to 80%. So this emphasizes the importance of protecting a soldier, which is mainly on the battlefield. So this is one of the most researched area in defense application, how we are going to protect, how we are going to give more and more protection by reducing even the weight of that particular clothing. In electronics, we have different electronic material like semiconductors, insulators, conductors, organic and polymers, composite material, magnetic material, and a lot of variety of them. Now, coming to the major challenge that is involved in development of any new material. So if the development cycle for any new material lies somewhere from 2 to 3 years to almost 15 to 20 years. And this is not the scenario in India. This is world over scenario. And this is reported by Shefrick from GE Aircraft Engine. He says that if we are already using the existing material for a non-critical application, including airborne application and other defense application, the development time is 2 to 3 years because it has to be certified. It has to be tested against all the parameters. But if we are using this similar material in certain critical applications, the development period increased to 5 years. And if we are developing a new material for which the science was already existing, some expertise in the workforce was already there, the development time takes about 10 years. And if it is a totally new material where we don't know what it is, just we are developing it based on the application or on the requirement, the development period ranges from 15 to 20 years. And same is true in Indian scenario also. We also take same type of development time. Why this problem is there for defense particularly? The main challenges are the requirement is low and sporadic. Sporadic means they are spread over a period of time, not regular requirement. Sometimes we had a requirement, sometimes we don't have requirement. The requirement is low. This can be explained by a simple example. The production rate of steel in India is almost 130 million tons per year. However, for defense, we require only 10 to 12,000 tons per year. So it is less than even a single 1%. So most of the industry, they are not interested to invest in this field for a small volume that is required. Moreover, there is a stringent qualification and certification process, and industries, they are not interested to go in that large loop, which takes about 4 to 5 years for the certification qualification. Number of tests, number of certificates has to be generated at different conditions, and industries normally looking for their interest in short time, not investing so much price in this. One common example is 7,000 alloy of aluminum, which is not developed in India. Although the capability exists, the infrastructure doesn't exist in India. Tentative amount of about 800 to 1,000 crore is required for developing these type of materials, which no one is ready to invest considering the small requirement. Moreover, the designer expects that every material in all product forms should be available indigenously, and that too at a cost lower than that available from the global source. So these are the major challenges due to which most of the Indian industry, they are not coming up to take up the development of new material to qualify them and to implement them as a product in the different type of systems. This slide, this explains how the development period increases from almost 2 years to 15 years. The first section shows the material science development time, which is almost 2 to 4 years for any material. A lot of excitement is there, a lot of enthusiasm is there, number of scientists, researchers from academics, they are involved in this. And daily almost 1,000 materials are developed and reported. So it takes about 4 to 5 years. People are working on a small particular thing with specific parameter, and they are developing new material and reporting them. But when we go from first phase to second phase, almost 90 to 95% materials, they doesn't qualify for the second phase, because second phase comes for the technology requirement, where the material should have a particular property to be used as a product in certain application. Like it should have a joining property or a machining property. It should be clear for non-destructive evaluation. Process should be standardized so that if we require a bulk production, we can go ahead with that. And then property database should be available, should be made available to the users or certifying agency and repair. So this period takes almost 8 to 10 years, and hardly 5 to 10% material which are developed in first phase goes to second phase. After completion of second phase, then cost and yield optimization is done, and they are used in different subsystems. So this again implementation take about 2 to 3 years. So this is how the development cycle increases from 10 to 15 years. However, this cycle can be cut down with certain approaches. So if we are having a complete database of material with us, it can be shared with design team as well as manufacturing and system engineering team. Both team separately can study those, and then they can cooperate with each other to understand what the design team requirement is and what are the manufacturing capabilities and compatibility with the system is. So we require a cultural shift in material R&D development. This includes system design and development is outpacing the material development cycle that I had already explained. System development time is hardly 4 to 5 years. No user is willing to wait for 15 years or 20 years for development of any system. However, material development for that particular application currently taking 10 to 15 years. So the system design and development time is outpacing. So the material development time has to be cut down drastically as fast as possible. Then again, qualification and certification procedure are such that the insertion of new material is becoming much more difficult and less frequent. If you are using a 30-year-old material, people are not willing to change the material because it has to undergo a complete certification process. So they say, let it go, whatever is going. So that is not increasing the quality of system that we are currently having. So the current and futuristic approach that is already started world over are two approaches. First one is integrated computational material engineering approach, and second is materials genome initiative. The first one is an emerging discipline which aims to integrate computational material science tools in holistic way for acceleration of material and development. So we have a database, we have a computational set on which we have developed certain material that is available. So when we are going to develop a new material, we are taking that computational capabilities and developing new material. So world is almost moving to this space. And the second is material genome initiative. So this is like studying the genes of a material. So to study the genes, you should have everything available. You should have experimental tools available. You should have a design tool. You should have a computational tool. Combination of this tool working in an integrated manner. So this approach has to be followed if we want to reduce the development time of any material. But these have a limitation. So this is a simple material development cycle from discovery. Then you go for development, property optimization, system design, system integration, certification, manufacturing, and then it goes for production. So if you are having a computational tools or a complete database, we can insert at different level parallelly. So each level can work parallelly based on the initial input that is available, and the process can be fastened in a very shorter time. Now, the challenges in implementing this ICME and MGIR, we require a cultural shift in material research development and deployment. Then integration of experiments, computation and theory, access to digital data and well-equipped workforce. What I mean by this, cultural shift in material development, material R&D and deployment. Currently, there is a collaboration between scientists who are working in a very narrowly confined field. Like someone working in processing, they will collaborate with those who are working in processing. Modeling person will collaborate with those who are working. So integrated approach is required where all these different field person can together sit and then discuss, learn from each other and develop new material. This will be more fruitful if it is across all three domains. So the multidisciplinary approach will accelerate process. And the bottom line is encourage and facilitate integrated R&D in all the academic and research institutes. So the next is integration of experiment, computation, and theory. Integration of tools, theories, models, and data from basic scientific research with the processing, manufacturing, and development of material has to be clubbed in a single source so that that is available for all the researchers, students that are working on it. And then creation of material innovation structure has to be taken up by all academic and research institute where a different field can be integrated together, providing access to digital resources as and when anyone requires them. Then we require a well-equipped workforce. The next generation students or researchers must be trained in these research methods. Students engaged in synthesis or processing must have enough training in material modeling, and those who are working on modeling, they should have a good exposure to the synthesis method. Then continue update in material science and engineering curriculum at all academic institute as well as department that contribute to the discipline. So we have to start new curriculum development and their implementation at the earliest. Now coming to my last slide, this includes various identified key research areas, which includes nanomaterial, metamaterial, materials for energy storage and generation, and multifunctional materials. And the research gap that are existing in different fields are cross-disciplinary teams for novel materials, rapid modeling, mass customization, sustainable manufacturing, smart products, integrated computational material engineering, additive manufacturing, nanoscale energetics, structurally related materials, metamaterials, and a list is very large. So there are a lot of opportunities for new persons who are coming in this field. They can take up any field, do an integrated research with other, move out from their domain, discuss with other users who require these material, understand this, do a modeling simulation and develop the material, and that can be used in a faster way in different type of application. So this was all from my side. Thank you and Jai Hind. I would like to thank Shulin, Amity University for inviting me. It has always been a pleasure to give a talk on a new topic. And the pleasure increases manifold if you are invited by your guru or your teacher who had given you a lot of knowledge and done your PhD guide. So I'm thankful to Preeti Thakur Madam and Atul Thakur sir to give me opportunity to be here. Thank you, sir. Thank you, Ram.
Hello. Wonderful presentation, Dr. Ashish.
Thank you, sir.
I have one question
Sir.
About proximity fuse sensor, like how we can use ferrites for proximity fuse sensor, and at what frequency these sensors work?
Sir, proximity sensors basically they are used to sense a particular distance. So they use an antenna. And antenna, when you are using for a particular weapon application, normal antenna doesn't survive in this environment. So mostly people prefer patch antennas. And patch antenna work, they have two conducting surfaces and between there is a dielectric material. In last 20 years, the research on dielectric material has almost saturated. So whatever the maximum permittive we are able to obtain, we already have. So ferrites, they have a property of higher permittivity as well as permeability. So if we are able to get both permittivity and permeability from those material, we can reduce the size of antenna, reduce the size of proximity sensors for a particular application.
Thank you. Thank you.
Thank you, sir. Thank you.
So please, you'll have to wait here. Thank you for your informative talk on highlighting the challenges of the defense sector and opportunities that lies towards the research on nanotechnology. Now I request Professor A.S. Rao and Dr. Atul Thakur to please come on the stage and present a memento to Dr. Ashish Saini on behalf of MAM 2023. So please. I request Dr. Atul Thakur to present a souvenir to our session chair, Professor A.S. Rao. We will now be beginning with the technical session 2 of the day. This session will be chaired by Dr. N. Vijayan, Senior Principal Scientist at National Physical Laboratory, CSIR, New Delhi. We welcome you, sir. I am honored to welcome Professor A.C. Sun, Department of Chemical Engineering and Material Science, Yuanzi University, Taiwan, Dr. Palas Kumar, Cosmoferrite Limited, Solan, Himachal Pradesh, Professor H.M. David Wang, Professor, Graduate Institute of Biomedical Engineering, National Chung Hing University, Taiwan, as our invited speakers for this session. Connect.
Hello. So, can you
Hello.
hear me?
Yes, sir, you are audible.
Okay.
So we welcome you, sir.
Yeah, so I will share my monitor. Just a moment.
Hello. Hello, Dr.
Yeah,
Sun.
yeah, I
You
do.
can, yes, hello. How are you?
I'm okay.
Can you see my back?
I'm trying. Just a moment. Okay, let me try.
Okay. Take your time.
Hmm? Okay, can you see?
Yes, we can see, but can you see us?
Yeah, I can see all of you. So,
You okay now?
no, not well. So here's my slide.
Yes, it's there. We can see.
So now it's okay?
Yes, perfect.
Okay, so may I start right now?
Yes, please start.
Okay.
Thank you very much.
Thank you, Takuo.
Yeah.
Hello, everyone. My name is Aiden Sam. Now I'm in Taiwan. I'm a full professor in Department of Chemical let me use this one. Okay. In chemical engineering and material science in Yunzi University in Taiwan. And it's my great honor to, because the professor Atu Takuo is my good friend when he was a postdoc in Taiwan. And I guess we are roommates. So I accept this invitation. Today I will give it a talk. The talk is about the high Ku material. Let me introduce this topic first. Okay, low temperature preparation of high Ku L11 cobalt platinum thin film for soft substrate. Why we prepare this one? Because in magnetic material, high Ku material always need a high ordering temperature. The temperature usually more than 200 degrees C. So for further using, we will deposit the magnetic material thin films on soft substrate. But 200 degrees is too high to deposit on the soft substrate. So we have to first reduce the ordering temperature. Okay, let me start my talk. Okay, this is my outline. I will give a brief introduction and why we need a high Ku material and why we need a low ordering temperature. Then we designed an ultra high vacuum sputtering system to do this material. So I will show some experimental procedure. And I also will show some results and the discussion, include we insert a platinum as an underlayer, and we change the annealing temperature and single layer thickness. Then we'll show the mechanism why we can reduce the ordering temperature and give a simple conclusion. Okay, I guess everybody understand this slide. This is all about the magnetic material, the application of the magnetic material for the needle, the magnet, and this one neodymium iron boron, and electromagnetic motor, servo motor, spin motor, also the powder. And now the massive usage is in the hard disk driver, include the recording media, okay, on the disk, and the sensor in the head. And we use the hard disk driver in the laptop, PC, and also the video camera. This is the smallest micro disk. It's about okay, this is a Japanese dollar or Japanese yen. This is size, and we collect all the hard disk driver. It becomes a cloud drive. Also, we use the magnetic as the switch to turn on or turn off something, and the GPS, the sensor, power steering, also the Hall effect. This all use the magnetic material, magnetic property. Okay, in the future, the massive using, we will use the neodymium iron boron in the electric vehicle. Okay, this is a neodymium iron boron, and the future now we always need a high pH maxima. So now it's more than 2010. But it's still at this point, okay, about 60 mega Earth state. This is the pH maxima. How can we calculate? So the neodymium iron boron also in my lab in Taiwan, we study the neodymium iron boron and also the samarium iron nitride. Okay, now we study these two materials right now. For the fin type, okay, we just mentioned the bug type. Now the fin type. Fin type, we deposit the fins on the hard disk driver, on the disk for recording. Okay, the data stored in the data storage you can keep the data more than 10 years. So some property mass approach, we usually use the iron platinum, cobalt platinum, and the MNG, this material in head and on disk. So it's a sensor and the media. Media on the disk, we call the media. Okay, so the recording material will be the cobalt platinum system, iron platinum system, but they are hard magnetic property. They have hard magnetic property. But in a sensor like this one, in the sensor here, and this is a head, the GMR sensor. Okay, we still use the thin film and the ferromagnetic film as the fixed layer. Okay, this is fixed layer. So fixed layer here to pin over to to pin the magnetic moment of the up layer. So the pin layer also needs a high Ku material because we need a high coercivity. So in the future, we all know the things becomes more thinner, more smaller, like this one. Okay, in Taiwan, in the company TSMC, Taiwan Semiconductor Manufacturing, TSM Manufacturing Company, already announced, everybody noticed in the world, already announced the 3 nanometer process already produced in United States. Now in Taiwan, we already prototype. We already have the prototype of the 2 nanometer. Okay, so that means the next age we will switch to the 2 nanometer. So that means that since all the component, all the device must be thinner, smaller, and compact all material becomes more complicated. So it's a multi-functions, but it's a dilemma. We cannot reduce the volume. Sometimes we call it magnetic volume or switch volume. We cannot reduce the volume and still keep a good magnetic property, high coercivity, because these two limitations. The first one is a Stoner-Wolfers limitation, means that this is the Boltzmann constant, and this is the temperature. Okay, for example, room temperature or Boltzmann constant and the room temperature, the number must equal over than 60. So the data storage can keep more than 10 years. If lower than this number, maybe 5 years, the data disappear. But we already told we cannot increase the size. We must reduce the size because thinner and smaller is our requirement. So the volume, we have to reduce this one. And in order to maintain this number, we need a high Ku material to maintain this number. Okay, and this one also, we continue reduce the grain size. Of course, the coercivity also increase with reducing the grain size. But you cannot reduce more because in this region becomes a super paramagnetic. The super paramagnetic means the magnetic property, magnetization, reorient, eventually disappear. So all the data, all the magnetic property disappear as this region. So it's a dilemma. We want to small volume, and we still want to keep a high coercivity. It's very difficult to keep them well. But we can find some material. We try. So the table shows many high Ku material. For example, 20 years ago, we used this material as a thin film material. And this material, the Ku is 0.2. The minimal stable grain magnetic grain size is 10 nanometer. And then we switch 2005, 2006, switch to the iron platinum. This one has a very high Ku anisotropy field, anisotropy constant, and the minimal stable grain size could reduce to 2.8. Okay, also the cobalt platinum 3.6. This one, neodymium iron boron, okay, still has a high Ku, and the size could reduce 3.7. So these are suitable material that we can use in the next generation. Okay, let me talk about the L10. You maybe ask me why ion platinum we choose, because this one, we like this one because the chemical stability is really good, better than others. So we choose this one. And this one also has the high coercivity, good saturated magnetization. And we can prepare this one with the perpendicular magnetic anisotropy. The stable grain size could reduce to 2.8 nanometer. This number is really small. But this material has a drawback that as room temperature prepare is A1 phase with a poor magnetic property. This one must pass through the high temperature. The temperature will be more than 450 degrees, so we can get a 10 phase. This is hard, or sometimes we say the good magnetic property, this phase. But with this temperature, it's not possible to use in the softer matter, okay? Because this temperature too high will melt this material. But future, we need a softer matter everywhere. So this is our challenge. We have to overcome this problem. So we think the only way, we have to look for a whole new magnetic material which can be prepared on softer substrate and still present good magnetic property. Therefore, we found this one, L11 cobalt platinum. Let me introduce the L11 cobalt platinum. L11 type cobalt platinum alloy thin film is a meta-stable phase. Meta-stable phase means we cannot find this material in binary phase diagram because it's meta-stable. In binary phase diagram, it always shows stable phase. There is no meta-stable phase. So it's very difficult to figure out, okay? The atomic number, the ratio is 50 to 50. The easy axis is this direction. So if we can deposit, make the O10 cross picking along this direction, we can get perpendicular magnetic property. And this one also has a high saturated magnetization, high chemical stability, high magnetocrystalline anisotropy. But this one really good. We just need a low ordering temperature, about 250 to 350. We can prepare this one. So it has a possibility to use in a soft matter. Okay, 1997, a Japanese, these guys, Iwata, already studied this material, but use the MBE, molecular beam epitaxial growth. We all know that in semiconductor process, MBE, the sputtering rate is very slow. So it cannot be used, applied in a mass product. We try to prepare this one, cobalt platinum thin film with L11 structure. But this time we use the sputtering. And we successfully prepare this one. This material is very interesting. Okay, if you deposit this one as lower temperature, lower than 250, it's A1 phase. So the magnetic property is very poor. We cannot use this one. But if you deposit this one between this temperature, 300 to 500, it's transferred to the L11 structure with a good magnetic property. If you continue increase the annealing temperature, then it switches back to the poor magnetic phase, A1 phase. Then you continue, increase the temperature to more than 700 and 750. It switches to the stable phase L10 structure. So from the room temperature to the high temperature 750 degrees C, there are 4 phase structure. So this one is very interesting. Okay, this is our sputtering system. We use the cobalt and the ion, the cobalt and the platinum here. Other material we don't use. Okay, we don't use because some other student use this material. This is my ultra high vacuum sputtering system. So we use the alternative sputtering method, make the layer to layer deposition. Then we check with the AFN, NFN, VSN, SEN, X-ray, EDS, and the transmission electron microscopy. Okay, so we call the atomic layer by layer deposition. Okay, this is a cartoon figure. Okay, then show you how we prepare this material. Okay, this is a substrate rotate, 1 layer platinum, 1 layer cobalt, 1 layer platinum, 1 layer cobalt. Okay, then we can get the structure layer by layer, like this one. It's a Lomohydro structure, layer by layer. Okay, this is our result. First, we studied under layer effect. We try to edit a platinum underlayer. Okay, this one. Okay, here there is no platinum underlayer, so only the glass substrate. Okay, this one we insert a platinum underlayer on the glass substrate. So what we found? We found the perpendicular magnetic property present after we insert the platinum underlayer. Also, we try to change the single layer synchronous. This one cobalt 2 nanometer, platinum 2 nanometer, and the cobalt 1 nanometer, and the cobalt 5 angstrom. So we get the good clear crystal structure, which is the L11 structure. Also, we have a good magnetic property. This is the cross-section TEN. We see this one without the platinum underlayer. Okay, the crystal structure is not very good, not clear, and have a different orientation. But here we insert a platinum underlayer. Here you can see the platinum, the orientation is very clear, and the things grows along the platinum underlayer. Sometimes we call it AP growth. So then we change, okay? We change the post-annealing temperature from the room temperature to the 300 degree. Then we try to change it, okay? We try to increase the periodic number, the repeatable, okay? Repeat times from 2 to 10. So this is our result of the temperature effect from room temperature to the 100 to the 400. Then we found it's interesting as room temperature is already perpendicular. Okay, this is our goal. Then 100, the squareness is good. 200, 300, we has a higher coercivity, and the 400. So also shows in the X-ray or in the crystal structure. Later, we stated this one. This one, we calculated the magnetocrystal and isotropic energy. It's about 1.2 times to 10 to 7. And based on the MH curve, the hysteresis curve, we choose this one as our suitable condition. Not optimal. I cannot say optimal, but we can say the suitable condition to further to continue other experiments. So this we change the synchronous. The total synchronous keep the constant. Okay. Oh no, total synchronous is change. It's a 0.44 angstrom and the 5 angstrom platinum and the repeatable deposition. Okay. So it's n equal to 4, 6 to 10, and we found all sample present a perpendicular magnetic property. Okay. Then but the Ku and isotropic constant reduce slowly, okay, with the repeatable number, and the anisotropic constant also reduced. So that means we need a thinner, like this region, we need a thinner. The total thickness cannot be too high. So the SRD also tell the same thing. If we increase the total thickness, eventually we get the crystal structure, okay? But it's also decrease the stacking quality. So the magnetic property also declines. So it's our cross-section microstructure from the transmission electron microscopy. And you can see this is the picture shows it's a platinum underlayer. This is a copper platinum magnetic layer. And we can see this look like the grand boundary, and this one also have a little grand boundary. So we can see it's look like the grains look like columnar grain structure here and here. So we can see briefly 3 grains in this picture. Okay, let me see this one like this. Okay, it's a 1 grain, another grain, and another grain. So it's easy to understand. That's the growth direction from bottom to top, and becomes the columnar structure. Okay, why? This is our mechanism. We try to reduce the ordering temperature. How? We use the layer by layer to layer distance. The D-spacing, this one, this there, and this there, the distance. We control the layer to layer distance. Okay, use the sputtering technology. Okay, each time we deposit 1 layer, 1 layer, 1 layer. So we shorter the diffusion length, and it could lower the ordering temperature. So we can image it that because the diffusion need thermal energy to completely finish the diffusion. So if we give the sufficient thermal energy, the atoms will move to its suitable lattice site and finish the diffusion. So if a long distance, we need a high thermal energy. So we try to control the distance, the atom, we try to reduce the distance, the layer to layer distance. Okay, make the atom no need to move too long, so they can go to their suitable location and finish the diffusion. So we don't need a high thermal energy. This is our way. So use the layer by layer structure. Okay, this is my conclusion. In this study, perpendicular magnetic anisotropy, a 1,1 type couple protein thin film could be prepared on glass subject at room temperature by alternative sputtering of copper and the platinum layer. The proper thickness of copper and platinum is 4 angstrom and 5 angstrom. Okay, in the maximum Ku anisotropy energy is 1.2 times 10⁷. Our studies may provide a way to fabricate a high Ku material at low temperature. It could be the best to deposit a hard magnetic phase on the soft matter. And this is my remember. Okay, this is Professor Atu Takuo. Okay, last year, November, I remember November, Professor Takuo visits my university, my department, and my lab. And this is my postdoc, Mary Homosa. This is my PhD student from Yunnan. And this also after the Professor Takuo is my student from the Pakistan. And we thanks to the MOST, give the budget, support us.
Yes,
And I
thank you,
also
thank you.
use,
Dr. Sun,
okay, yeah.
can you see me? The same t-shirt today?
Okay, just a moment. Yeah, 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 yeah.
It's the same magnetism, magnetic material, thin film, nanostructure, hysteresis loop. So it's quite inspiring. And thank you very much. Like on a short notice, you agreed to address our students, our research scholars. We have distinguished eminent speakers sitting here listening to you very patiently. So I really thank you very much. Okay.
Okay, thank you, thank you.
You can see plenty of students, masters and PhD students, staff, teachers, everyone is sitting and they're enjoying your talk, and probably they will look for, to work in your lab as postdoc, or some of them, the inspiring student to do PhD in Taiwan in UNZ University. So I know you have a very fantastic world-class facilities to deposit thin film for high density memory storage. And I'm also adjunct professor in your university. Thank you very much, and convey my regards to the dean. And
Okay, okay,
definitely-
okay. No, he understand. I give a talk today. The dean already understand. Also the chairman.
Yes, yes, yes. Thank you very much. So I'm starting with a question. Uh, can we use ferrite for high density memory storage?
Ferrite high density magnetic storage possible if there is a material we call multiferroic.
Yes.
Multiferroic, the coercivity could higher than 3 kilo state. That is possible. Multiferroic. Even not multiferroic, if we just want to use the ferrite, at least, I mean for the recording, only for the recording, not for the head. Only for the recording, the coercivity at least have to over 3 kilo oyster.
Okay, okay.
Yeah.
So how much is the optimum value for KU?
KU, you better higher than the like 10 to 7.
10 raised to power 7.
Yeah,
Okay.
yeah, 10, yeah, then 10 to 7. Yeah.
Okay, okay. Thank you. So my colleagues, they also have some questions. You can come in.
Okay.
Good morning, sir.
Yeah, good morning. Hello, where are you? We welcome the students from India. So if any students you finish your bachelor and you want to join my university, my department, also my lab, okay, please go to the website. Okay.
Hello, sir, am I audible?
Hello.
我有听到，
But
现场好像
so right now, what we are waiting for?
the microphone have some problem.
Oh, I see. I see. We can have a chat first. So, Alden, will you go to Seattle in October?
I am
I hope you
considering
can. Yes, James, Leo, and me will go. So how about we
the
can?
James and Leo.
James,
James and Leo.
Leo, and me
Okay.
will go.
So
So if you
okay.
come, so 4 persons, we can rent a car or something else. So
Hello,
that would be
hello.
wonderful.
Okay. I
Hello.
am considering I want to join because I have to
Okay.
finish the abstract first.
Hello.
Hello,
Hello.
we are chatting.
For another trip.
Hello. Hello.
Hello.
Yeah, we are talking about we will go to the
Hello.
United States.
Hello. Yes, all together.
Okay, welcome.
Hello. 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 Hello.
Hello, I can hear.
Sorry.
Yeah, sure.
I'm sorry. There was some technical problem in our central. Hello.
Did you pay the fee?
Hello.
No, not yet. Not yet.
As R2, did you pay the fee for the equipment in this room?
Hello. Hello, Professor Sun.
Yeah, I'm here still.
We were listening your nice conversation among Professor Sun and Professor David. And who's going to pay the fee?
You mean by air or by cash?
No, we'll go by ship.
Okay.
Okay. Anyways, we have some technical glitches now. It's overcome. I have Dr. Ashish Saini. He has one question for you, Professor Sun.
Okay.
Hello, sir.
Hello.
Good morning.
Good morning.
Sir, I just want to know there are few techniques available to measure the crystal size. What is the minimum possible crystal size that can be measured with the currently available equipments?
You mean a minimal stable grain size, the meaning?
Yes, sir.
The minimal stable grain size means, okay, it's a limitation. Over that grain size, we can keep the magnetic property well. Okay, if a lower than that grain size, there is no the magnetic property disappear.
No, sir, I'm just interested in measuring the crystal size. I'm not worried about properties. Just want to measure what is the current possible minimum size measurement capability that is available.
I don't understand what's your point.
Actually, he is trying to ask you what is the minimum size in nanometer we can measure with the help of any instrument, like is it 2 nanometer, 5 nanometer? His question is basically related with the instrument.
About the instrument, you mean what size we can measurement?
Yes. What is the possible size, minimum possible size, which is measured till date with the help of some instrument?
And right now, we can check. If my information is correct, we can check the minimal grain size until now is 5 nanometer. We can approach right now in Taiwan. 5 nanometer with the granular structure. That means some oxide surrounded the magnetic particle. 5 nanometer is okay, but there is a paper that means I remember Science 2000. There is a person in United States, Professor Sang, is already studied 2.8 nanometer is really approached. We can see the TEM. Yeah.
Any question?
Thank you, Professor Sun. Thank you for your
Okay.
time. Yes, thank you. See you soon.
Go to Taiwan. Go to Taiwan.
Yes,
Atu,
yes,
I
yes,
see you. You know, you wear our suit today.
yes. Especially, I'm just to impress you.
Mm-hmm. Yeah. Take some time to Taiwan. Okay.
Yes, sure. Thank you very
Okay.
much. I'll come with
No
some of my
problem.
students or some of my faculties to join your lab. You have a wonderful guest house. You are a wonderful host. You are taking care of guests. You were there at the midnight to pick me up and drop me at the airport.
Yeah.
Thank you very much. Okay.
Okay. Bye.
Oh,
Mm.
listen. Dr. Preeti
Okay.
is also.
Yeah.
Hello.
Hello. Ni hao.
你好.
Yes. We were very happy to listen to your talk, Dr. San. And I think the audience all here were very excited and patiently listened to what you talked about. Thank you for joining us. And we all had a good time listening to your work.
Thank you very much. Thank you to all. Thank you.
So for your educative talk on low temperature preparation of cobalt platinum thin films of high Ku materials. Thank you, sir. Thank you for joining. Sir, shall we continue with Dr. Wong's? Dr. Prakash. Okay. Dr. Palas Kumar has rich experience in material research, product development, and process engineering. During these years of his career, Dr. Kumar has developed energy-efficient ferrite materials for hybrid car engine, low-carbon cement for concrete and building applications, building products using 100% waste residue. I'm privileged to invite Dr. Palas Kumar from Cosmo Ferrites Limited, Solan, to share his ideas about soft ferrites as advanced magnetic materials and its application and industrial practices. Welcome. Sir.
Once again, good morning, everyone. So now I would like to give some idea, some industrial practices and application of ceramic material named ferrites. So lab experimentations and research are conducted aiming to new innovation. But this innovation needs to successfully transform into industry, where broad aspects of science, technology, economics, environment are considered. Technologists face several challenges during this transition. So this needs to be essentially addressed and resolved. Today, I have given emphasis on the novel application and widespread application, of course, and industrial practices of soft ferrite manufacturing, especially manganese zinc. Okay, let's couple of words about the ferrites. Most of you know about the ferrites. What is ferrites? Yesterday, there were several lectures on ferrites. Ferrites is basically a group of, a class of advanced electroceramic component. Yeah. This is magnetic in nature and it contains iron oxide, which gives the magnetic properties as a major component. Broadly, it is classified in two categories, or soft version and hard. Soft ferrites basically, they are easy to demagnetize, but hard ferrites, obviously, this is a kind of permanent magnet, right? In fact, both soft and hard ferrites, these two are functionally, structurally, they are different. Soft ferrites basically are of spinel type structures and hard ferrites have hexagonal structure. Here we will discuss on soft ferrites. If we see the discovery of soft ferrites long back during Second World War, 1939 soft ferrites were discovered in Japan, and the pioneer company is TDK, Tokyo Denki Kagaku. And its major objective was to efficiently transfer the signal from battleship to land through shortwave formation. Right? That time it was very important part. So your airships, from airships to land headquarter Tokyo, it was very important. So this was the basically the reason and driving force of innovation of soft ferrites that time. But presently it is used in everywhere. Subsequently, I'm coming its widespread application. Again, soft ferrites has two major versions, manganese zinc and nickel zinc. I'm coming. And needless to explain that the growth rate of the ferrite market globally, if we see up to 2030, its CAGR is approximate 6 and above. Hopefully, it will be up because of EV, because now EV is coming in the market intensely. Yes, this is the classification. Ferrite is already we discussed. Soft ferrite, hard ferrites. Again, soft ferrite two types, mainly manganese zinc and nickel zinc. There is also copper zinc also, but this is not so important now. Mostly manganese zinc and nickel zinc cover the entire spectrum, hopefully 90% spectrum of the soft ferrite division. Again, manganese zinc soft ferrite can be classified based on function, two major groups, one power grid and another high permeability. Power grid, low power loss and high saturation, and of course, high Curie temperature. High permeability material normally characterized by high initial permeability and low loss factor. Now, raw material used for the formulation of soft ferrites, any ferrites, should be as pure as possible. And you know that the purity of iron oxide, which are used for soft ferrite formulation, which is more than 99.3%. If the purity level is less than 99.3%, the quality drastically deteriorates of the ferrites. Okay. Now let's have some difference of manganese zinc ferrite and nickel zinc ferrite. Yesterday also there are some lectures. Nickel zinc ferrite basically used for high frequency application up to gigahertz level. From common Yes, everywhere. I can show you. This is basically used in EMI EMC applications. Probably you can see this kind of this protection where noise, to arrest the noise and EMI interference, nickel zinc are used. Not only for common electronic circuit, but also it is intensely used in space research, exploration, rocket, aircraft, everywhere, where signal transfer is very, very important. So nickel zinc is especially used for high frequency application. Manganese zinc is basically used in normal frequency up to 10 megahertz. We can use manganese zinc, but beyond that, manganese zinc ferrite doesn't work. And manganese zinc has higher permeability compared to nickel zinc. These are the common aspects of ferrites. Now, if somebody asks why ferrites का application, why ferrite का जरूरत क्या है, and how and why it is so important in modern technological advancement. In high frequency application, there is a scope to save the energy. I'm giving a simple example. आज से 10 साल पहले और 20 साल पहले there was 2G, then 3G, 4G, 5G. So with increasing generation, basically is increasing frequency. The more we increase the frequency of the system of the circuit, the efficiency of the power transformation or signal transformation will be easy and more efficient, more effective, and it will be helpful to reduce the energy of the systems, and which is very crucial in nowadays. So therefore, ferrites are now widely, vastly used in every areas. And I'm giving a simple example. Before 70 years, we use the normal lamp, or then tube light, then fluorescent lamp, then LED. With decreasing the wattage of the lamp, you see the remarkable intensity or lumen of the lamp, just due to using the electronic circuit in the LED lamp systems, and the core material is the ferrites. It helps high frequency transmission and power transfer, which is helping less electricity consumption or power. So this is the main funda of using ferrites everywhere, starting from our charger, laptop, electric light, this camera, everywhere it is used. Okay, now let's have a couple of words about hard ferrites. Though we'll focus manganese zinc ferrite, but yes, we can touch hard ferrites. You know very well, this is characterized by high corrosive. It is very difficult to demagnetize and very resistant to becoming demagnetized, right? So basically, this is permanent magnet, and mostly 2 versions are available, especially in India. So barium hexaferrite and strontium hexaferrite. Barium hexaferrite is a little bit conventional, but now widely used strontium hexaferrite. Its major application, the permanent magnet. So now, uses of permanent magnet in new forms. EV design, the motor BLDC. First of BLDC. BLDC, what is BLDC? Brushless DC current motor. It is very efficient. It has a couple of advantages over conventional motor. You know very well, because there is no direct contact commutator in the brush, right? It is easy to control. Even अभी तो घर में जो पंखा है ना, उसमें तो BLDC fan you can easily control from remote, right? It electricity consumption again almost 50 to 60% of the conventional fan. So in BLDC there is a huge application of hard ferrite, mainly for low-end application strontium hexaferrite, but for EV BLDC even strontium hexaferrite is not so compatible. They are niobium, boron, iron, metallic compact. These are widely used. So hard ferrite is also importance of hard ferrites and new applications of hard ferrites also parallelly increasing to the greater extent as soft ferrites. Now, though here we are focusing on manganese zinc soft ferrite, also we need to touch about another categories and another version of soft magnetic material. These are not ferrites, but soft magnetic in nature. This is a kind of, the material is sandust, which is basically, you can say, a kind of amorphous or nanocrystalline type soft ferritic material. Sandust cube. Basically, sandust was first discovered in the year of 1930 to 1950, during Second World War, basically, you can say. So in the Sendai province or Sendai area of Japan, I'm not so sure whether it is a province or whatever maybe, but it is in Japan. The first it was discovered, right? So sandust structurally, it is completely different from conventional soft ferrite. Basically, it's a metallic kind of component where distributed air gap maintained is very, very important, right? And it has a couple of advantages over conventional manganese zinc ferrite because it has high flux density, even up to 1500 millitesla, where manganese zinc ferrite has maximum 500 to 600 even, yes, but it has even more than double. This is one of the more advantage. Number two, low power loss, high initial permeability, and it is comfortably used. It can be used and low frequency, where noise factor plays a crucial role. So these are the basically limitations of manganese zinc ferrite till date, but itself sandust has some limitation because unlike manganese zinc ferrite, it can't work up to 10 megahertz level. So maximum 400 kilohertz, it can work very well, but beyond 400 kilohertz, its function is deteriorated. So it has also self limitations, but there are so many components which can well and efficiently operate in the frequency bandwidth up to 400 kilohertz, like solar application. There it is used output choke, wind application, of course, electron EV, common mode choke, SMPS, and consumer electronics, yes, fridge, etc. But it's a limitations. Now come to the coming to the our mainstream discussion. This is the industrial aspects of soft ferrites. Let's have some industrial procedure, how it's conventionally processed. So key operational steps are first, powder processing. This is one of the most important thing. The masala kaise banna hai. Pressing, here we give the shape of the granule to the powder because we need some product in defined shape as designed by the client or engineers, scientists. Then there is an important stage in ceramic processing, we can say, not only ferrite. This is sintering, but here sintering is some special. We'll discuss subsequently. And of course, grinding, polishing. This is also a crucial step. So these 4 steps are very, very important for industrial processing of soft ferrites. Now, powder production process itself contains several sub-steps. First, mixing of the raw material. We have already discussed the raw materials like pure iron oxide, manganese oxide, zinc oxide is the key ingredient with absolute purity. Next, pelletization, pre-sintering in rotary kiln, then coming to coarse milling, fine milling through attrition, then organic addition. We selected, yeah, powder, raw material, everything. But in order to provide the save, we must have to administer organic material in defined quantities. And finally, spray drying. Spray drying is very important because it controls the granulometry of the pressable samples. Spray drying, you know very well. Amul spray. Amul spray, why it is spray? Because this is process to spray drying. So similarly, same process we also followed. Now pressing, there are different types of press. It is used on the basis of the weight of the size of the ferrite core. Smaller, where rotary press are used, with the weights limit up to 24 gram. Beyond that, up to 350 gram draw stripe. This is a typical hydraulic, of course. And for a larger one, up to 2 kg per piece. So we use a hydraulic type press where 400 ton press is used. Now, come to the sintering. For this sintering, 2 types of kilns are used. And the uniqueness of the sintering practices of ferrites are, here we have to use the atmospheric control kiln, unlike other conventional ceramics, because simultaneous control of atmosphere and temperature are essential to achieve the desired electromagnetic property of the soft ferrite. If there is some mismatch of controlling atmospheric condition, so this product will be completely wasted. So 2 types of kilns used: a tunnel kiln, which are continuous, where profile is fixed, product moving, and just opposite, static type. So this side. So here product is fixed, but sintering profile is dynamic. And there are some pros and cons in both. Tunnel kiln is basically used for high production, but not for absolute quality. If we want to achieve the quality, then we have to opt the batch kiln, but operational cost of batch kiln is obviously higher compared to tunnel kiln. We have both because sophisticated ferrites are not achieved, quality not achieved in tunnel kiln. It's the grinding, different types of grinders used, rotary kind of precision, 2-station and 4-station. The mechanical people, if they hear it, they can easily understand. Okay, now coming to the quality gate. So it plays a crucial role for any manufacturing industries. You know, the manganese zinc ferrite is a very advanced type of material. So quality control is very crucial, starting you can say to get. So from starting from raw material to final product. So raw material evaluation, ferrite granulate, fresh, sintering, grinding, packing, everywhere it is very important. These are kind of typical materials. The name manganese zinc ferrite power grade high permeability material for the stars. So this is a new material, and also there are nickel zinc materials. These are new type or develop. We already developed, specially used for space application. And this is the product portfolio. You see, just I mentioned couple of geometries, 12, yeah, 1, 2, 3, 12 geometries. But we have so other geometries, more than 300 geometries. It is next to impossible to put it in one single page. So these are the major and conventional geometries used in electronic circuits. Ferrites are another unique application during welding for making seamless pipe. How pipe is made? Iron pipe. Everywhere we use iron pipe. Iron pipe is made from a sheet, iron sheet. Once iron sheet is given to shape, This joint to make the seamless, we have to put a high intense magnetic field to aid at high frequency, of course, 400 to 500 kilohertz. So it will help at high density, high flux density, the material characteristics must have. So it will help the seamless joining for industrial practices. Normal welding process we can't follow for industrial practices, but we must have to process for high frequency welding, where ferrites impeder having high impedance are used. Yes, this is basically absorber tiles, nickel zinc type used for anechoic chamber. This is now is coming very important. If we see the gross area of application, ferrites mostly used in automotive application. And if we precisely see the what parts of automotive, now antenna application is going very, very important. So sensor, antenna, lighting is very common now. Solar, industrial parts, EV, EMI filters, lighting. These are the broad area of applications of sub-ferrites. Under automotive segments, now antenna is going very, very important. We're going robust because each manufacturer has unique parameters. And we are crazy about that. So ferrites in coils, transformer, and electronic circuits. Yeah, this is the typical peaks. And if you see once the circuit board, how it is PCB application and normal circuit board, how it is mounted. E-vehicle BLDC need lighting segment, DC-DC converter, AC-DC converter, and needless to explain, already described. Similar kind of thing. Because first ferrite, then component, then coming to circuit, and main product. So there are alag segments. We are producing ferrites and components in terms of transformer also. Now this transformer is now getting built in some circuits. Now this circuits in the final product, like car or anything. Yes, this is ferrites for automotive application. Of course, non-heavy. I mentioned here non-heavy, non-electric vehicle, because if the status of uses of ferrites in non-EV is like that, then imagine what would be in EV, because which is their complete part is electronically driven. In fact, 1 year back, I didn't have this kind of idea. Is car contains 24 sets of antenna, modern car. And this is a status, again, non-EV. And with defined and unique properties everywhere. Yes. So we just covered the broad aspects on area of application. Now let's have a couple of words of design aspect. This from technology and engineering point of view, this is important. How we will design a ferrite material, what should be the key properties for that application? This is the major point for, this should be the major point of technologists. Okay, first for, this is the generic and typical schematic, right? So for power application, the requirement of core, what are the requirements? It must have the low loss at high temperature, of course. High temperature means maximum highest temperature possible where the system or equipment is working, right? This loss, you know very well, if we consider the overall power loss of a ferrite of its systems is basically a combination of three parts: eddy current loss, hysteresis loss, and residual loss. With increasing frequency, the eddy current loss increases drastically. So low eddy current loss is desirable. Number three, high flux density. Flux density should be as high as possible in order to improve the system efficiency. I already mentioned for manganese ferrite, currently we have maximum 600 millitesla, but Sandust, they have beyond 1000 to 1500 millitesla. And yeah, so in that table, there are a couple of very common power material. And in the right hand side, there are some schematic of push-pull converter and flyback converter, right? This schematic diagram. Coming to another area, this is a filter application. You know very well the physics people. You understand much more better than me even. So for designing filter application, the key requirements, low loss factor. Don't confuse with this power loss. This loss factor is different, 10 delta. Or you can say the relative loss factor, 10 delta by mu y. Of course, the inverse of 10 delta is quality factor. So low loss factor means high quality factor. Of course, precise inductance value as must have the we can correlate with the initial permeability of the component. Low disaccommodation factor, and of course we need to choose the tolerance, close tolerance for the temperature coefficient. This is called basically alpha F, the change in permeability or inductance per unit temperature. This is very, very important for antenna application. Now we are getting the requirement from some premier car manufacturer. When this alpha should not be more than 1 into 10 to the minus 6. This is very, very stringent parameter, where normally 6, 7 alpha value. Basically, it helps for smooth communication and signal transfer. Now, ferrites for broadband application. Yes, of course, high permeability is required. Of highest Curie temperature always welcome. Saturation flux density should be also high. All the requirements should comply here, or requirements of filter application also equally comply for broadband of application. But here another new thing, jo low hysteresis material constant eta B, which in magnetic world it is called eta B. It should be as low as possible. Basically, eta B is related to the hysteresis nature. If you plot the hysteresis low base curve, you can calculate from amplitude permeability and eta V from there. And below there are a couple of material grids which cater this application for broadband application. Again, coming to the same point, soft ferrite is a very advanced material, and to develop and characterize this kind of powder, R&D plays a very crucial part. There must have XRF for material composition, particle size, distribution analysis, BET, same if there is high resolution digital microscope, if there is same, most welcome. And of course, atmosphere controlled kill, BH loop tracer, power loss setup. These are the key requirement to characterize quality control and develop the new ferrites material. Now, already the end slide will come. So here, I would like to show you how the evolution of ferrite material now gradually improve. So here the central material CF139 is the common power material having 400 power loss at 400 milliwatt or kilowatt per meter cube, right? So how with increasing the technological demand, how ferrites properties are getting, the requirement of improvement is required through a consistent R&D. And our conference, multifunctional advanced material, there is very close relationships with this evaluation picture. We have classified the 4 areas measure: low loss, high frequency, high BSET, white temperature. If you see in white temperature, this one, CF289A and CF289B, you will see that the operation range -40 to 140 degree. And this is the flat loss. ऐसा नहीं है जो माइनस में एक पावर लॉस आएगा, यहाँ पे एक पावर लॉस नहीं, बिल्कुल फ्लैट. And this is basically for aircraft and space research. This is very, very important. And this is these two materials. This is the such kind of advanced materials are going to be where one material grade fulfills 4 or 5 properties simultaneously. These are typical power material. It must have low power loss, but it has simultaneously have high saturation, high initial permeability, and of course, it is compatible to high frequency application like 5 megahertz. 1 megahertz is common, but 5 megahertz too. This is so important. So here, our concept of multifunctional advanced material technology, yes, especially if we go through nano route, it is very, very important for us. And the classification of manganese zinc ferrites and nickel zinc ferrites, and even manganese zinc ferrite, high permeability and low loss material, I think after 2 years, this concept will be gradually diminishing, because we need and we have to develop some kind of hybrid material which caters simultaneously both as high permeability material and low loss material. And this CF29A and CF29B, this kind of materials not only cater this requirement, but also wide spectrum -40 to 140 degrees centigrade. So yes, coming days are so important. This material plays so vital. We have to cater. Otherwise, our life will be stopped. Like artificial metaverse, artificial intelligence, to design their core metrics. These kind of ferrites are very, very crucial. And already our R&D is going on. And there is timeline. Hopefully, within stipulated timeline, we will be able to publish. Thank you.
Thank you, Dr. Plas. Wonderful talk. And magnesium ferrite is something like very close to my heart. My PhD topic, and I've been working on magnesium ferrites since last 25 years. Now, Cosmoferrite is a company. We have signed one MOU about 2 years back. So if anybody from physics, chemistry, biochemistry, mathematics, forensic science, student or teacher, anybody wants to collaborate with them, wants to do some internship, so they are open. And there's one good news, like in coming time, they're also going to open one outlet for research. You can say one industry in our university. So I think this is a wonderful opportunity. So I thank Dr. Plash and Sanjeev Kutoji, CMD of this Cosmoferrite. He was here yesterday, but somehow he has to go to Germany for some important meeting. So today he's not here. So I take this opportunity to thank Dr. Plash. Thank you very much for the interactive session which you had. Now the session is open for the students. If you have any question, like you want to collaborate, you want to know about the magnesium ferrite, because to the best of my knowledge, there are only 2 industries working on making products based upon magnesium ferrites. And these products, they're used everywhere. You look at the mobile, there will be one device, very small device, or you can say the charger, any electronic equipment, you think about LED, LCD, everywhere these ferrites, they're used. And the market is very huge. So one industry is Cosmoferrite industry, and another is based in Bengal, I suppose.
Yes. It's a part of TDK.
Yes. So in India, there are only 2 industries, and the scope is enormous. So if we are going to have like 10 such industries, even then I think we have still scope. And maximum, what we are doing, we are importing these ferrites from China, from Taiwan, from other countries. So I think it's a wonderful opportunity. So thank you very much, Dr. Plash.
Thank you, sir. Any questions?
Sir, I have a question.
Sure.
What is the technology insertion time from your company? What I mean to say is, suppose there is a power supply AC to DC converter.
Mhm.
Okay, so that uses a transformer. That is in production, say from last 5 years or 10 years, you are continuously making those transformer which are used in these supplies and they are continuously in production. Now you develop some material which is having a better quality or for which you can reduce the size or reduce the improve the performance.
Mhm.
Now you want to replace the existing with new one. So how much time normally your company or you take for new material or new systems to be incorporated in the existing, because there is a lot of resistance always.
Yeah. Sir, as per our roadmap and our present practices, it is quite sure that 3 to 4 new materials we are developing per year. Right. From last year, we developed till date 5 materials. From last year means last April 2022 to till date, we developed 5 new materials. And in our roadmap, there are another 5 materials we have to develop. And we are quite hopeful that, yeah, 4 materials average per year, you can say.
No, sir, that is okay.
Mhm.
But when you converting those material into a product, say now with new material, you are making again a transformer core,
Mhm.
which is having a small size because you have advanced material now. So how much time you take to qualify those to replace in the existing system? Because as existing system owner will always say कि नहीं मुझे तो जो दे रहे थे वो दे दो, मेरा तो already सामान बिक रहा है.
Yes, sir. It depends on the material properties and requirement of the product. There are so many factors, but I guess for one product, yeah, 1 year enough. Because we have to consider apart from material, design is the most important, product design and final field validation. So yeah, one year for one product, new product.
Okay.
Thank you, sir. Ma'am, I need.
Thank you.
Thank you for your insightful talk on ferrites and its usability and other typical soft magnetic materials along with their industrial processings. Now I request Dr. N. Vijayan and Dr. Atul Thakur to come up on the stage and present a memento to Dr. Palas Kumar. Professor H.M. David Wong is a full professor at Graduate Institute of Biomedical Engineering, National Chang Seng University, Taiwan. In his 5 years of research in biomaterials on skin, drug discovery, and biomass production, he has published around 100 papers and obtained 7 patents. His present study covers the search for a novel environmental resource in place of our world's depleting natural resources. I invite Professor H.M. David Wong to apprise us about nanocedia treatment in preventing the development of urological chronic pelvic pain syndrome.
So I use this one.
He will be joining us online.
Hello, Professor David.
Yes.
Hello, ni hao.
Can you see my monitor?
Yes, so I would like to add, Professor David is a very big professor. He is working in nanotechnology, biotechnology. He has plenty of students, more than 25. He has one animal house, I think on 21st floor of the building. And he's top 2% scientist by the Stanford University ranking. Very busy person. So just 3 days back, I sent him a message. We are organizing one conference. So I'd like to invite you to deliver one talk. And he was so generous, so sportive. He didn't say no. So thank you very
Originally, I
much,
say no.
Professor David.
I say no several times.
Can you hear me, Professor David?
Yes, I'm here. Can you hear me?
Yes, we can hear you. We can see you. So
Okay, very good. So, the most important issue is, can you see my PowerPoint?
yes, we can see your presentation.
Okay, wonderful.
Yes, thank you. So you can proceed.
Okay, thank you.
Thank you very much. Thank you.
Yes, so I will start from right now, and if there is something wrong, please just remind me and let me know. I try to fix it and everything. And I will use my PowerPoint as a full screen so you can see my presentation this afternoon. Once again, thanks for the invitation. And I know Professor Tu is holding this a video conference and the real conference in India. I definitely believe the work is very, very hard, and definitely the duty is also very, very heavy. So I will make it easier and for everyone and easy to understand my topic. Okay, here is my briefly CV, and I'm happy to see Professor Atu in Taichung, I think maybe last year. And my lecture focused on 4 topics. The first one is about gene engineering. We try to use genomic and the recombinant protein technology to synthesis human disease. And it follows the number 2 topic, drug discovery. So we focus about skin dermatology and plastic surgery and else. And human disease for the skin, not only melanoma or skin cancer, but also some kind skin whitening, anti-algae or virus, microorganism infections. And we move also to the number 3. The number 3 is about tissue engineering. We try to repair the skin wound. And right now, we also focus some kind of hard material, just like a bone or teeth. So we can synthesize hard materials and culture with stem cells for bone regeneration and the teeth repair. The number 4, the final part, is biomass production. I can use microalgae or a lot other fermentation technique and to produce a larger amount bioactive ingredient. And right now, I also serve 3 SCI journals as associate editor. First one is Food Science and Human Wellness. Second one is Frontiers in Bioengineering and Biotechnology. Number 3 is BMC. So if anyone is interested in this field, welcome to submit your papers and submission. And you can see the photos. The photos is of my group's members. We take photo together. So today, according to the time issue, so I will talk about 2 topics. The first one is cancer research. Number 2 is nanotechnology. For the first one, in this slide, I want to share some information about the scientists for the cancer research. About half century ago, we start chemotherapy to treat cancer. However, you can see the title. I say it, cancer is very smart. So they always try to solution to escape our treatment. So right now, we still cannot find a cure treatment for all the cancers. You can see through these figures, after about 20 years, then we start a new strategy about target therapy. And the target therapy, the aim is to find a specific gene or protein just located belong to cancer. So that's why we can do specifically focus on cancer, not with other side effects to normal tissue or normal cells. And 10 years ago, we start about the third stage. This is immune therapy. I definitely believe right now, all of you have already heard and a lot of information about immune therapy. So you can see, if you have time to see the details, you may see for the chemotherapy, there are lots of side effects and the damage to the patients. Okay, I will continue because I heard some noise. So, okay, I will continue. And for the target therapy, unfortunately, we can't find out a specific gene or protein just belongs to cancers only. The usual case is the protein or gene is also located in normal tissues, but the amount are kind of different. Usually the normal cells with low level and cancer cells with high level, that's all. So side effects are a very, very huge problem right now. And 10 years ago, we tried to reprogram our immune system and awaken them to attack cancer cells. However, the truth is cancer cells know how to manipulate other cells to protect themselves. For example, you can see, I use mouse, you can see like this. This is CAF. We call this cancer-associated fibroblast. And this is TAM. TAM is tumor-associated micro. Originally, in the very, very beginning, fibroblast, macrophage are good friends of ours. However, cancer cell knows how to make them become bad friends. Us. I will make it quickly. So here is the very brief anatomy of human skin. We have 3 layers: epidermis, dermis, and from the top to the bottom. And then you can see this is normal cell and normal skin, tissue, and melanoma. This is very, very bad skin cancer. You can see that there are lots of reasons to cause melanoma or cancer, like UV, like family history, like alcohol, like metal contamination or others. And here is the most important slide for you, and I will move to the treatment, finish the introduction. From the right-hand side, you can see this is the chemotherapy. From the left-hand side, this is the basic chemotherapy and the immune therapy. So from the right-hand side is the immune therapy. From the left-hand side is the chemotherapy. And in the chemotherapy, I originally catalog all the commercial drugs specifically for melanoma. And for the immune therapy, this is only phase 2. But in 2014, we have K medicine. In 2015, we have O medicine. And even right now, side effects are very, very severe. For example, we will lose hair. The damage is happening in the snail. And we will have some fugue and diarrhea, because this is our regeneration so fast. And the blood formation from your spine is also damaged. So the side effect is too severe, and the patient cannot survive with these toxic elements. Let me move to the nanotechnology. And you can see, here is my briefly idea. I make a very quickly slideshow for you. This is a cartoon map. However, this is pronounced in Mandarin. So I hope you can hear. Okay, I will make this in English for you all. So this is Troy battle. We create a vesicle, and this small particle is composed by melanoma cells. And inside, we put our drug. So once again, we use two basic theory. The first one is homing. All the cell well located, the surrounding he likes. Okay, the first one, homing. So every circulation system cell will try to find some place friendly to them. And the second term is about cheating. I make a small particle. The outside shield is composed by cancer cells. However, the inside is our drug. Right now, we use curcumin. This is a natural product ingredient. So we use curcumin as our target to treat melanoma cell. So once again, we create a narrow particle. This narrow particle is composed two parts. One part is about the outer shield, and the outer shield is composed by melanoma cells membrane. And the inside part, we insert curcumin as our treatment target compound. Okay, so we can make it quickly. So here is all the experiments, and we use UVB to remove all bad genomic materials, including DNA, RNA, or other disease proteins. So we remove it all. Then with syringe, so we can make this happen like a small, very small, narrow particle. So here is the evidence. I will make it quickly. So we can use chemical reagent. We can also use kit and use color to purify this non-wanted DNA and RNA, and we demonstrate in here. And since my background is engineering, so we can all experimental condition, including culture time, temperature, pH, surfactants, or other concentrations. Then we can get a suitable, very good concentration and the pH and temperature and others, and make it in a table. Okay, this is a procedure. Make a table to demonstrate, yes, according to our simple procedures, we can get high yield, high quality, high purified narrow particles. Then we move to physicochemical assays, and to see the data, use SEM, use TEM, and also culture with normal cell. 33 cells is normal cell. B16F10, this is bad cell, melanoma cell. So we can see our narrow particle just focus on bad cells only. Then we move to another system, and this is healing. You can see we can treat the narrow particle and inhibit the migration ability. And this is another interesting issue I would like to show you. And since our target compound is curcumin, so we can reprogram our immune system, then ask T cell to kill melanoma cell. So this experiment is kind of interesting. We culture the cell, two types cell, melanoma cell and the T cell. In the very beginning, nothing happened. Nothing happened. T cell survives. Melanoma cell also survives. However, once we treat our nanoparticle, this kind nanoparticle will awake T cell and ask T cell to attack, kill melanoma cells. Then we got some good result and consequence. So here is the final slide for this topic. We can make a narrow particle very easy. The component just for melanoma cell membrane and curcumin. We assay and use some chemical and physical device to test the basic particle information and then treat with melanoma. Yes, we can get some positive result. Also, we can treat with T cell. Then immune system also can help us to kill bad melanoma cells. That's all. Okay, I will move to the second one topic. This is about UCPPS. This is a side effect of chemotherapy. Right now in the world, we don't have a very effective treatment for this kind of patient. However, we still spend lots of money to treat these patients. And you can see, sorry, some are in Mandarin, some are in Chinese, some are in English. So you can see the English part. And there are several reasons to cause this kind of disease. First one is trauma. The second one is about infection. If this is trauma, maybe we can use surgery to help them. However, the effectiveness is not so good. If this is from infection, yes, we can use antibiotics to kill microorganisms. And the number 3 is use steroid and painkiller. So you may think this is not good. This treatment are not so healthy in one way. But as I mentioned, some digestive system or urinary system also will be affected by chemotherapy drug. So that's the question. If the disease syndrome is caused from chemotherapy drug, how to treat that? Surgery, not effective. Antibiotics, no good. Painkiller or steroid, also no good. So we try to figure out how to deal with this. We found a compound. In fact, this is very famous. The name is serine. And you can see in here, this is some basic information. Serine is very, very abundant in the world. So a lot of. And in the structure, in the chemical structure, it has 4+ and 3+ because of lactase defect. So you can see this slide, it will automatically oxidation and reduction, automatic because of lactase defect. So this kind of oxidation reduction happens all the time, always. This is about in a chemical field, but in a biochemical, physiological field, we will say oxidation and anti-oxidation. In a basic idea, anti-oxidation is anti-inflammation. Once we can do something about anti-inflammation, usually, normally, this is pain killing. So once again, we find a compound and make it like a oxide, like a bioceramic. Automatically, the compound nanoparticle with 3+ and 4+. Spontaneously oxidation and anti-oxidation all the time. After we know that, we test it in cell, animal, and human being. So we can see this is our treatment. We use a chemotherapy drug already used in clinical. And one of the side effects is digestion pain, urinary system and the digestive system pain. So we also use this kind of drug for our inducer. So this is the procedure of a cell and animal. This is the procedure. And we assay evaluate the basic information of neuroceramic theory. And this is from the cell. And we culture the cell and treat this kind of compound. This kind of compound is chemo drug. First is chemo drug, and the second is our synthesis drug. Then we can reduce the oxidation, reduce the chemokine and the chemokine, cytokine production, and then we move to animal. Yes, the animal is the same syndrome with human. Once we got a pain in hands, for example, just like my left hand got some hurts, I don't want to use my left side hand. Once we have a problem of our urinary system, then the feet, the back feet, even animal don't want to move or act. So we can see this kind of behavior and measure the scale. And then we sacrifice the rats and to see the blender information and other some kind biophysical data. We can also see this kind of reduction because of our target compound. Then we use NGS to see the all gene, including DNA and the RNA changes. So we found out a very specific gene. The name is 13B2. And this is the first time in the scientific field we discovered this gene, this protein is highly related to UCPPS. And so finally, we test the human genomic database. We can also confirm the same result and consequence. So this is the final slide. We found a compound. We test in cell-based, animal, and human. Then we found out a specific unique gene, 13B2. And this 13B2, once enhanced or reduced, the consequence is as our predict. Then we publish the paper. Okay, I finished all my stories today, this afternoon. So here is my group for some memories. So we take photos together. And I would also take this chance to introduce Taiwan beautiful view for all of you. As Dr. Sun Adian as mentioned, this is a wonderful place. And welcome to join Dr. Sun's group, and also welcome to David's group. And you can see my hometown is just very close to 101 building. I can see 101 building through my window, so very close.
Yes,
And
you're
my
very lucky.
location.
Yes, you're very lucky, Dr. David. And I think this is a time like you can announce you have plenty of positions in your group for masters, for PhD, and
Yes, welcome.
yes, I
And
know.
so you can see, and the things I
Wow,
love food.
it's a
Everybody,
lunchtime
every
here.
friends.
We all are
Yes, every
starving.
friends. My name is Davy Wang. In Mandarin, this is the same pronunciation. Davy Wang means stomach king. So that means I love food very much. So you can
Yes,
see
yes,
both,
Dr. David.
you can see dumpling, you can eat sticky tofu, you can eat fried chicken and the beef noodles, lots of very good food, lots of. And I would like to show you in here. I live in Taichung right now, my university. And this slideshow is very quickly. So welcome you to Taiwan. And the night market right now is a culture for us. So every place in Taiwan. And we call Taiwan is Treasure Island. So all the time, more than centuries. So this is worse. Okay, final slide. I finish.
Thank you, thank you, thank you. Now you tell me, are you listening? Are you able to hear me?
Yes,
Professor
I can
David?
hear you very clear.
Yes, thank you now. On the behalf of all my students, my teachers, my guests here, I would like to say a big thank you. Okay.
Thank you. Any
Yes.
questions or any suggestions?
Many questions. Yes, Dr. Deepa.
Many.
Hello.
Yes.
Hi, good afternoon. Thank you, Dr. Wong, for the wonderful speech. I have one simple question. I just wanted to ask you if you could please explain the nanoparticle that you made. You mentioned curcumin, and you infused curcumin into what? I couldn't understand that bit.
Okay, once again, I insert the curcumin to be a drug. And since this drug need to be located and find out, trace the cancer cell, so I create a capsule. And this capsule is composed by cancer cell membrane. So according to the term homing, this kind of particle automatically find cancer location. Once they contact to each other according to endocytosis, cell membrane fusion, and the cell door other mechanism, then this kind particle will enter into cancers. Then curcumin release. But the important thing is here, not only this, curcumin also will affect the surroundings. Right now we know cancer cell surroundings, including macrophage, T cell, epithelial cell, and the fibroblast. So we ask curcumin to kill the cancer. How? Because of immune system. So we test the T cell. Then T cell will transform through regulator type to the killer type. Then according to our experiments, we found out once T cell transform to the killer type, then kill melanoma cell. Is this clear for you?
Yes, thank you. Thank you so much. Also, one question. Did you say that
Okay.
it will encounter apoptosis?
Yes, apoptosis. Yes,
But
apoptosis.
why apoptosis? Why not necrosis?
Right now, we already identify 40 cell death pathway:
Yes.
autophagy, apoptosis, ferroptosis, apoptosis, necrosis, many types. Right now, we identify 40. May I say something from my heart? Right now, just me in my office. Because students want to live, so we can test everyone. So if you are interested, please send your students come here. We can test other and more cell death pathway. So we can publish a super high impact factor journal.
All right. Thank you. I got the hint. Thank you. Thank you so much. Good day.
Any other question? Dr. Nirvan? Do you have question? Okay. So two very rich and big professor from Taiwan, Professor Sun, Professor David. Yes, they are here. So big round of applause. And
I'm a small potato.
no, not small. I've seen you.
Small.
You are taller.
Small potato. And one now I have, as I mentioned to Professor Atul, and I have several project funding. The first one is TEEP. TEEP is very friendly to the all students, no matter bachelor student, master student, or PhD student. So I have the funding for from TEEP in Taiwan. So you can remember TEEP.
Yes, I do remember.
Oh, you remember.
Two of our students, they are already there in Taiwan right now.
Yes.
On this
This is the
project.
first one.
Yes.
And the second one, yes. And the second one, I have left one postdoctor position. Postdoctor position. I still have one left postdoc position. And so if anyone interested in my group about my study, so welcome. Send me email or let Atul know, and Atul can share this information to me.
Of course.
That's all.
This is useful information. And Professor Sun, Professor Sun. Yes, you can unmute and you can also announce you have some PhD and postdoc positions in your group. Please unmute.
安正，你要打开麦克风。您的麦克风是关的，到现在这边看起来都是关的。
佩珍，谢谢你。
Okay. Can you hear me?
Yeah.
Yeah. Here we also need the PhD student and the master students, especially a foreign student. So, as my authority, I can waive the student the tuition fee. So we welcome all Indian students come to our Yuanzhi University. We have the chemical engineering, material science, mechanical engineering, and some other. You can go to the website to check. And okay, just come here. I have the budget. I can waive my authority. I can waive your total tuition fee.
Yes,
welcome.
Wonderful. What else you need? Your tuition fee could be waived. Okay, and these are two professors who are working day and night. I've seen them working like 12 o'clock, 2 o'clock in the night, working in their labs. You call them, you send them any message like 2:30 in the night, they'll respond. But they are hardly on WhatsApp, but they are found online. There's a, yes. We have another professor here, Professor Anirvan Das. He has a question.
Oh, that was a wonderful talk, sir. Thank you. So a small question, the Cerium 3+, Cerium 4+ system that you had, so is it tested in vivo or in vitro? Kindly unmute yourself, please. You are muted, sir.
Professor David, unmute.
Oh, I found it. Yes, I'm
Ah,
sorry.
sure.
I'm sorry. Okay, once again. I test the 3 platform. The first one in vitro, cell-based, and the second one animal-based, use big rat. And the third one, we can also use human genome database. So 3 platform.
Okay, the Cerium 3 plus Cerium 4 plus system, right? The one, that drug you're talking about.
Yes.
Okay, thank you. Thank you.
So, so we can officially thank our guest, Dr. Shweta.
Thank you, sir, for your enlightening words. And thank you for extending opportunities to MIT students for higher studies in your departments. Thank you.
Thank you very
you.
much. Thank you, Professor Sun. Thank you,
Thank
Professor
you.
David. So big round of applause for them. Thank you. Okay, bye-bye. Bye-bye.
I extend my thanks to Dr. Vijayan for his precious time. Now I request Dr. Atul Thakur to present a souvenir to the chair of the session, Dr. N. Vijayan. Yeah, this brings to the end of technical session 2 of day 2. My sincere thanks to all the invited guests for taking out time and joining us here on this platform. Thank you all for all your participation. Now, before the next session, the attendees are welcome for the lunch. And there is an announcement for poster presenters. The participants for the poster presentation are required to display their poster during the lunch time. The poster number 39 onwards in the D block foyer. I request Dr. Vijay Kumar, Dr. Nitin, and Dr. Arjun Singh to evaluate the posters. I request you to proceed for the lunch break. The post-lunch session will commence sharply at 2 p.m. Thank you. इसे
हुआ
May I extend warm welcome to our charming faces, students there. Please keep quiet. Very good afternoon. Don't lose your patience, right?
इसको स्टॉप कर
लोग आगे आ जाओ। आरती Please come forward.
कर दूं उसे? हाँ, play कर दूं।
Please come forward.
Display
Students.
setting. Duplicate.
All of the events taking to the students only, and who are sitting in the back in the corner.
Slide change करना। Share screen. Check कर। एक करा सकते हो आप।
So again, very warm welcome to you all, ladies and gentlemen, and our dignitaries, distinguished dignitaries over here. Namaskar and very good afternoon to all. I'm Dr. Leena, Assistant Professor representing here the Department of Forensic Sciences, MIT School of Applied Sciences. It is my great privilege and pleasure to welcome you all in the technical session 3rd of today's day 2nd of National Conference on Multifunctional Advanced Materials, MAM2023. We feel immense pleasure and fortunate to have a very eminent personalities amongst us as resource person for this session. So may I request as a session chair, Dr. Ashish Saini sir, and my words will be little to just get into its speech to explain his expertise. But Dr. Ashish Saini sir has his expertise in the electronics, material, and fusion technology. Am I right, sir? So he is working as a scientist in TBRL, and he's heading the Department of Advanced Materials as well. So may I request Ashish Saini as a Dr. Ashish Saini sir as a session chair. So our next consecutive 3rd technical session to be started, and may I request before starting the technical session, I would like to take an honor to invite our eminent speaker of today's session, Professor A.S. Rao. Professor Rao is the professor in the Department of Applied Physics at DTU. He has a more than of 28 years of academic experience. He has more than 140 research articles, which is been published in international journals, and it is into his credit. He has completed many sponsored research projects worth of rupees more than 2 CR, and will some more projects are in the go. Under his guidance, he has guided 15 doctorate students as well, and is guiding many more. And many more doctoral students are pursuing his post-doctoral fellowship under his supervision. He has been enlisted as among the top 2% scientists by Stanford University. He has also reviewer of for many international journals of high repute, and acting as a head guest editor for international journals. He got the Best Teacher Award for these academic years, Commendable Researcher Award 4 consecutive times. His career of research interests include rare earth doped phosphors for white LEDs, RE doped nanophosphors for biophotonic applications, phosphorus doped with Re transition metal ions for solar cell spectral modification, green synthesis of carbon dots for bioimaging and drug delivery applications. He would be discussing with us rare earth doped phosphorus materials for photonic application. So thank you so much, sir. Please, I may request sir to come.
So can I change the slides here or? Okay, change your right.
I'm Dr. Lee.
Good afternoon to all the participants, speakers, and thank you, Dr. Leena, for introducing me to the audience. And I also want to say my sincere thanks to the authorities of Amity University for giving me an opportunity to present my talk in this national seminar, national conference on rare earth doped phosphor materials for various photonic applications. So we are basically working on luminescent materials. So luminescent material is a one which will take some input energy and gives you output energy in the form of electromagnetic radiation. So depending upon the type of energy what the material is taking, this luminescence can be categorized into different names: cathodoluminescence, chemiluminescence, electroluminescence, mechanoluminescence, like that. Luminescence is of different types. And our research lab is focusing mainly on photoluminescence process, where the input energy is a light or photons, and the output energy is also in the form of light. So the kind of materials what we are preparing in our laboratory, they are taking light as input and also giving light as output. And of course, in the electromagnetic spectrum, we have different ranges for the frequencies starting from UV, visible, NIR, etc. So from visible, you have left side some radiations and right side also some kind of radiations. So we'll try to manipulate these wavelength values using the luminescent materials by doping them with some active elements like rare earths and transition metals. So basically our work comes under photoluminescence, where the input energy is light photons and output energy is also light photons. And our group is mainly working on 5 to 6 areas where first, rare earth doped glasses we are preparing for photonic applications such as lasers, optical fibers, and LEDs. So in this, we'll prepare the glass materials, variety of glass materials, transparent glass materials, and doping them with suitable rare earth elements. Sometimes a single rare earth and sometimes 2 rare earths and 3 rare earths. And we are studying their absorption spectral futures and utilizing some standard models. Judafelt model will calculate radiative properties possessed by that material. And we'll also study the excitation emission spectral futures. And by correlating these radiative properties which we are obtaining from the absorption spectral futures with the emission spectral data, it is possible to understand the quantum efficiency and emission cross-sections of the as prepared materials. See, quantum efficiency means, see here in this entire work carried out by the scholars in my laboratory, material is taking some input energy and it's giving some output energy. So if you take the ratio of our output energy to input energy, that is called as quantum efficiency, and that quantum efficiency is the main factor for our investigation. So we are working for the materials which will give very high quantum efficiency. So we will measure such quantum efficiency and emission cross sections. Based on these values, it is possible to understand the utility of this glosses doped with rare earth elements for various photonic applications such as lasers and optical fibers. And we are also we are also measuring the color coordinates, and with the help of color coordinates and some other calculations, it is possible to understand the utility of these materials for white LEDs. Next, we are also converting some of these glass materials, good glass materials, which are giving very good quantum efficiency values into glass ceramics. See, a glass can be converted into a glass ceramic by giving a heat treatment. So to understand at what temperature we have to give heat treatment for hours together, we'll record DSC TGA information. And from that, we'll understand at what temperature we have to give heat treatment for that. So if you start giving heat treatment for a glass material, slowly we can see microcrystals and nanocrystals produced inside. And the development of such a micro nanocrystals without spoiling the transparent of that material much converts that glass into glass ceramic. And from literature, it is evident that glass ceramics are giving very good values when compared with glasses. So some of the scholars are working in this area. And another area where we are working is we are preparing the phosphor materials. In place of glasses, we are also preparing phosphor materials. And you know the fundamental difference between an amorphous material and a glass crystalline material. So the crystalline materials also we are preparing using different techniques, and we are recording their spectral features, excitation, emission, decay, and understanding the utility of these materials for white LEDs. Especially for white LEDs, where we are doing this kind of work. I'll come back to the significance of these white LEDs later. Next, we are also preparing nanophosphors for biophotonic applications. See, in medical fields, we used to have two important applications like bioimaging and targeting drug delivery. For these two medical applications, bioimaging and targeting drug delivery, right now people are using organic dyes and quantum dots. So when you are using organic dyes and quantum dots for these applications, you need to exert them with ultraviolet radiation. See, all of you know that ultraviolet radiation is a high frequency radiation. When such high frequency radiation enters into the body for these two applications purpose, it will kill the healthy tissues, and there are some issues related to this kind of applications by the usage of UV radiation. So in place of UV radiation, we are looking for the usage of NIR radiations, and through NIR radiation, with the help of this nanophosphors, by observing the upconversion phenomenon, we are understanding the utility of these materials for biophotonic applications such as bioimaging and targeting drug delivery. And we are also preparing quantum dots using an organic synthesis process and trying to understand their utility for photonic applications. And quite recently, we have started work related to spectral modification of the solar spectrum utilizing some phosphor materials and converting unconverted spectral regions into converted spectral regions. You know that silicon crystalline material is having an energy gap of 1.1 electron volts. And whenever such a silicon solar cell is exposed for sunlight, it is capable of converting the light energy coming from sun, whose value is equal to 1.1 electron volts. So below 1.1, above 1.1, the spectral energy coming from sun is getting wasted. So here we are planning, we are preparing some kind of phosphor layers, right, which can be kept, which can be utilized along with solar cell, where the energy below 1.1 electron volt can be converted into 1.1 electron volt energy region, and above the energy which is above 1.1. So using up conversion process and down conversion process, which I'm going to explain you later, it is possible to convert unconverted spectral regions into the convertible region, and thereby there is every possibility for enhancing the efficiency of the silicon solar cells. And right now, these cells are said to be having approximately 30% of quantum efficiency. So this will try to enhance with the help of the phosphor materials doped with suitable rare earth and transition metals, utilizing the concepts like up conversion and down conversion. So in all these kinds of works, most of the times we are going to use different synthesis and characterization techniques. For the preparation of glasses, we are using melt quench method, and for preparation of crystalline materials or phosphor materials, we are using solid state reaction, wet chemical route, hydrothermal, etc. To understand the structure and morphology of the materials, we are using XRD, FTIR, IDAX, Roman, SEM, FESM, TEM, and we are recording the absorption spectral features, especially when we are characterizing the glass materials doped with rare earth elements for lasers and optical fibers. We need to record the absorption spectral features to measure the radiative properties. So we are recording excitation, emission, and decay spectral profiles to characterize the materials. So basically our work comes under luminescence. And here for the today's talk, I'm concentrating on only three things. One is phosphor materials doped with rare earth elements for white LEDs, and nanophosphors for biophotonic applications, and spectral modification concepts related to solar cells. So here, a phosphor is a crystalline material in which it will take the energy from an excitation source and in turn emits some radiation. Sometimes to enhance the emission capacity of the phosphor material, will dope it with suitable impurities, and that kind of impurity which will help the rare earth element which is acting as an active element inside the material to transfer the energy is called sensitizer. So we can use one rare earth element which will act as an activator, and we can use two rare earth elements. One will act as an activator, another one will act as a sensitizer. And the duty of sensitizer is to sensitize the activator and to help the activator in enhancing the emission properties. So sometimes when we are selecting the host materials in such a way that the host can also act as a sensitizer and sensitize the activator and helps it to enhance the emission properties. So here, if you look at the broad applications of these materials, we have a set of down converting applications as well as up converting applications, especially down converting applications for phosphors. If you take LEDs, different colored lights producing materials can be prepared, or white LEDs can be prepared. And on the up conversion, as I told you, in bioimaging targeting drug delivery, right now people are using organic days and quantum dots. In their place, we can use phosphor materials doped with rare earth elements, and they are finding better when compared with the usage of organic days and quantum dots. So under up conversion, we are having biophotonic applications, and utilizing both the down and up conversions, we can modify the unconverted spectral regions into converted spectral regions. So this is an electromagnetic spectrum. We'll focus on visible. So left side to the visible, we have gamma rays, X-rays, and ultraviolet rays. And right side to the visible, we have infrared, microwaves. So let us focus for three areas: UV, visible, and infrared. For the sake of the students, see, from left to right, if you are moving, the frequency is gradually decreasing, and whereas the wavelength value is gradually increasing. And you know, energy of the photon is E is equal to h nu. When frequency decreases, energy associated with the light photons will decrease. So when you compare the energy values carried out by the visible light with UV, that will be less. Then infrared radiation, photons energy will be still less than visible. So here in this luminescence process processed by these phosphor materials, sometimes we need to excite them with ultraviolet radiation, and in turn we'll get emission in visible or in infrared region. And sometimes we'll excite them in infrared region, and in turn we'll get emission in visible and ultraviolet region. Say, I'm exciting the material with UV radiation. That means I'm exciting with a high energy radiation. And if we are getting emission in visible or in NIR, we can say the output energy, the outcoming photons energy is less than incoming photons energy. And here is, so in this process, what is happening is energy is getting down. That's why such emission is called as a down conversion. So on the other hand, when you are using infrared radiations for excitation, and if you are getting emission in visible, so low energy photons are entering into the material and they are coming out as high energy photons. So the energy is getting upgraded. That's why that emission process is called as upconversion. So you may get some doubt like how a low energy photons entering into the material comes out as high energy photons. Is it in accordance with the law of conservation of energy? Yes, it is in accordance with the law of conservation of energy. What happens in this process is two low energy photons will combine and gives you a single high energy photon. So that is in accordance with the law of conservation of energy only. So using this upconversion and downconversion processed by the materials doped with rare earth elements, we are characterized the materials for various applications, as I mentioned. So UV radiation is entering into the host lattice doped with rare earth elements, and that is converting into either visible or NIR, and this is called as down conversion. Whereas NIR radiation is entering into the material and coming out as UV or visible, this is called up conversion, as I explained. And if you take LEDs, see, starting from 1962 to the end of last century or in the beginning of this century, the lights, LEDs are used for only indicating lamps. So for at various places, we used LEDs up to the end of last century as indicating lamps only. And slowly, if you observe this graph, slowly starting from 1960, the output power is increasing by 20%, whereas cost for lumen what we are spending while designing these LEDs are decreasing by 10%. So that shows that the LEDs are not only useful for indicating lamps, they are also going to play a major role in lighting industries or lighting purpose. And if you go to this slide here, the input power required for the LEDs is just 1.2 to 2.6. And whereas luminescence efficacy, the lumens produced by LEDs per 1 watt is 50 to 70. And these values, when you look at and compare with the conventional light sources, they are not at all comparable. So they are having very good luminescence efficacy and electrical input. Very less input they will take for producing more luminous. So lifetime is also very, very high when compared with the conventional light sources. And you have the lumen per watt produced by the LEDs ranging from 20 to 120, and no other conventional light source is having this kind of stretch. So when you compare LEDs with the conventional light sources, they have potentially longer lifetime, very high energy efficiency, small in size, instantaneous on-off is possible, and produces color without using any filters, and can be integrated very easily with semiconducting diodes to prepare LEDs, and high color rendering index they are possessing aesthetic appeal. And we have standard methods for producing white LEDs. In the first one, we can use red, green, blue LEDs independently by driving different currents through them, and the combination will produce white light. We know that white light is a combination of RGB, and we can use blue LED as an excitation source and yellow phosphor, a phosphor capable of emitting yellow light. And this blue LED light coming from blue LED with yellow phosphor gives you a white light. And in the other one, last technique, we can use 3 different parts of phosphors and blend them with suitable proportions. And finally, by exciting with UV source, it is possible to get white light. These are the different methods and advantages and disadvantages for these 3 different techniques you can see here. So when we are working for phosphor materials for LED applications, the first and foremost thing what we'll look for is we need a host material having low phonon energies. See, when the system is having low phonon energy, if that system is excited with an excitation source, most of the energy entering in that material cannot be utilized by that material lattice, right, for vibrations. See, what are phonon energies? Phonon energies are nothing but lattice thermal vibrations. If the system is having very high phonon energies, when you excite such a material with the input energy, most of the input energy will be wasted by the phonon energies, and very less amount of energy will reach to the active elements like rare earths. And obviously the output energy will be less. So we are always looking for a system having very low, relatively low phonon energies. Chemically, that host material what you are selecting should be stable, thermally stable, non-toxic to human tissues, especially when you are using the nanophosphors for biophotonic applications. You need to inject such chemicals into the body, and they need to have non-toxic nature. Of course, we'll cover them with some kind of materials. Still, they need to be having low toxic efficiency and high absorption in NR region. As I told you, in the conventional technique, we are using UV radiation for biophotonic applications, whereas in the new technique, what we are discussing, we are using NIR radiation, so that post-lattice should have more NIR absorption capacity and high luminescence efficacy. And rare earth elements, see, rare earth elements belongs to 4F group, and they will possess very narrow absorption as well as emission lines, and their lifetimes are said to be relatively high. And there are well-developed theoretical models to describe the emissions given by rare earth elements doped into materials. So this is the concept of the work, white LEDs, and we are preparing different variety of materials, micro in size and nano in size, doping them with suitable rare earth elements. Sometimes with only one rare earth element, which will act as an activator. Sometimes with the two elements, one will act as an activator, another one will act as a sensitizer. As I told you, sensitizer will sensitize the activator. It will take the energy from the excitation source and transfers that energy to the activator, and activator in turn gives you emission, and from which you can calculate the efficiency. So these are all the different techniques involved in the solid state reaction method for the preparation of the phosphor. And phosphor materials we are preparing without any flux, with different flux, and in those flux, by identifying the suitable flux, we are changing that concentration of the flux. So flux is a material which will help the host lattice and the doped rare earth elements to enhance the emission capacity of that material. So these are all the characterization techniques employed. XRD will be used to find the phase analysis, and to measure the size, we are using FACM. And this is the excitation spectra. And in this, you can see two intense peaks produced by this material. And utilizing those two different excitation wavelengths, we have recorded the emission spectra without flux, with flux. And finally, we compared the efficiency of this material with the commercially available material, right? And since white light is a combination of three different colors, red, blue, green, we are developing phosphors for different colors. And this is a phosphor doped with europium, which is designated for giving red light. So the efficiency of this red emitting phosphor, we have compared with a commercial material, and almost it is matching with the 85% of the energy given by the commercial phosphor. See, in technology, we will always look for the financial viability. So when you are preparing the material, the technique, whatever you are following, that should be a low cost technique, and efficiency always will compare with commercially available materials. If that efficiency is almost equal or more than that or less than that, financial viability will decide the utility of that material in future technology. So this is how we are working on different materials, doping with rare earth elements and characterizing them with the excitation, emission, decay, and CI coordinates measurement. So some of the papers got published in these journals. And we are following different techniques also. As I told you, solid state reaction, combustion, wet chemical route. So different routes we are using to prepare the materials to understand their efficiency, photoluminescence efficiency. So these are all the results. And since the time is less, I am not going through the results obtained. So when it comes to the biophotonic applications, as I told you, conventionally, people are using organic dyes and quantum dots for bioimaging and targeting drug delivery applications. So these organic dyes and quantum dots, they need to be excited with UV radiation. And such a usage of UV radiation, high energy radiation, is not safe for the human tissues. So obviously, there are certain drawbacks like photo bleaching, autofluorescence, low SNR ratio, high cost of manufacturing for quantum dots. And this process depends down conversion, unnecessary side effects will be there when you are using UV radiation for excitation. So in place of that, when you are using NIR radiation through upconversion process, high SNR ratio you can expect, no autofluorescence, zero photo bleaching, and cytotoxicity, and low cost of production. See, the method of utilization costs nothing when compared with the preparation of organic days and quantum dots. So zero tissue damage because the excitation source is NIR when compared with UV. NIR is a low frequency radiation. It will not damage the tissues when it enters into the human body. So in this process also we have prepared so many materials and characterizing them using the same techniques. And these are all some of the results which we got and get published in journals. And the last topic is if in increasing the efficiency of the solar cells using up-down conversion techniques with the help of phosphor materials. As I told you, so these are all some of the statistics. We are using very less amount of solar energy when compared with the conventional kind of energy producing techniques. So fossil fuels are giving good amount of energy, and because of that, there are so many drawbacks as shown here. Yes, this slide will help you to understand how the unconverted solar spectral region can be converted into energy band gap equivalent to silicon solar cells. See, the students who are sitting here, they know that silicon is having a forbidden energy gap of 1.1 electron volts, right? So pertaining to that, there is an arrow mark here. So that part of the solar spectrum is only converted into electricity. So below to that and above to that, we have so much of energy coming from sun, and that is getting wasted. How that is getting wasted, you can see here. So when you are using the energy, can you see there? So when you use a energy above this 1.1 electron volts, as shown here, the electron cannot be excited from valence band to conduction band. So it falls in between the forbidden gap, as shown here, right? So this is how this energy above this 1.1 electron volt in the solar spectrum is getting wasted. On the other hand, when you take UV radiation or the radiation below UV, which is available in the solar spectrum, it is pumping the electron from valence band to far away from conduction band, and energy is getting wasted through thermalization loss. So in one process, the electron is unable to reach the conduction band, and in another one, it is reaching far away above the conduction band and getting wasted. And only the energy pertaining to 1.1 electron volts is only getting converted. So here, how to think of this unconverted solar spectral regions into converter region is an important task. There is every possibility to enhance the efficiency of the solar cell, and right now solar cells are giving 30% efficiency only. So here, this picture will help you to understand how up and down conversion processes are helpful to convert unconverted spectral regions into converted spectral regions. Say, for example, if you consider a high energy photon falling on solar cell, which is supported with a phosphor material doped with rare earth elements. So you can see a high energy photon converting into two low energy photons, and their energy falls in 1.1 electron volt window. And this is called down conversion or down shifting. I will explain you that the difference between down conversion and down shifting. So in this process, we are converting a high energy photon into two low energy photons such that their energy falls in the silicon window. And the other hand, so one high energy photon is converting into one low energy photon, and this is called down shifting actually. So in the previous case, where a high energy photon is converted into two low energy photon, that is called as a quantum cutting or down conversion. So in down conversion, you will get two photons And whereas in downshifting, you will get only one photon. One high energy photon converts into one low energy photon. Whereas in down conversion, one high energy photon converts into two low energy photons. So on the other hand, in the upconversion process, we'll use two low energy photons. As shown here, they will combine into a single photon and comes out such that its energy falls in the silicon band gap. So this is how, using upconversion and down conversion mechanisms, by growing phosphor materials and doping them with suitable impurities, it is possible to enhance the efficiency of the solar cell. And this picture also helps you to understand the upconversion and downconversion phenomenon useful for converting unconverted spectral lesions into converted spectral lesions. So in this direction also, we have prepared so many materials using different techniques and studied their efficiency. And we want to prepare a prototype devices utilizing all these materials and measure the actual efficiency. So that is under process. So this is all about the kind of works which we are currently doing in our laboratory. And I want to thankful to, I want to express my sincere thanks to all my collaborators in India and abroad. And special thanks to my guide from Sri Venkateswara University, Tirupati, Andhra Pradesh, Professor J.L. Rao. And I'm having a collaboration with Professor G. Vajaprakash, IIT Delhi. I'm utilizing some of his experimental facilities to carry out. And these are all the details of my scholars. So I once again wants to say my sincere thanks to the authorities of Amity University for giving me this opportunity to present my work. Thank you, one and all.
Thank you very much, sir, for your insightful speech over the doping, over the activators, and much more. We are looking forward for some more applications to extend in the era of biomedical applications for the healthcare professionals as a diagnostic appliances as well. And adding few more colors to the rainbow of the visible region. So thank you very much, sir. Now the forum is open for the question answers. If any curiosity from the students, my dear students and dignitaries, please. Okay, we may get mic for him.
Mic is here. See, so when you are doping the organic days and quantum dots and excite them with UV radiation, human tissues will have the capacity of absorbing UV radiation much, and they will give, see, healthy tissues will take that energy and in turn gives you the output energy, right? So in place of getting the emission from organic dyes and quantum dots, you will also get emission from tissues, right? And this kind of signals which are coming out will produce some noise, and that unwanted kind of signals coming out from the material, and the degradation, activity degradation of these quantum dots is called as photo bleaching and autofluorescence. Autofluorescence is emission of the light other than the organic rays and quantum dots, and photo bleaching is the effect which is degrading with respect to time.
So thank you, sir. And any more question? Thank you, Sagar, for the patient hearing. It means you've been hearing here today from the beginning of the session. So thank you, sir. Please. Now I would like to take the privilege to invite our next speaker, Professor N. Vijayan. Sir is the principal scientist and professor at Academy of Scientific and Innovative Research. His research areas include growth of technology, important single crystals by melt and solution growth techniques, preparation of Indian reference materials, Bharatiya Nirdeshak Dravyas for the calibration of sophisticated instruments, preparation of nano and allied materials. He has more than 230 of publications in SCI journals. He has been selected for the Young Achiever Award in 2022 by Elevenil Indian Science and Technology Association, Chennai. He is recipient of Raman Research Fellowship in the year 2021, sponsored by CSIR New Delhi, and his outstanding performance, he got the Outstanding Performance Award as well for the dissemination of meteorological traceability through Bharatiya Nirdeshak Dravyas and many more. He would be discussing with us accurate and precise measurements in advanced scientific research. So, sir, please.
30 minutes. Yeah, sure. So good afternoon to everyone. So before going to my detailed presentation, I would like to thank the conference organizers and the authorities of Amity University, and particularly Professor Atul Thakur and Professor Allam Rao and Dr. Lucky for giving the excellent opportunity. So today, from the past yesterday and then today, you have listened many lectures on variety of nanomaterials, nanoferrites, and then different advanced technological for different applications. But today, I am going to discuss about the importance of accurate and then precise measurements in academic research. This is somewhat relatively new for the young students. So before going to that, just I want to give you a gist of information about the importance of calibration and then precise measurements. See, for example, everybody, we are having the blood pressure, right? If you go and then measure your blood pressure in 2-3 places in Manesar, otherwise wherever you are living, nearby clinics, you are getting 2-3 types of blood pressure results. Similarly, whenever you are going and then measuring your sugar level in 2-3 places, you are getting 2-3 types of sugar report. Which is right? The person, he is not having the blood sugar or the blood pressure because of the wrong report or the wrong calibration or the instrument result, he is forced to take the medicines. You can imagine, if the person is not having blood pressure, if he is taking the blood pressure tablet, it will indirectly affect some other organ. If the person is not having the blood sugar, if he is taking the medicines, that is very dangerous. But it is daily happening in India. The simplest example is, everybody knows about the Sir C.V. Raman. His great contribution. He discovered the Raman effect in 1928. We are celebrating the National Science Day every year, 28th February. He got the Nobel Prize in 1930. Maybe another 7 years, we are going to celebrate the 100th year of Sir C.V. Raman's achievement or discovery. But you know that Sir C.V. Raman belongs to an Indian. He discovered the Raman effect in India. He designed the equipment in India with the cost of less than 500 rupees. But you know the scenario now. We are purchasing Raman spectrometer from Germany. We are purchasing Raman spectrometer from Japan. You know those countries' total population, it is less than 10 crores. But India's total population is approximately 160 crores. In that, more than 60 to 65 crores, less than 40 years of age. Majority of the Indian roads are filled with foreign cars. If you go and then see our sophisticated instruments or the gadgets we are using in our household applications, all are made in some other country or the technology from other country. If you see the ratio export and then import. Import is always making majority. We are simply the importers. So that's what Government of India, initially they encouraged for the Make in India program. Now slowly they are encouraging for the Made in India. So that's what now I am going to focus. Importance of calibration for the sophisticated instruments. We got the independence in 1947. 75 years over. But still, we are purchasing water from the foreign companies. We are not able to treat the polluted water. We are not able to concentrate for the societal research. You can imagine how many years the fossil fuels it will come. It will come for another 10 years, maybe another 20 years. But we are not having the proper roadmap. So these things we have to address. Without addressing this important societal based research, if I am doing the advanced research, there is no meaning. In addition to that, if I am doing advanced research, my instruments are not giving the proper results, then how I can come to a proper conclusion? Yes, what are all my synthesized materials? It will be applicable for a particular application, because in case if your instrument is properly calibrated, that is fine. In case if your instruments are not properly calibrated, how we can able to assign for the particular applications? These things I am going to discuss. So I am from the National Physical Laboratory. So it is the National Measurement Institute of India. I hope many of the young students, you may be knowing that Indian Standard Time, IST. IST is maintained by National Physical Laboratory through CCM atomic clock. Not only that, Indian Parliament has given the status to National Physical Laboratory that it is the National Measurement Institute of India. And in addition to that, we are maintaining all the 7 basic SI units. I hope everybody knows about the SI units. Length, meter, or the mass, kilogram, like that 7 basic SI units are there. Whenever we studied during our graduation or maybe during our school times, we never given that much attention about the 7 basic SI units. But if you recall, without the 7 basic SI units, it is very difficult to pass a single second in your life. All your day-to-day activities are related with the 7 basic SI units. So those 7 basic SI units, primary standards are maintained by National Physical Laboratory. And National Physical Laboratory, you know, it is located in New Delhi. You are always welcome. And we are encouraging for the student communities, even the college students, school students, and even the general public. Anybody, they can come. Every year we used to open for the open day celebrations, almost the 4th week of September every year. And last week we conducted the 1 week, 1 lab program. And time to time, in case if you want to visit National Physical Laboratory, you are always welcome. And in addition to that, we are encouraging for the student dissertation and we are encouraging for the summer internship also. If anybody is interested, in case if your areas where you are having more interest, in case if it is falling, then you can always welcome. And then we are having different types of research work, mainly for the societal development. So this is the slide. National Physical Laboratory, it was established before our independence. We got the independence 15th August 1947. National Physical Laboratory was established 4th January 1947. The first founding director of National Physical Laboratory is Dr. K.S. Krishnan. He was the student of Sir C.V. Raman, and he was, his contribution for the development of Raman effect is enormous. And in addition to that, you can see this is the handwritten notes of Sir C.V. Raman. And those days, he made wonders. And in addition to that, he designed his own equipment. The cost of the equipment is less than 500 rupees. You can imagine. So whenever, if you want to do the research work, it is not necessary to have crores of rupees. If you are having innovative thinking, if you the particle size. Some places they are telling 5 nanometer. Some places they are telling 100 nanometer. Which is right? Because our instruments are not properly calibrated. And almost all the industries, all the academic research institutions, everywhere we are using the sophisticated instruments, advanced equipments for the advanced research and technology. Many of the instruments are not properly calibrated. Because of that, our scientific image of our nation is getting destroyed. 100 years, we are not in a position to get the Nobel Prize. Not only that, we are not having the proper attention for making the technology transfer also. You know, all over India, approximately 10 lakhs of MTech students, 10 lakhs of science stream students, more than 10 lakhs of undergraduate engineering students, approximately 30 to 40 lakhs thesis every year we are getting from the various academic institutions across the country. You can imagine if one thesis is concentrating for solving the societal research or societal based problems, you can imagine we are going to get almost 50 lakhs of solutions. In that 50 lakhs of solutions, you can imagine maybe 5 lakhs we are converting into a technology transfer. They are making a startup industries. You can imagine how many people we can able to employ. Employment generation. And indirectly, it will boost our economy of our country. So those things, it is really missing. So we have to make a bridge. That's what research and development we are doing excellent. That's what earlier I have mentioned that developed nations, they are selling their knowledge into wealth. But developing nations like India, we are making knowledge only in the library level. We are displaying our journals in the library. We are displaying our thesis in the library. We are not concentrating the outcome of the research into technological devices. That bridge is missing. So we have to make a more effort to bring up some commercialization of the products from the research and development outcomes. So these are all the things. Because of the time limitation, I am skipping some of the slides. And directly, I will start with metrology. Earlier, I have clearly mentioned that if you go and then measure your blood pressure in 2-3 places, you are getting 2-3 types of BP. If the person is not having the BP, he is forced to take the medicines. So whenever we are hearing this, we are getting shocked. Similarly, in your advanced research, what you are getting the powder XRD data that is reliable. In your advanced research, you are doing your FTIR that is correct. In your advanced research, you are using the TEM as well as the SEM. That results are correct. How you are ensuring your data? Then how authentically you are publishing the data to the international community? That's what we are not getting any citations. No citations from our Indian researchers. I mean, nobody is citing because very less citations. That's what metrology comes into the picture. Metrology is the science of measurement. Whenever you are having the proper measurement, not only in the science, whenever you are getting the outcome of your results, then you can authentically say that my materials will be useful for the particular applications. It will suit exactly. Not only for doing the day-to-day research work, it will indirectly boost our exports. See, for example, I am the company owner. I got the order from some other foreign country for making 10 centimeter length screw. You can imagine for the automobile industry, 10 centimeter length screw. I got the order of few crores. Finally, I made the screw, maybe 100 crores worth of screws. Finally, I have sent my consignment to the particular country abroad, but they will not accept as it is. They used to measure again. Unfortunately, instead of 10 centimeter, 100 mm, my screw is 9.9 centimeter. They have not accepted because what purpose they have given the order it will not suit. Then finally they have rejected. You can imagine, because of the wrong measurement. So our measurement, metrology plays not only for making our science and technology perfect. Metrology makes perfect for selling any material to any nation. Not only that, whenever we are purchasing any material from the other nation, import. That's what earlier I mentioned, that nowadays we are simply importers. What they are predicting in the future, there will not be any war. It will be based on the bio war. What are all the materials they are selling to the other nations? Indirectly, it will be a very dangerous material. But how to identify that material is having dangerous content? We need some check, quality. Again, metrology plays an important role. That's what, whenever you are selling a product, whenever you are purchasing a product, in both ways, metrology plays an important role. I am making 1 milligram of a product in India. It should be same, whether it is in the Germany or whether it is in the USA. That is the simplest concept for the metrology. Whenever my measurement is proper, you can imagine in the trade sector, supplier, as a customer, both will be getting satisfied. In the health sector, both will be getting satisfied. So it is having lot of enormous advantages. And finally, our National Physical Laboratory. So that's what I always encouraging our young dynamic students. It is in NCR region. You are in NCR region. You are always welcome, and then see what NPL is doing for the nation. Particularly our division, that is Bharatiya Nirdeshak Dravya, Indian reference materials. We are making reference material for the sophisticated instruments. Whenever our instruments are proper, then our research is proper. Whenever research is proper, then outcome of the research is for the particular assigned applications. So that is the advantage. Our National Physical Laboratory, we are tirelessly working for the development of various Indian reference materials. You can see, we got the independence 1947, 75 years over. You know, Japan, 1945, 2 major cities destroyed, but even they are economically very strong. And we are having 160 crores of population. And till date, we are saying India is a developing country. And particularly for the reference material sector, we are importing more than 10,000 crores from the other nations. But now, government has encouraged, and then we started making our own products. It is not necessary to depend on the other nations. Simplest example I am going to take, maybe another 5 minutes. You can see, whenever you are just opening the daily newspaper in the science and technology sector, you are always reading new material innovation. That's what I have given example of automobile. When the first automobile invented, 1 liter of petrol, it has given only 2 kilometers, because there is no lightweight material those days. See, now science and technology has improved a lot. New material innovations. But how to identify that material belongs to a new material? We need some research equipment for identification of that material. You can see, whenever I am innovating new material, in case if that material is not properly identified, what are all the resources I have invested for identifying that material? It will go waste. Not only that, if I am not able to reach the proper conclusion, then there is no devices from my research outcome. So I am forcefully to give a wrong interpretation to the international community. And finally, I am not doing wrong. And finally, my scientific image of my nation is also getting destroyed. Simplest example, I am taking X-ray diffraction. I hope many of the researchers, they know about the X-ray diffraction. It is having lot of informations, structural informations. Even nowadays, the Debye-Schiller formula they are using through this X-ray diffraction. Phase, crystallite size already I mentioned. And many of the geological, even the mines, sectors, they are mainly depending on the X-ray diffraction. You can see X-ray diffraction, there are different way we can able to perform. One is Bragg-Brentano geometry, that is for the, you are using for the 2 theta, right? X-axis 2 theta, Y-axis is the intensity. So theta 2 theta operation, that is called the Bragg-Brentano geometry. Mainly for the thin films, they are using the grazing incidence X-ray diffraction. So in the powder X-ray diffraction, you are using the powder materials, bulk materials, even thin films. You can imagine if your instrument is not properly calibrated, what are all the consequences will come. You can see now X-axis, that is called the 2 theta, Y-axis intensity, and inside if you see, there are many different intensity peaks. It is having full width of maximum. You can imagine if the instrument is not properly calibrated. I have given 3 examples. One is effect of angle variation. Your 2 theta getting shifted. Originally, you have to get the peak approximately 31 degree. Because of the wrong instrument is not properly calibrated for many years. 31 degree peak is shifted into 32 or 33. If one peak is shifted, then other consecutive peaks automatically will be getting shifted. You can imagine how you will come to a conclusion, how you will assign that material is properly synthesized. Not only that, 2 theta, you can see intensity. You can imagine the major intense peak approximately 2000 intensity counts per second. If the instrument is not properly calibrated, in case of giving 2000 counts per second, it has given only 1000 counts per second. You can imagine the second peak. What will happen about the small peaks? The peaks of 100 CPS, it will disappear. Finally, what you will do, in case if you are adding some dopants, you will come to a conclusion that my dopants has not gone inside because of your intensity reduction. That is also one type of error in the X-ray diffraction. And it will give you a wrong calculation of your lattice parameters. And the third one, effect of FWHM, that is full width of maximum. Nowadays, many of the students, they are using the Scherer formula for calculating the crystallite size, 0.9 lambda divided by beta cos theta. Beta is the full width of maximum. You can imagine if the instrument is not properly calibrated, full width of maximum of approximately 13 degree, it has to give. Because of the wrong instrument, it is giving maybe higher or maybe lower. Then automatically your crystallite size calculation also will get wrong. So these are all the simplest example for your understanding. And NIRF data showing that NIRF, NIRF, registered university and then academic institutions, few lakhs of institutions all over India. All institutions, we are using the various sophisticated instruments, including X-ray diffraction, FTIR, SEM, PL, UV, many. But you can imagine how many instruments. I am not saying that all instruments are giving wrong data. Many of the institutions, they are not able to procure the reference material, that is called the calibration purpose, because of the huge cost. National Physical Laboratory has taken the challenge. We started making the reference material in all sophisticated instruments. And we started selling almost 1/5 of the cost of the other countries what they are selling. One way we can say that it is the import substitution. And in the future, it is not necessary to depend the other countries. And proudly we can say that this is our own Indian product. Reference materials are not new. It is very old. Many of the countries, developed countries, that's what I told, knowledge into wealth, they made already. But our knowledge is still in the library level. We are not making knowledge into wealth. We have to make it. That's what technology transfer is missing from our side. And National Physical Laboratory, we started making in the name of BND, Bharatiya Nirdeshak Dravya, that is called the Indian reference material. And from our group, particularly my group, we are working for the development of X-ray diffraction standards. And X-ray, I told clearly, 2 theta, you need a reference standard. Intensity, you need a reference standard. And full width of maximum, you need the reference standard. And we started releasing, already we have released the 2 reference standard. And you can imagine, if we are giving this technology to our own Indian industry, that is called the SE or the startup industries, you can imagine how many people we can able to give employment. How many institutions are there? Every year we can able to sell lakhs of reference standard. For making lakhs of reference standard in different sectors, we need a lakhs of manpower. Indirectly, it will boost our employment generation. Whenever we are getting our own product, our own sectors, it will increase our GDP. That's what I have clearly mentioned in this. And BND, that is the brand name of National Physical Laboratory. And till date, India is, that's what I told importers. We are simply importers and we are purchasing thousands of crores reference material in various sectors. And slowly we are making import substitution. It will not be immediately possible. Now only we have taken the initiation, and maybe another 1 or 2 decades, definitely we are going to achieve reference material in all the sectors. So we are having, as a NMI, National Measurement Institute of India, we are having very good collaborations with our Asian nations, because each and every country, there is only one NMI. India's NMI is the National Physical Laboratory. Similarly, Korea, that is called the CRIS. USA, that is called the NIST. So all the National Measurement Institutes, we are having the collaborations. And whenever we are releasing the material, we used to confirm from the other National Measurement Institutes, that is called the round robin test. There is some protocol is there as per the ISO. So we are following the protocols. And we used to make proper reference standard in various materials. And the first product we have released in 2020. And similarly, the next product, 2021, we have released, and the next product we have released in this year, January 2023. The 2 reference standard in the powder X-ray diffraction. Not only from our group, some of my other colleagues, they started making reference material for the FTIR, SEM, UV visible standard. You can go to our NPL website. You can see separate division that is called the Bharatiya Nirdeshak Dravya. Till date, NPL has released by its own or with collaborations with industries. We made 147 Indian reference materials. And collaboration industries, we used to say that is called the reference material producers. And you know, Bharat Stage 6, BS6 for the all vehicles, automobile vehicles. For that, our Indian reference materials plays an important role. We are having MOU with BPCL as well as the HPCL. And we have released many of the reference standard. Not only that, we are having collaborations with Indian industries, government as well as the private partnership. We are making reference material. And 2021, our Honorable Prime Minister of India, Narendra Modi ji, has inaugurated the separate wing for the Bharatiya Nirdeshak Dravya, that is called the Indian reference material. You are always welcome, and then you can see the facilities, how we are working, and particularly how we are taking the challenging problems, particularly for the industries or academic institutions. And not only that, in the future, we are planning to concentrate by our own or along with other industries. Food also we need a reference standard. Fuels, already we started making. Mines, we need the reference standard. You can imagine, I am the mine owner. In my mine, I am having, very costly chemicals, maybe gold or platinum. Unknowingly, I have tested my sample. Instead of showing the platinum peak, it has shown only iron peak. You can imagine, I sold my mine with very less cost. And whose fault? Because of the wrong instrument, it has to show the proper platinum peak. It has shown only the iron peak. You can imagine, these are all we are the losers if we are not properly able to make the proper instrument data. And CSIR, we are having almost 37 laboratories all over India. Each and every laboratory, we are working for the societal development, and each and every laboratory, they are having their own, expertise. And NPL is the nodal laboratory. We are collaborating with all the national laboratories, not only for making the product. We are disseminating the informations to the general public. We are disseminating the informations to the student communities by writing articles in all national languages. And without my students, they are really hardworking. And proudly we can say that we have released our own 2 Indian products. That is called the Indian reference material in X-ray diffraction. And still we are working for the development of various reference standards. Maybe in the years to come, maybe within few years, we are planning to release particularly my expertise. And maybe some of my colleagues, they are also working. And soon we are going to release few more products of reference standards. So anyway, without our director and then other member support, not only that, Ministry of Commerce, I am the principal investigator of the project of 32 crores. Ministry of Commerce and Industry, they have given 16 crores, and then our nodal ministry, CSIR, has supported 16 crores. 32 crores, we are making separate building for the Indian reference material. Not only that, we are establishing the basic infrastructure facilities for developing the Indian reference materials. So thank you very much.
Thank you very much, sir, for the insightful session and adding some values in the calibrations of the devices. So this forum is open for the question answer sessions. We may please request to anyone, the curious minds over there.
Thank you, sir, for your nice presentation. The presentation was really very informative to all of us. Sir, for XRF calibration, XRF, X-ray fluorescence, right? Thank you. So we need different types of reference material like iron oxide, zinc oxide, manganese oxide. And I strongly believe that once we purchase from import, opt for import, it is very huge costly. So is it possible to supply to set up an indigenous source, so that this is very urgently required for our electronic industries, because these materials we desperately need?
Yeah, that is a very good question. In XRF, normally, whenever you are seeing our periodic table, some of the instruments, it is having capability to measure from, boron to uranium. And depending upon the materials, we have to develop XRF standard each and every separate element. And now we are in the process. And for making with the proper protocol, by following the protocol, at least it will take maybe another 2 years. We started that. Maybe in 2025, we are planning to release for the XRF standard. Definitely, we are in the process for making the development of X-ray diffraction, X-ray fluorescence. But presently, we are having expertise of X-ray diffraction, and already we have released, and then maybe another 1 or 2 material we are planning to release maybe December of this year. Definitely, there is, definitely we will take into our consideration.
Please do that.
Yeah, sure.
Okay.
Definitely.
Thank you.
Yeah.
So I think we may proceed for the refreshing tea break. Before proceeding to the refreshing tea break session, we may request our Honorable Session Chair, Dr. Ashish Sani, to call upon the stage for presenting the token of appreciation. And I may correct myself, he is scientist at DRDO as well, TBR DRDO, and he is Vice President ISRS also. So it's my correction, sir. Sorry for that. So I may request Dr. N. Vijayan sir, our eminent speaker, and Dr. Rao sir, to please come on the stage, please. हाँ जी. हाँ. May I request Professor A. Rao sir. So we may present our souvenir to our Honorable Session Chair, Dr. Ashish Sani sir. And may I request Dr. Atul Thakur sir to present the token of appreciation to our Session Chair. तुम भी आ जाओ आओ बाहर स्टूडेंट बैठे हैं चलो आगे जाओ कहाँ है दिख नहीं रहा रक्षक में मेरे स्टूडेंट्स कंटिन्यू करो खत्म Now, proceeding towards the next consecutive technical sessions 4, I would like to invite our next eminent speaker of the session, Dr. Yasina Silmani. Dr. Yasina Silmani is an associate professor and senior researcher at Institute for Research and Medical Consultations at Imam Abdul Rahman bin Faisal University, Saudi Arabia. He has completed his PhD degree in material physics and applications from the Faculty of Sciences of University of Carthage, Tunisia. His current research activities cover the fields of superconductivity, energy storage systems, magnetism, dielectric and multiferric magnetoelectric materials, photocatalysis, and environmental remediation applications of nanomaterials, advanced ceramics, and so on. Today, he is going to discuss methods for enhancing the performance of high temperature superconductors. Sir, please share your screen.
Yes, Professor Yassin. Can you hear me? Unmute, please.
Hello.
Hello, how are you?
Thank you. Thank you. Sorry.
Yes, thanks for joining and accepting our invitation. So Professor Yassin is a renowned scientist, and he's also among top 2% scientists by the Stanford University. He's our collaborator. So we are doing a lot of joint research projects. And recently we are working on nanomaterials for multiple applications. And so I welcome you, Professor Yassin, and thank you for accepting our invitation in a short notice.
No problem. Most welcome. Thank you all. Nice greeting to all attendees, ladies and gentlemen.
Yes,
Thank
so-
you for attendance at this presentation and also for being with you. It's very nice to see all of you for the first time online. Thank you also to Dr. Atul and also to Dr. Preeti for their invitation and for this nice introduction.
Yes, so we are connected through online, through Facebook, through Zoom, and we
Yeah.
have plenty of students sitting live here, offline, and they want to get inspired by your research. We have eminent speaker from NPL, from National Physical Lab here in India, from Delhi Technological University. Next speaker is again one of our friend, Dr. Nikhil Valla from University of Ulster. So all of us are listening to you and welcome you.
Thank you. Thank you very much. Thank
Okay,
you
you
again.
can start, please. Thank you.
Okay. Okay, thank you. I feel that some researcher and some students are not familiar with the field of superconductivity and the importance of superconductor materials in our life. So I decided to make today's presentation on some of our research on some of our recent works within the field of superconductivity, and particularly on high temperature superconductor material. These materials can really revolutionize the world's energy system. These materials can allow the energy to flow efficiently through them without any loss of energy. So they received a great interest and they have a great potential and many cost-effective application in various fields. So it is my pleasure to make a talk on methods for enhancing the performance of high temperature superconductor materials. So in this talk, we will start by answering the question, why superconductor? Why we selected superconductivity? So we will present the importance of superconductivity in our life and the main important applications of superconducting materials. After that, we will describe the fundamental properties of superconducting materials, their limitation, especially the problem of energy dissipation in high temperature superconductors and how to solve these detrimental effects. Then we will report the synthesis of superconductors and their various structural, microstructural, morphological, electric, and magnetic properties.
I'm sorry to interrupt you, Professor Yasin. Could you please share your slides? Because we cannot see your slides.
Sorry, just okay.
Yes,
Sorry, okay. Thank you.
it works now. Thank you. Thank you. You please
Thank
continue.
you. Yeah. So as you well know that waste heat is all around you. So on a small scale, if your mobile or your laptop, your computer feels warm, that's because some of the energy powering the device is being transformed into unwanted heat. So on a larger scale, electric grid, for example, such as high power lines, can lose over 20 to 40% of their energy during the process of only transmission. So this loss can even reach 80% in some poor countries. So this is really a tremendous amount of wasted money. So globally, the computer systems and Facebook and other, they require enormous amount of energy, of power to power massive cloud service and data centers, and even more energy to power water and air cooling systems. So is required to offset the heat generated by these computers, laptops, mobile, and etc. So from where does this wasted heat comes? As physicists, we know that it comes from electrons, and these elementary particles of an atom move around and interact with other electrons and atoms. So since they have an electric charge, as they move through the material like metals, which can easily conduct electricity, they scatter off other atoms and can generate heat. So here we are talking about the well-known Joule effect. So by using superconductor, they can revolutionize, as I mentioned, the world's energy system. They are materials that allow them without generating any unwanted heat. So they receive it great interest and have great potential and many cost-effective application in various fields. So by using superconducting materials, we will be able to transmit very high electric power over very long distances without any loss of energy or any voltage drop, not like the conventional or the standard materials like the copper. So they can be used in transmission cables to transport the current or in windings for motors, generators, and transformers. And they can replace, for example, if we would take the case of 10,000 kilogram of vintage copper cables, they can be a conducting wire. There are also many other advantages. As I mentioned, we can say no power loss, and also they can carry tremendous amount of power. So they can create and generate very high or very intense magnetic field. And compared also to conventional conductors, they need less maintenance and also less maintenance cost and better lifetime. So they are also environmentally friendly and also high, because why? Because high tensor superconductor materials need only liquid nitrogen as a coolant to work as a superconductor. So the coolant liquid nitrogen is a dielectric medium, and so no need for the oil to generate energy. Another example in recent years, you all know that the global warming become really a serious environmental issue. So the great majority of land transport machines, mainly automobile, consume large amount of petroleum, either in the form of gasoline or diesel fuel. So to cope with these issues of depletion of fossil fuels and the global warming caused by CO2 emissions and realize sustainable motorization, significant improvement in energy efficiency and a shift to non-petroleum alternative fuels are required. So nowadays, the world is oriented towards electric vehicles, which use electricity to deliver power from a motor. So realizing high efficiency, high performance motor is the key to the development of electric vehicle systems. So thanks to the recent improvement in the performances of high temperature superconducting wires, the feasibility of a more efficient electric vehicle system by applying superconducting motors is being really actively investigated. So, and also additionally, superconductors could be used for some technology based on strongly resonance coupled method that realize large power charging without any wires through the air. So we can call them as superconducting wireless chargers for electric vehicles. And this can wirelessly charge the power in a magnetic resonance scheme by combining a cryogenic cooling vessel and a superconducting transmission coil. So the superconducting wireless charger for an electric vehicle generally comprises of a transmission coil, which is installed in the floor, in a floor or in a wall surface of a parking lot, which resonates at a specific resonance frequency and emits an electromagnetic wave. And there will be a reception coil, which is attached to the lower surface or to the side surface of the electric vehicle, which will receive the power from a specific resonance frequency, which is identical to the transmission coil, and transfer the power to a load of the electric vehicle. Here, for example, in this graph, we presented some examples for the application of superconducting materials that really require high current and high magnetic field than do other, like in comparison to conventional conductor. So as you can see here, so extremely high current and magnetic field could be reached only by using superconducting materials. So for example, here, the electrical generators here made with superconducting materials wires will be more efficient than conventional generators wound with copper wires. Also, the superconducting generator used in the field of windings, for example, they can produce also higher current, and therefore you can create a much higher magnetic field. So also it has some other benefits, like for example, the small size. So their size and weight is about here, for example, the half when it is compared to conventional generators. So also superconducting generators, they have also the benefit of low energy consumption than conventional generators. So their efficiency is above 99% and a 50% reduction in input power losses. So these graphs here illustrates the cost against the power. So as it is clear here, we can say that conventional technologies really they cost cheaper. They cost cheaper when we are dealing with low power level. But when we are dealing with high power or high energy, of course, here we noticed that the cost of superconductors based technologies is much lower and achievable compared to the conventional technology. So the utilization of the superconducting materials is really significantly boosted in the recent years. For example, here the curves of the use of motors, for example, and the transformer-based technologies are expected to reach up to 70% by 2025 in upcoming few years. So the curves of the use of superconducting generators and also cables are expected to reach 50% by 2025. So at the same time, the cost will be reduced progressively. So who knows? Who knows? Maybe one day we will have electronics like mobile or laptop or computers that utilize superconductors to give us really smartphone or laptop that only needs to be charged one time, once a time per year, or maybe for several years that you need to charge them one time. So it's anyone guess, but really with the nowadays with the rapid advances in our technology, we will all likely see the superconductivity in our lives as a regular future sooner rather than later. Here, for example, I summarized some of the important technological applications of superconductors materials. In addition to the previously mentioned examples, here we can mention quickly that superconducting materials, they can be used to transport huge amount of the current without any loss of energy. So they could be used in the transport of energy. So here, for example, they can be used in transmission cables or in windings for motors, generators, and transformers. They could be also used in superconducting magnetic storage system to store enormous amounts of energy with minimal loss of energy. Also, the superconducting materials, they are largely used in the production of sensitive magnetometer that we call it the SQUID. So the SQUID, superconducting quantum interference device, which are the most well-known efficient system to measure magnetic field with great accuracy and even to detect and measure the Wick's magnetic field. Superconducting materials, as I mentioned, that can be used also in the production of powerful superconducting electromagnets, which are, for example, necessary for maglev levitation train. So they can be used in the transportation area. Nowadays, the well-known examples for the largest application for superconductivity are the magnetic resonance imaging and the nuclear magnetic resonance machines, MRI and NMR, which really require strong magnetic field, which can be provided only by using powerful superconducting electromagnets. We can find also superconductivity in the utilization in particle accelerators to accelerate particles with a speed near to the speed of the light, like the well-known CERN's Large Hadron Collider. Recently, superconductor materials, they started to be used in a quantum supercomputer, which will lead really to very fast computing calculation. And there are many important applications of superconductors. Just here, I tried to mention some of them, and there's still many other fields that can be covered by the superconductors. So what's make the superconductivity interesting? Let's here focus on their fundamental properties. Actually, the superconducting materials, they display two fundamental properties. First, it is the zero resistance or zero electric resistivity, which means that the conductivity is finite. So the superconducting materials, they are considered as perfect conductor. They have the capability to conduct an enormous amount of current compared to conventional conductor without any loss of energy. But of course, this is happened below a certain critical temperature. The next fundamental or important discovery in the field of superconductivity is the Meissner effect. So Meissner effect, or in another word, perfect diamagnetic, or the perfect diamagnetism. So when an external, for example, when an external magnetic field is applied to a superconductor meteors, the superconductors will tend to totally exclude, to totally expel the flux line from its interior. So here, of course, here also the external magnetic field should be below a certain critical magnetic field. And one of the spectacular phenomena of Meissner effect is magnetic levitation, as I mentioned the example of magnetic levitation train, as shown in these examples. So in summary, I can say that superconducting materials have two fundamental characteristics: zero resistivity, so they are considered as perfect conductor, and they display perfect diamagnetism. So and also the superconducting materials are limited by three main important physical parameters that we mentioned: the critical transition temperature, the critical magnetic field that we can note, for example, Hc, and also critical current density. Here in this slide, we present the evolution of in the critical transition temperature as a function of the year for the main important superconducting materials. Shortly, we can classify these materials into the following big family. We have the conventional superconductors, which are mostly pure elements or alloys, plus also some kind of furans. Also, there is also like the carbon 60, elements based on carbon 60, and also there is the pnictide, which are based on iron element. So most of these materials that I mentioned display superconductivity superconductivity phenomena at critical transition temperature below the liquid the temperature of the liquid nitrogen, which is 77 Kelvin. So here we need the liquid helium to cool and to show the to cool these materials so that they can show superconductivity phenomena. So one of the interesting family in superconducting activity, they are the cuprate superconducting materials showed by blue color here. So which will be the subject of upcoming discussion. They are called cuprate or cuprate oxide superconductors because they are mainly based on copper and oxygen, and their crystalline structure consists of different layers of CO2 planes and CO chain. So the well-known cuprate superconductor that we will focus on it is the YBCO yttrium barium copper oxide material. So as it is clear, most of these materials display critical transition temperature above the temperature of the liquid nitrogen. So they are classified therefore as high temperature superconductors. So to show superconductivity phenomena, they necessitate only the liquid nitrogen as coolant medium, which is very easy to be produced, and also it is much cheaper when we compare it to the liquid helium. So generally, these materials, particularly the high temperature superconducting materials, they are considered as type 2 superconductor. So these materials display in their phase diagram a mixed state where there exist normal phases and there exist also superconducting phases called as vortices. So under the effect of an applied magnetic field, and in the presence of transport current density, a Lorentz force volume will be applied on the vortices. So this force will put instantly the vortices in motion, and which will induce dissipation, or will induce a non-zero resistivity, and consequently a dissipation of the energy. So once we perform, for example, the measurement of the current density as a function of magnetic field, we find that it decreases sharply, quickly, with increasing the intensity of the applied magnetic field. So to minimize or to reduce this detrimental effect, we need and to improve also the electrical property of superconducting meteors, these vortices should be pinned. So to achieve this objective, the generation of efficient structural defects inside the superconducting matrix could be a possible way. So these generated defects, if they are well distributed, they can allow to pin the vortices in their places and thus prevent the energy dissipation. So here we should be careful. Sometimes the defect can also be detrimental to the superconductivity. They can destroy the superconductivity. So the art here is how to create good defects for a given application. So the good defects will act as really strong artificial pinning centers within the superconducting materials. So one of the efficient ways to enhance the superconducting performances of high temperature superconducting materials is the inclusion of nanostructural materials within the superconducting matrix that could be in the vortices. So firstly, we need to prepare our superconducting precursors. There are different techniques that can be used to prepare the superconductor precursor. Then some amount of nanostructural material should be added to the precursor. They will be mixed. For example, if we will follow the solid state reaction, they will be mixed, ground, and compacted in the form of pellets. Actually, there are many other techniques that can be used. It depends on the desired application. It could be in the form of thin films, so we can use in coating, or of in the nanofiber, so we can use the electrospinning technique. So it depends on our kind of application. Then, of course, will be subjected to heat treatment at high temperature. And in this presentation, we will mainly focus on the analysis of the structural properties using XRD technique, the morphology, and the microstructure by using the SEM and PM coupled with EDX system, and also the electrical and magnetic properties, which were performed using the PMS coupled with vibrating simple magnetometer. So as additives to superconducting materials, based on our recent publication, I selected the following kind of nanoparticles or nanomaterials. So here we will try to make a summary to investigate the effect of different factors related to the nanostructural materials. For example, here, the effect of the shape, for example, nanoparticles or nanowires and nanotubes, like the case of carbon nanotubes. The effect of also of the size, like for example here, particle size near to 100 nanometer for tungsten oxide, 20 nanometer, for example here for the cobalt chloride. For silica oxide, they are around 30 to 40 nanometers. So we will study also the effect of particle size. Also the effect and the nature, or the effect of the nature and the type of nanostructural materials, like for example, semiconductor nanoparticles, tungsten and titanium oxide, or magnetic nanoparticle like cobalt chloride, insulating or insulators like silica oxide, and many other examples that we will show in upcoming slides. So these are some of the recorded XRD patterns for the YBCU superconductors added with different amount of tungsten oxide nanoentities and magnetic nanoparticles, like for example the cobalt chloride. So as it is clear here, we can see a predominantly single YBCU phase with orthorhombic structure in all prepared sample, and also no noticeable shift when we look to the enlarged view, no noticeable shift in XRD peak, also no noticeable variation in the latest parameters, especially for low doping amount. So so this indicates that the orthorhombicity of YBCU compound was conserved with the addition of very small amount and also appropriate amount of tungsten oxide, for example, nano entities. But in the opposite case, when we take the example of including magnetic nanoparticles, they affected greatly the different plates parameters and also the orthorhombicity. So which will reduce gradually with increasing the content of the additive. So here we can say that depending on the objective, we can select the appropriate nanomaterials for doping. If we are dealing with the improvement of the superconducting performances, we mainly aim to do not affect the structural properties. If we are tending to apply, for example, our materials as a magnetic probe, so it should be very sensitive to the addition. At that time, we need to look to some examples like magnetic nanoparticles. Here, for example, these are SEM observation for YBCU superconductors added with tungsten oxide, but with different shapes, nanoparticles and nanowires. So they showed that the nanostructured materials with diverse shape, they affect differently the morphology of the final product. For example, here in the case of nanoparticle added samples, we can see some nanometric bright entities of tungsten oxide which are dispersed on the surface or embedded within the YBCU grains. And the density of these nano entities increases with the increase of dopant content. However, for the case of nanowires added samples, we noticed that the tungsten nanowires tends to enter between the grains and to fill the voids between them. So this will provide metal bridges network among the superconducting grains, and consequently the connectivity between the grains will be enhanced and the porosity also will be reduced with the doping. So in this case, it is expected that the percolation and the transport of the current would be improved much more in nanowires added sample. Similarly, in a study performed in titanium nanoparticles effect on the morphological property of YBCU compound, the SEM analysis also showed the presence of nanometric bright entities of titanium oxide dispersed within the grain, but contrarily to the previous example, here the titanium nanoparticles also at the same time tend to fill the voids between the grains, like the tungsten oxide nanowires. So here it is expected that the titanium oxide nanoparticles can show much better electrical transport properties than the tungsten oxide nanowires, because here we improved the intragranular and intergranular properties. Another important information to say is that the inclusion of nanoparticle into high temperature superconducting materials could generate some additional structural defects. For example, This is a TM micrograph taken for YBCU simple added with titanium oxide nanowires, which showed the presence of inhomogenities as well as twins. So the observed planar defects and inhomogeneity can be seriously acting as efficient sources of flux spinning. We presented also here an example of insulating nanomaterials such as silica oxide. So here the TM micrograph interestingly showed the presence of nanophases which are rich in silica embedded within the YBCU superconductor, as well as we can see here some straight line, as well as the appearance of interfaces and columnar defects that could really effectively contribute more to the thinning of vortices. However, for the case that we mentioned in XRD, if we take the case of magnetic nanoparticles, they are harmful to the structural and morphological properties. For example, for the case of adding magnetic nanostructural materials, we found, for example, that the grain size is greatly reduced with increasing the content. So it is evident here that the type and the nature of the incorporated nanostructural materials, they affect in a different manner the morphological properties. For example, here also TM images of magnetic nanoparticles added to YBCU superconductors revealed the presence of relative contrast and also high density of twins, also stacking fault, and as well as the formation of nano phases here indicated by the arrow here within the prepared YBCU compound. So such microstructure could reinforce really the capacity to pin the vortices. Just to save the time, we can escape this. So we presented here the electrical resistivity measurement versus temperature of YBCU samples added with different amount of nanostructural materials. They have different behavior, the semiconductor tungsten and the insulator silica oxide. So it is evident that the different tungsten nanomaterials added to YBCU displayed here a metallic behavior in the normal state, which is followed by a transition to the superconducting state and below a certain temperature, which we call it the critical superconducting transition temperature. And also the addition of small amounts leads to decrease in the resistivity. For example, when you compare the 0.1 compared to the pristine one, it leads to decrease the resistivity in the normal state, it does not also affect the critical transition temperature, or sometimes to slightly increase the critical transition temperature for some cases. So this is mostly attributed to the enhanced connectivity between the YBCU grain, as we showed by the morphological observation. Considering the case of adding insulating nanomaterials like the silica oxide, we observed really metal-like behavior in the normal state for lower contents, and then semi-metallic behavior for moderate contents, and a notable insulating behavior for higher concentration. So this can be understood due to the nature of the inclusion. So evidently, the TC0 showed a sharp transition, a sharp decline for higher concentration of silica oxide nanowires. Here we presented other results of electrical resistivity versus the temperature once magnetic nanoparticles are included. So in the case of in this case, the cobalt ferrite nanoparticles provoke a rapid degradation in both intragranular, for example, if it was here, in the intragranular properties, as well as in the and the intergranular properties of yttrium-based superconductor. So here the cobalt ferrite lead to a great reduction in the metallic phase and increase in the semiconducting phase fraction. So the inclusion of magnetic nanoparticle should not reflect, here we can see there is a destruction of the electrical resistivity, but this inclusion should not reflect definitely that the inclusion of magnetic nanoparticles, that the capacity of the transporting high current will be deteriorated. We can escape this one to save the time. We can also look, we can focus on this slide. So on the other hand, we performed, for example, we focused on the magnetization versus magnetic field measurement, which were performed at the temperature of the liquid nitrogen. By means of this measurement, we can deduce the critical current density GC from magnetization. We can determine the critical current density by using the Bean model. So this parameter, I mean the GC, is an evaluator parameter to judge if the material is useful for real, for practical application or not. So here we presented the GC values of one of the examples, like the tungsten oxide nanowires added to YBCU superconductor. So here we can see, in comparison to the Bristol compound without addition, there is a significant improvement in the absence and in the presence of an externally applied magnetic field. This is due to the addition of tungsten. So the enhancement in the critical current density value with nanowires inclusion, when we look to this data, is by about, we can say, 4 to 5 times in the absence of an applied magnetic field, and it is about 20 to 25 times under an applied magnetic field of 1 Tesla. So here the pinning strength is really reinforced and strengthened with the tungsten oxide addition. Then we calculated the pinning force from the GC measurement. We determined the pinning force, and the plots are presented in this graph. And different pinning mechanisms were considered according to the Hughes model. After a careful analysis and fitting, we deduced that over the applied magnetic field range up to this maximum, for example, the normal surface spinning is mostly the dominant pinning mechanism in the Preston compound. However, in doped sample, the sample added with tungsten oxide nano entities, we found a contribution of normal surface spinning and point pinning mechanism. So this indicates that the inclusion of tungsten oxide nano entities enhances the flux spinning capabilities by strengthening, by reinforcing the contribution of the normal centers in pinning properties. In addition to magnetization, we investigated the AC susceptibility measurements for some compound. Here, for example, we presented one of the case of AC susceptibility measurement as a function of temperature, which is useful and practical to evaluate the intergranular properties. It means the properties between the grains. So here the formation of the peak in the imaginary part curves is originated from the energy losses caused by the penetration of magnetic field in the intergranular networks of weak links. We can see here that the loss peak, the amplitude of the loss peak reduces with the addition of tungsten oxide nano entities. Furthermore, the loss peak at a certain temperature, for example here, it shifts to higher temperature achieves to high temperature with the addition of nano entities in the YBCU compound. And this shift is much slower, for example, in the case of nanowires added simples. So these results revealed again an improvement in the flux spinning and inter-grain grain coupling properties. And to validate this evidence, we calculated the intergranular critical core density of the samples by means of this measurement and by using the bin model. So it is found that the intergranular critical core density it improved with tungsten oxide nano entities addition. And the nanowires, for example, showed the best values among other samples. And the improvement in intergranular critical core density is approximately 5 times with the tungsten oxide nanowires addition. So with the help of the SEM and with the TM observation, and also with the help of several other analyses, we established that the improvement in the values of intergranular and intra and intergranular critical core density and the pinning force are mainly attributed to the variations in the composition of grain boundaries due to the nanoparticles that reside among the grains, also to the nanophases implanted into the YBCU matrix, also attributed to the intensification of the interface between the YBCU matrix between the superconducting grain and the nanophase, as well as to the generated defects within the sample. So let me just run over the key point again. So in a summary, we can say that superconducting materials are of great importance nowadays, as well as they constitute a part of the new technology for improving the quality of our life in the future. But unfortunately, these materials faced some difficulties that limit their wide application, especially the energy dissipation phenomena. So we established that one of the useful ways to boost the superconducting performances of high temperature superconducting materials is the inclusion of nanostructural materials. However, we need to carefully select the appropriate nanostructural materials. So as we saw here in the different slides, the main important features related to these nanoparticles are the size, the dimension, the nature, and the behavior of the of the nanostructural materials, the shape, and the concentration of the doping elements or materials. So the inclusion of appropriate nanostructural materials could lead to improve the intragranular and intergranular properties, which will greatly affect on the performance of the final product. So the implanted nanophases into the high temperature superconducting matrix and the intensification of the interfaces between high temperature superconducting matrix and the inserted nanophases could play as efficient pinning centers to minimize the motion of the vortices. As well, the inclusion of nanostructural materials could generate structural defects that could reinforce the pinning strength of vortices. The next stage after this achievement, so one of our perspective works is to further enhance the superconducting parameters by adopting other methods like deposit enhanced samples in the form of thin films and prepare superconducting wires or tapes to transfer to transport our products into commercialization. So nowadays we are in the stage, we are focusing on the commercialization of our product and how to achieve this level. Thank you very much. By taking this opportunity, I would like to dedicate special thanks to all our collaborators from around the world.
But we are not listed in the collaborators here.
Oh, you are listed here.
Yes, you missed us.
No, no, no. I would like really to dedicate all our collaborators from different countries without any border. We are collaborating with people from India, Germany, China, from different
Yes, yes, I can see it's written MAT University, Haryana.
yeah.
Yes,
and
yes.
we did the great achievement with our collaborators. We published hundreds of papers together, and also we initiated several projects together. So really, I want to dedicate special thanks to all of them, particularly to those from this university that I mentioned in this list. The list is very long, but this is the main important collaborators with us nowadays. We want to thank them for their continuous valuable help and cooperation in the area of superconductivity on nanomaterials, nanotechnology, environmental remediation, energy, whatever, yani. We are working in many different kinds. And all people are welcome for any
Yes, you can note down the email, students.
Yeah, so by also thanking this, I would like to say that we are open to any kind of collaboration and cooperation. These are my personal email for any further communication if student or any person need to communicate with us. Thank you again for your attention.
Thank you, thank you. Thank you
If you
very
have
much.
any questions, I will be pleased to answer them. If you also have some suggestions, you are most welcome.
Yes, thank you. Really,
Thank you.
the presentation was wonderful. You started with very minute details of superconductivity. You started with the magnetism. You talked everything. You've also given the live picture of levitation. So I have a question, like, when, that ball was rolling, so did you require some liquid nitrogen?
Of course. One of the requirements for these materials to show their superconductivity phenomena, it should be cooled at low temperature. So they show their superconductivity below a certain temperature. So below a certain temperature, the electrical resistivity will suddenly drop and become equal to 0. So below this critical transition temperature, the material will show this interesting phenomena and interesting Meissner effect phenomena. So you need to cool the materials below this temperature. So it depends on the kind of the materials will be used. There are what we call it low temperature superconductors. Low temperature superconductors, they display critical transition temperature below the 77 Kelvin. So mostly it needs to use the liquid helium. And for the case that I presented, they are high temperature superconductor materials, which display temperature above the 77 Kelvin. So here, much cheaper coolant medium, which is the liquid nitrogen, can be used. Actually, there are a lot of now of research, fundamental research and theoretical computational research to further improve the superconducting phenomena. The critical transition temperature. I hear it that they are near to the room temperature, but still the main challenges with this kind of materials that they show with room temperature superconductors, they need really enormous pressure, which can even reach more than 200 and 300 gigapascal. So our aim is always to focus on superconducting materials above liquid nitrogen. We aim to reach the room temperature, but in normal condition.
Okay. Okay. Thank you very much for the informative and inspiring speech. I know you are a wonderful researcher, in top 2% researcher around the globe by the Stanford University, and you are very hardworking. We really appreciate your time, and thankful to you. Thank you very much.
Most welcome, most welcome.
Okay,
I try to focus on some fundamental properties, because I'm sure that some students are with us.
Yes.
So I try to explain some fundamental properties like
Yes,
superconductivity.
yes. We really
more than
enjoyed.
focusing on the experimental
Yes.
result.
Thank you. Thank you very much.
Thank you.
Thank you. So big round of applause to Professor Yasin. Thank you very much. So our next speaker is Dr. Nikhil Bhalla. So he's a versatile person. He's a very good researcher. Again, top 2% researcher in, can we see Dr. Nikhil Bhalla? Yes, we want to see you first before the slides.
Yeah, I was just about to organize.
Yes. So here is Dr. Nikhil Bhalla. He's a dynamic person. I know him since his childhood. He's a graduate from BITS planning. Then he was in Taiwan, then Japan, then University of Bath, and finally he landed in University of Ulster as assistant professor. So he's working in biosensors, nanotechnology, and so many, versatile fields he's working. And jointly, recently we backed one project from British Council. So one partner is University of Ulster, second partner is University of Delhi, and third industry partner is NanoLatisX. So it's a privilege to have you here, Dr. Nikhil. Thank you for your time, and definitely our students and listener, they will get benefited from the research and the talk which will make. Thank you very much. Please proceed.
Thank you very much, Professor Atul Thakur, for your invitation and kind introduction. So I work in the area of biosensors, and primarily, I work from the electronics and optical background. I hope you all can hear me and see my screen as well. Yeah, so if not, just drop a message here on the chat window. As Professor Thakur mentioned, that I work in the area of biosensors. There are several biosensors that we have produced in the past, but I would like to talk about one of these sensors, which is more relevant to the current pandemics, or let's say the COVID virus, or the COVID-19 that has spread across the whole planet. So we developed one of these sensors that is capable of detecting multiple variants of virus, multiple variants of this COVID virus, and that's what I will talk about. But before we go into details, I will speak about our technology here and also give you a brief introduction about what biosensors are and the ideal properties of a biosensor, which can address the need of pandemic. Also, I'll speak about a little bit on LSPR technique. I'm not entirely sure how many of you are aware of it. And then I will introduce MIPS, which is molecular imprinted technology. And then I will show how we combine these two bits to detect multiple variants of viruses. And of course, in the end, I can highlight some aspects which speak about scaling up of this technology. So if you have any questions, anytime you can, stop me here if there is an opportunity, or you can also ask me at the end of the presentation. It's up to you. So if we speak about biosensor, here I have a schematic showing what a biosensor is. So essentially, the need of this biosensor comes from the need to measure something that is required, and that need can come from your healthcare perspective, or also from the perspective of food security. So for example, if you wish to detect if your food is safe to eat, of course you need a sensor or a tool which can measure that or quantify that. So that's what we call as analyte. And then the first aspect of your gadget, or let's say the technology or biosensing technology, is the bioreceptor, which has direct interaction with your analyte. And once this interaction takes place, then you have a signal which is generated. And that signal can be in form of light, heat, pH change, mass change, or even some sort of a current or optical, let's say, stimulus which can be generated. So these bits are then picked up by transducers, and then transducer essentially converts one form of energy to another, and you can then use appropriate electronics to quantify that signal, and perhaps also use a display system to display your result. So this is something what is having an interface with the user. So this whole thing, as you see here, is a biosensor, and in between this, or let's say some aspects of this can also be categorized into biorecognition event, or signalization event, or quantification events. And that's what I will show you with the help of MIPS, which we developed, that can do some biorecognition, and how we generate the signal using the LSPR, and how the quantification is done. So speaking of the need of biosensor in pandemics, ideally, you need something that can be made affordable, cost effective, and is also disposable, because obviously you don't want technology to sitting on the table which no one can afford, yet it can detect pathogen or some viruses of your interest. So some of these features, which if you wish to read more about them, what sort of ideal characteristics biosensor should have, which meets the requirement in pandemics, you can refer to one of these papers in ACS Nano. And to address these technologies, to address these needs, I would say, we have several biosensors, or I would say, competitive technologies which are available, ranging from microscopy to crystallographic techniques to what we call as the electronic and optical biosensors. So I focus in this area of optical biosensors, and one of the examples that I will pick up is the localized surface plasmon resonance technology. So before we actually see how we can create a biosensor, I would like to introduce you to what is nanoplasmonics and what is LSPR. So here, if you see one of these, cups, which is a Roman cup and commonly known as Lycurgus cups, you can find this in British Museum, and perhaps also you can see some of these artwork in several monuments, including churches in Europe. So what really you have here is that this glass is made up of nanostructures comprised of gold and silver, and we categorize them into noble metals which have certain dielectric properties. Now, those certain dielectric properties allow light to be absorbed at a certain wavelength, and then light also gets transmitted, or let's say the rest of the light which is not absorbed gets transmitted. And as a result of this, if you see this structure, or let's say if you shine light from inside, it appears slightly pinkish, and if you keep it in the dark, it appears, let's say, slightly greenish. So if I show this video again, you can clearly see this effect. So now this was something which wasn't really very, let's say, explicit until very recent, when, Professor Richard Van Duyn in Northwestern identified this property and associated with the scattering and absorption of light taking place in nanomaterials, and which was primarily due to the free electrons residing on those metallic nanostructures. And that's what later was considered or put into the field of plasmonics, where those electrons associated with absorption of light, they oscillate at a specific frequency, which is associated with, as I said, plasmonic frequency. And we can actually capture these events using a very simple tool, that is your spectrophotometer. And we utilize these properties not for building, materials such as what you see here, but to create biosensors. And to make it more simple, if you take one of these metal structures, shine light, you have some resonances. As I said, free electrons, they oscillate. And I also mentioned that you can capture this using a spectrophotometer. And that's exactly what you can do. You can capture the spectrum, and you can capture the wavelength at which these resonances take place. Now, the whole idea is that if you attach some biomolecule onto it, there are shifts in the resonances. So you can imagine that you have a sea of electrons which is resonating, or essentially you have a resonance of electrons taking place. And now if you touch that, it will perhaps show changes in its own properties associated with either damping or getting much more excited. So we usually see that when you attach when you attach these biomolecules on nanostructures, the dampening of oscillation takes place, and that can be observed by change in frequency. So the frequency at which they were oscillating decreases and wavelength increases. There are several equations which correlate these features, and in fact we have developed quite a bit of fundamental equations to correlate some of these features. But one of these equations which allow us to quantify these shifts is associated with change in the wavelength. So the change in wavelength can be associated with the changes in the local dielectric constant, or you can say changes in local dielectric constant, which has, let's say, a depth of 10 to 15 nanometers. So anything that attaches within a proximity of 10 to 15 nanometers away from your metal nanostructure is depicted or is featured by this delta n, whereas the rest of the features are more or less constant with decay length, size of your nanoparticle, and also bulk refractive index. And once you can associate those changes in refractive index with changes in wavelength of your nano resonances, you can then attach your X number of molecules and associate the concentration of your analyte binding on your surface with wavelength change. So this is how we create a very simple biosensor, and how we have utilized this to actually detect COVID is what I will show. So in this slide, you see one of our chips that we've created. It is comprised of nanostructures of silver, and that's how the chip would really look like, if you have it in your hand. So it's a large-scale chip, and if you look deeper into it, it is consisting of several nanostructures that gives rise to this slightly yellowish color as well. What we've done here is we have created some molecular imprinted polymers on these chips, which are, very simple to make. And you can think of these polymers as artificial antibodies or artificial elements that allow you to attach to a specific, target of your interest. So we have also pioneered a process where we can selectively create polymers to attach to a specific target. And we do that by a solid phase process. So you can imagine that you have, let's say, some target of your interest, you throw that on a solid surface, and then you start polymerizing the whole surface. And in the end, you remove those targets, and you're simply left with a scaffold which will attach those specific polymers. And that's exactly how we create these MIPS. The advantage of these MIPS is basically that they're more stable, they're more resilient as far as its temperature requirements are concerned. So you do not have to worry about storing these into ultra low temperatures, and perhaps it will allow you to sustain your chips for a longer duration. So then by drop casting, what we've also done is we've attached these MIPS on our nanostructures as the silver LSPR chip. And there's a small characterization that we've done to show that MIPS actually attach to our surface. So it's done using AFM. And now what we do is we collect samples from patients. We also collect, prospective patients, I would say. We've also had some trials on humans, but we've not gone very far. So this shows how you can actually do a test rather than other results showing how the test was actually done. So you can collect a sample from the body and then centrifuge this, and in the end you collect your serum and throw it on the sensor surface, which is immobilized with your MIPS specific to your COVID proteins. Or what you can do is you can collect your sample from nasal cavity. We are all aware of this, and then you can dilute the sample in PBS and then throw this sample on your sensor surface to see the results. We've done this in both buffer and blood, and what we see is if we sort of calibrate the sensor to observe wavelength and absorption shifts, as I explained in my first few slides, there is a distinct shift which is seen as soon as your analyte of interest attaches. And over here, these wavelength shifts are quantified. So if we pick up the alpha, beta, and gamma type of your proteins, you can clearly see that there is a distinct concentration or dose response which our sensor has achieved as compared to your homologous proteins, which are essentially from human coronaviruses OC43 and 229. And also, if you do not have MIPS, you have low sensitivity, as demonstrated by one of these curves. We've also translated this in blood, so not only on buffer, as I mentioned. Here you see this concentration response of the sensor in blood. And then in the next slide, I will try to show you a bit more on the visual evidences and statistical correlation between your blood and buffer measurements. So here you see all the three steps. You have your silver nanoparticle chip, and then it is immobilized with MIPS. And once the proteins of our interest attaches here, you see a further change in the morphology of your sensor. So really what we have shown is that you can successfully detect the target of your interest here, and both in your buffer solvents and clinically relevant, or let's say more clinically relevant sample, which is blood. And there is a very strong correlation between the measurements done in serum and buffer. And that's the sort of a relationship here. And we further tested its stability as well. Day 1, day 15, and day 30 results are shown here. So by this, you can clearly say, or clearly see that one of our sensors that you've just seen in the previous slides is suitable for measuring multiple variants of protein. And this is something very important, because traditionally when a virus mutates to its new variant, there is a need to develop a new serological test. However, we have a sensor, or we have a bioreceptor that can attach to any variant of any potential variant, which is yet to come in future, and has a interaction with the host cell. So which shows that the MIPS has some capabilities which is beyond the state of art achieved by your antibodies. And also, to conclude, I would say that the limit of detections which was achieved by us for 3 different variants is in the range of femto and picomolars. So it suggests that these are also very sensitive, and the whole assay time, including sample collection to results, is less than 30 minutes. So we do not need to wait for long durations for our results to come using PCR and stuff, and it's completely extendable, or it is transferable to portable systems, which I will show you one of our portable systems that we are using. So you can perhaps think of home testing. You can take this to your home and take some of these chips, put it in the chip loader or cassette, which we have, use our MIPS technology, and detect potential COVID variant. So this work was done with our industrial partner and some collaborators in within Ulster and United States. So I would like to acknowledge them here before I bind up. And if you are interested to know further details or similar research which is on these lines, you are more than welcome to visit my site, and I'm happy to answer your questions now. Thank you for your attention, and thanks again.
Thank you, Dr. Nikhil.
Thank you.
It was a very nice presentation, and we thoroughly enjoyed it. If anyone has any questions. No questions. I think the presentation was very good. And thank you, Nikhil, for taking out the time and enlightening our students and faculty here. So if anyone has any query regarding it, I think Dr. Nikhil is always available, and his email you can take from me, and you can discuss with any collaboration. He's our old collaborator. So thank you for your time. And again, thank you very much, Nikhil.
Am I audible? Hello?
Yeah, I can hear someone speaking.
Okay. Thank you. I'm Florin Hunzis, and I'm from Marish Menekashkwa University. I have a question about biosensor, as you have been saying about it. So you told us that it takes about 30 minutes to get the result. And I would like to know, like, how long it takes for you to process the urine? I mean, the sample, the blood sample, how long it takes for you to process the sample?
Within 30 minutes. So just take the sample, centrifuge in 5 minutes, 5 to 10 minutes, take the serum out, measure it. Within 30 minutes. So let's say if a patient comes to us from taking the sample and giving the result, less than 30 minutes.
And the second question, and why do you use PBS buffer? What would happen if you use any other buffer in any collecting the sample?
So see, we have successfully tested with PBS, and we have optimized the condition for pH there. That's why, I say PBS. There is a possibility that you can use other buffers as well. We have not tried it. That's all.
Okay, thank you.
But you need to make sure that you maintain the osmomolarity of your proteins and the other biomolecules involved here. So if you can control the ionic strength and pH, you can use any buffer.
Okay, thank you so much.
Thank you so much. Any other question? Okay, then thank you, Dr. Nikhil,
Thank
for
you
taking
again.
up the time.
Yeah, and thanks a lot.
Okay.
Yeah.
Thank you, ma'am. Thank you very much. Now we are proceeding towards the oral presentations. So though I would like to announce that for the series of oral presentations who are present here, it is 8 minutes per presentation, followed by 2 minutes question answer session. So overall 10 minutes, it should not be exceed than 10 minutes. So make sure, okay? It is one of the criteria of scoring the marks as well. So make sure that you must be stick to the time limits. So first presentation is with the Priya Goyal. Priya Goyal is present here. Next is Priya. So who is present here? Please come. Avinash.
Yes, sir.
And I would like to request the judges of the session, Dr. Rao sir, probably is not here. Okay. Dr. N. Vijayan sir, please, you are requested to evaluate the sessions. And Dr. Rajesh. Okay, so I would request all the honorable judges for the evaluation of the sessions. These are the young minds over here. Thank you, sir.
Thank you. Good afternoon, everyone. It is my pleasure to be here today to present my research on the topic, the role of nanomaterials in high-performance Li-Fi system. This is a significantly evolving field and a lot of exciting developments, and I hope to share some of my insights with you. Firstly, let me give you a brief overview. In today's world, wireless communication has become an indispensable part of our lives. We rely on it for everything from staying in touch with our loved ones to doing our businesses. But where did it start? Let me take you a moment to give you a brief history of a wireless communication. It dates back to the late 19th century with the invention of radio waves. Since then, there have been several advancements in wireless communication technology, such as the invention of Wi-Fi in 1990s. However, traditional Wi-Fi has few limitations. This is where we can use Li-Fi. Li-Fi
uses light waves to transmit data instead of radio waves. This is done by modulating the light source, such as LED, to transmit data. Li-Fi has several advantages over traditional Wi-Fi, such as higher transmission rates and greater security and lower interference. To illustrate the difference between the Li-Fi and the traditional Wi-Fi, let's take a look at this slide, where you can see the Li-Fi uses light waves to transmit data, where the Wi-Fi uses radio waves to transmit the data. And the Li-Fi gives a higher bandwidth with up to several gigabytes per second, and it has an unaffected radio frequency of interference. Basically, it is short range type, but it's more secure than the Wi-Fi because Wi-Fi can be interrupted or hacked. So while Li-Fi technology has several advantages over traditional Wi-Fi, it also has some of the limitations. For example, it requires a direct line of sight between the transmitter and the receiver and is not suitable for the outside use. And this is where the nanomaterials comes in. Nanomaterials, with their unique properties, as our Honorable VC Sir said, have a potential to revolutionize the technology. This presentation will not cover the technical implementation and the design of the Li-Fi systems or the manufacturing and synthesis of the nanomaterials. This research is to provide a comprehensive understanding of the role of nanomaterials to provide the better performance to Li-Fi systems. So what is nanomaterials? Nanomaterials are the materials with have at least one dimension in nanoscale range, typically between 1 to 100 nanometers. Nanomaterials with their unique properties can help overcome some of the limitations of the Li-Fi technology. There are several types of nanomaterials that can be used in Li-Fi, such as quantum dots, graphene, nanotubes, and gold and silver nanoparticles. Each of these nanomaterials have its own properties and advantages. Let us dive into those properties and advantages a bit. Quantum dots are the types of nanomaterials that have unique optical and electrical properties. In Li-Fi technology, quantum dots are used as phosphorus to enhance the efficiency and performance of LEDs. One of the main advantages of using quantum dots in Li-Fi technology is their tunability, meaning that they can that their optical and electronic properties can be tailored and meet the specific application requirements. This allows for higher degree of precision and control in the design of Li-Fi systems. Graphene is another nanomaterial that has been explored for its potential use in Li-Fi technology. Graphene is a single layer of carbon atoms arranged in an hexagonal lattice, and it has an excellent electrical and optical properties. One of the main advantages of using graphene in Li-Fi technology is its high electronic mobility, which allows for the fast and efficient transfer of signals. Graphene also has a high surface area and high thermal conductivity, which can help dissipate heat generated during operation and using graphene in Li-Fi, such as the difficulty and of producing large-scale, high-quality Sorry for this little interruption. However, there are also some challenges associated with the using of graphene and Li-Fi technology, such as the difficulty of producing large-scale, high-quality graphene sheets and the need of sophisticated fabrication techniques to integrate graphene into devices. Carbon nanotubes are used in Li-Fi technology as a means of transmitting and receiving data. They have several advantages over traditional metal wires or other conductors. They have several, including their small size, high conductivity, and ability to withstand high temperatures. Additionally, carbon nanotubes have the potential to be integrated with the other nanomaterials to create more efficient and versatile Li-Fi systems. And here comes our last nanomaterial, which is gold and silver particles, which are also shown a promising applications in Li-Fi technology. They can be used as plasmonic resonance that can enhance the transmission and reception of light signals in Li-Fi systems. These nanoparticles can also be used to create nanoscale antennas that can focus and direct light signals, leading into improved performance in terms of transmission rate and change. Some of the advantages of using gold and silver nanoparticles in Li-Fi systems include their high conductivity, plasmonic resonance, and ability to enhance light absorption and scattering. These properties make them ideal for use in enhancing the performance of LEDs and photo detectors in Li-Fi systems. While nanomaterials have the potential to revolutionize Li-Fi technology, there are some limitations that need to be addressed. For example, the high cost of producing nanomaterials and the difficulty in integrating them into the existing systems. However, with the further research and development in nanomaterials have the potential to overcome these limitations and make Li-Fi technology even more efficient and secure. In conclusion, the use of nanomaterials in Li-Fi technology has the potential to transfer the way we communicate wirelessly. The advantage of using these materials, including increased transmission rates and the power efficiency, make them a promising avenue for future research and development. Thank you for listening to my presentation on nanomaterials and Li-Fi technology. If you have any questions or comments, please feel free to ask them now. I suppose there are no questions. So,
hello,
yes, please.
am I audible?
Yes, sir.
So I'd like to know, like, what is the difference of using graphene quantum dots or graphene oxide or any other nanoparticle? What is the uniqueness of each and every one?
I beg your pardon, sir. Can you please repeat the question?
So thank you. I would like to ask, what is the difference between using either graphene quantum dots or any other nanoparticle?
Okay. So you are, I suppose you are asking that why can't we use graphene, like graphene particles or other substances other than the graphene particles, right?
Yeah.
Okay. So that's because of the potential. That's because of the potential which graphene have, because the graphene is like, there are some tests which shows that the graphene has the mobility over 2 lakh to 1 crore centimeter square per VS. So, and like the quantum efficiency of the graphene is like from 2 to 30%, and its stability is moderate other than comparing to the less stable components. And it's like the cost per gram of the graphene is much lesser than the other components. That's why, sir.
Okay, thank you.
Yeah. Any other questions? I guess if there are no, thank you so much.
So it's very good presentation indeed. Abhishek, right? Avinash. So may I request to another presenter, Pooja. So please be in queue the next presenter and stick to the time as well. Make sure. So please come up on the podium, please.
Good evening, everyone. My name is Pooja. I am from MSc Mathematics. My presentation topic is reduced differential transform method for fractional order partial differential equation. In this, we are going to discuss about introduction of fractional calculus, definitions, and analysis of the method, application of our FRDTM method, and conclusion. We'll start with introduction of fractional calculus. We all know about normal derivative, first order derivative, second order derivative, but what about half order derivative? One second. Leibniz introduced the notation of half order derivative. In a letter to L. Hospital, he raised the possibility defining order derivative for non-integral values of n. In reply, L. Hospital wondered, what if order is half? That was the beginning of fractional calculus. Fractional calculus is the ordinary differentiation and integration to arbitrary non-integer order. Next, we'll discuss about definition related to fractional order. In this, we will discuss about RL fractional derivative, capital fractional derivative, and Mitage-Leffler function. Let's start with RL fractional derivative. It is denoted by capital D alpha, which is written as equation number 1. In this, m belongs to positive integer and alpha belongs to positive real number. Then capital fractional derivative. This is denoted by equation number 2, where C denotes the capital derivative of order alpha belongs to a real number, positive real number, which is defined as equation number 3. In this, alpha is lie between n minus 1 and n, and x is greater than equal to a, where n belongs to natural number, and gamma function is denoted by gamma. Then comes Mitage-Leffler function. This gives the power series definition of one parameter Mitage-Leffler function, which is defined as equation number 4. If we give gamma is equal to 1, then it will give us exponential function. And if we put gamma 2, then it will give us cos hyperbolic function. Next come analysis of fractional reduced differential transform method. Let's take uxy as an analytical function with variable x and y. Then its transform form will be written as equation number 5. Then inverse transform form of uk is written as equation number 6. Now combining the both equation, we'll get a new equation uxy, which is the result. Then putting x naught is equal to 0, we'll get an equation of uxy. The inverse transformation of the set of values uk to n yields an approximation solution as equation number 9. Now we have taken 2 examples. The first one is time fractional heat equation. We have given a time fractional heat equation as equation number 10. In this, alpha lies between 1 and 2 with initial condition exponential x. Applying transformation method to equation number 10, we'll get a recurrence relation as equation number 12. Now putting the values of k as 0, 1, 2, 3, we'll get we'll get values of u0, u1, u2, and so on. In general, we'll get a value of uk as equation number 13. Then the differential inverse transform of uk UK gives the value of UXY, which is EX and capital A alpha, where capital A alpha is the one parameter Mittag-Leffler function, which is discussed before. Second example is time fractional inviscid Burger's equation. We have taken equation, time fractional equation, where alpha lies between 1 and 2, and initial condition is AX plus A. Now applying transform form to the equation number 16 will get equation number 18, where putting k is equal to 0, 1, 2, 3 will get U0, U1, U2, U3, and so on. In general, we can write it as UK as equation number 19, where we have used in Catalan series because we are getting 1, 2, 5, 14, 42. Then we have used a Catalan series. The differential inverse transform of UK can be written as equation number 20. By putting the value of UK, we'll get a UXY as a solution of the equation, where alpha belongs to, alpha lies between 1 and 2, and capital E alpha is the one parameter Mittag-Leffler function. Now, conclusion and future scope. The FRDTM is applied to examine fractional model of heat equation and inviscid Burger's equation. In this, we get the we get a solution in form of alpha, which is order of the fractional derivative. This method gives us exact solution. It may be exploited to study more complex physical problems appearing in various fields like biological engineering, mathematics, and many more. These are the references I have used. Thank you.
Any questions?
Okay.
No?
I have one question about the presentation. I'd like to ask her, like, what is the one one application of this differential equation in the biological field? You mentioned it in your presentation.
Sir, what are you asking about? Other applications?
Yeah, I was asking, like, what is like one or two application of this differential equation in the biological field, as you mentioned it in your presentation?
So we have solved it using heat equation and Burger equation, but now we are further solving it by using more complex problems, which we are doing now, right now.
Okay. Thank you.
Thank you.
Thank you, Pooja, for giving solutions with the equations. So I would like to invite the next presenter, Garima, and then after, please, Khushbu in the anyone after Khushbu? Is there any presenter? Your good name, please? Aviral.
Good afternoon, everyone. My name is Garima Rao from MSc Mathematics. I am here to present on the title, Petri Net Modeling and Analysis of Control System. So in this presentation, I'm going to discuss introduction, then preliminaries, applications of PetriNet, and then the case study, resolving factors, other types of PetriNet, and then the conclusion. A PetriNet is a graphical and mathematical modeling tool used to describe and study the information processing systems of various types, which was originated from the dissertation of Carl Adam Petri to the Faculty of Mathematics and Physics at the Technical University of Darmstadt, West Germany in 1962. As a mathematics tool, it can be used to set up algebraic equations, state equations, and other mathematical modeling governing systems. A PetriNet is drawn as a weighted graph, bipartite graph. So what is bipartite graph? It's a graph with two distinct set of nodes such that there are no edges between the nodes of the same set. These two sets are defined as places and transitions. Places are represented as circles and transitions as either bars or boxes. A PetriNet has states designated as markings. This corresponds, which you can see the black dots. These are called the tokens. Normally, there is no limit to the number of tokens which may mark a given place. An arc, either from a place to a transition or from a transition to a place, has some weight k. A place with an arc from itself to a transition is an input place, and a place with an arc from a transition to itself is an output place. Formally, a PetriNet is defined as a 5-tuple in the form of Pn, which is P for the finite set of places, T for the finite set of transitions, F is a finite set of arcs, W is a weight function, and M0 is some initial marking. A PetriNet structure with no initial marking may be defined as N equals PTFW. Likewise, given a structure N with no initial marking, a PetriNet may be defined as Pn is equals to N, M0. So now, what is a firing rule? A transition is fired or triggered when there is at least one token in all its input places. Once fired, one token is removed from all the input places and one token is added to all the output places. A transition does not need to have both input and output. And a PetriNet whose arcs all of weight 1, that is called an ordinary. Here are some definitions of which is used in PetriNet or in graph theory: weighted graph, directed graph, undirected graph, timed nets, stochastic nets, and variance. So applications of PetriNet are modeling, analysis, and control of urban traffic, communication networks, intelligent task planning using fuzzy PetriNets, in manufacturing systems, which is modeling, control, and performance analysis, business process management, models, techniques, and empirical studies. So now we have taken a case study of police vehicle command and control system when a passenger train derailed on a bridge and plunged into Bhagmati River on July 6, 1981. So in these types of cases, police must be well informed about where the accident took place and should provide with the medical facilities and operate the system with extreme caution. So the police vehicle command and control system will be discussed in the following section. In every nation, a police control system is required for the incident management and response. This system controls how the police station handles the calls, and it keeps a record of every incident details and allots the resources to deal with them quickly and effectively. A command and control system goals is to ensure that incidents are recorded and sent to the most appropriate police department. The rescuing factors are type of incident, availability of vehicle location, vehicle types availability, the location of the incidents, and the report on specific. The system must be designed in such a way that the reporter's information is recorded. This is the model we have created by using the Snoopy tool. And after, so what this describe is, after call to a police, in this, after calls to a police station, call is transferred and decision is ready to accept or reject a call. If the call is from citizens, it is transferred to the operator who records the details of the incident. And then the location of the incident is retrieved. Finally, the priority queue is made with the incident location label. Then everything is properly set up. And after the investigation, the report is prepared and finally record is closed. And by using the simple example, we have drawn a Petri net, which also incidence matrix is given. -1 is for sinking and the +1 is for, which is away. The incident matrix, which is based on the PetriNet model, can also be used to generate the linear equations, as we can see the following. The linear algebraic invariant calculus is a powerful technique for the verification of PetriNets. We have used Python program for getting the graph and also to detect the location. Other types of PetriNets are high-level PetriNets, timed PetriNets, object-oriented PetriNets. So the conclusion, this paper proposes a police vehicle command and control system that is converted to DSS with suggestions. Decision support system can be combined with different issues to better deciding in special conditions. Thank you.
Thank you, Garima. Very good presentation indeed. Any questions from the audience, students? No? Don't think she's your friend. Just ask the questions. Okay. It was the mutually decided question.
PetriNets can be used as a visual communication aid similar to flowchart, blow diagrams, and networks.
Advantages of PetriNet.
Ma'am, advantages. This is used for, which I said, visual communication and block diagrams and mathematics also. And we can use Snoopy tool as well. Yes, ma'am. Thank you, ma'am.
So hope you will implement your applications for the fruitful outcome of the disaster management system. Thank you, Garima. Our next presenter is Khushbu. Where? She's. This one's.
Good evening to the session chair present. Today, I am presenting a review paper on the topic green communication and networking using nanotechnology.
नहीं हो रहा है ना। हाँ वही ना। वही तो नहीं आ रहा, ऊपर ना वो पूरा वो घूम रहा है।
Green communication and technology encompasses a range of strategies and technologies, including the use of renewable resources, virtualization, cloud computing, network optimization, and smart energy management systems. Nanotechnology is a technology that can improve the efficiency and sustainability of green communication and networking. So let us look how. Here, as you can see, our key areas of focus have mainly been basic researches and advancements in the field of green communication and technology, also focused on nanotechnology. The worldwide growing energy demands, together with the increasing depletion of fossil fuels, have been recognized as a major challenge that needs to be addressed at an early hour by the society in order to have a sustainable future. It is well understood that information and communication technology is one of the keys to a future of low carbon and sustainable society. The tendency is to develop equipments with better performances and higher availability. The goal is having a powerful device that in turn will require adequate cooling systems to maintain their functioning. Now let us look at recent researches in the field of green communication and networking. The first being hybrid placement of internet gateways and rechargeable routers. This study examines the placement of nodes and energy management in a wireless mesh network, and also electricity-powered internet gateways and solar-powered rechargeable routers. It aims at minimizing both capital expenses and operational expenses related to energy consumption. A minimum cost association algorithm and a greedy placement algorithm to find approximation solutions for hybrid node placements are also used. Securing and greening wireless sensor networks with beamforming. The use of beamforming technique with clustering to improve the network lifetime in a wireless sensor networks is proposed in this study. It also focuses on transmission of radio signals towards specific target directions using a combination of clustering in order to increase the node availability in wireless networks. It also evaluates the proposal and scenarios with varying number of nodes and antennas, isotropic and also conventional dipoles were tested. Next, let us look at saving energy in smart cities, also the wireless backbone network for environment sensors. More and more government technologies with the help of research sector are developing great efforts in developing the wireless sensor networks for monitoring the levels of pollution and regulation to combat them. The behavioral pattern of humans is also monitored through this. For this reason, D. Marito et al. Presents a novel mechanism for energy saving in smart cities focused on reducing the power consumption of unused access points in the backbone. Now, let us discuss about service-oriented virtual machine placements optimization for green data centers. The tree algorithm is proposed to place a virtual machine role instances at the lowest communication costs. economizing the construct cost with fewer physical servers, while another forest algorithm is also proposed for balancing the computation load between the physical machines. Best fit algorithm is also used in the simulation with total power consumption and average utility slightly impaired. For the management of wireless mesh networks, optimal energy efficiency management design, also known as OEEMD, was introduced by formulating the problem as a mixed integer linear program. The green energy efficiency management design techniques applied on a wireless mesh network can be generalized so that they are also applicable to other access networks. A context-aware green ICN model. The power adaptation in ICN nodes is conducted through dynamically adjusting the link rate corresponding to content popularity and traffic load to reduce wasteful energy consumptions. Moreover, a smart popularity-based caching strategy called distinguished caching scheme is also used. The DCS improves the content diversity of the cache storage by adjusting for each content. The number of chunks to be cached at ICN nodes based on its type and popularity level are also used. The DCS can further decrease the network system power consumptions. If we design a Wi-Fi direct scheme, now, let us discuss on the influence of nanotechnology in the rise of green and sustainable future. Nanotechnology can be beneficial for green communication and networking because it provides a headway for creating smaller and more efficient devices with reduced power consumptions. By utilizing nanoscale materials and structures, communication and networking devices can be made much more energy efficient, which is crucial in reducing carbon emissions and also the carbon footprint, promoting sustainability. It also ultimately contributes to our final goal of improving sustainability. Now, let us look at recent researches in the field of nanotechnology contributing to our goal. First, the impact of nanotechnology in development of smart cities. Cities utilize smart technology in many of their processes already, and with automation and the Internet of Things, big data, and machine learning algorithms, we can see a major shift from just enhancing an existing infrastructure to a more disruptive phase of urban living. Nanomaterials and devices can also be used for chem-bio sensors, which make the sensors much smaller by use of materials like gold, silver, platinum, etc. And they can also be functionalized with biomolecules and selectively detect specific analytes. Nanotechnology in wireless communication is beneficial because it makes a headway for creating smaller and more efficient devices by utilizing nanoscale materials and structures by which the devices are made much more energy efficient. Nanotechnology for semiconductors. In the term, we can also see the values around 10e4 ohm centimeter have been measured, and they have stable current densities as high as 10e12 A per centimeter square. One of the major causes of power consumption and propagation delay in semiconductors is RC time consistence, and reducing an R by a factor of 10 will confer significant benefits to conventional times. Here are a few of the recommendations which suggest that using nanotechnology can enhance green communication and networking to a much bigger cause, and it can also help in reducing our carbon footprint. Here is the future scope of nanotechnology, where we discuss how nanotechnology will further help in green communication and networking. Here are the references. Thank you.
Thank you, Khushbu. Probably it's going beyond the time. So is there any questions? If not, please, Aviral, for the next presentation, please come up on the stage. Yes, time is over. You may take her contact number. She'll answer your questions. Okay.
आपका presentation.
Thank you. Full sizing. Hello, hello, hello. A very good evening to one and all. It's been a long day with full of knowledge and thoughts, I guess. I won't take much of your time, but I'll discuss everything in crisp and short points. So what we did, obviously in developing India, healthcare is what we are taking up and moving forward with. So we thought of taking up the topic of autism spectrum disorder, and we thought of identifying it on based of psychological parameters. Obviously, so if this is the topic we have taken, so we have to know about autism first. Before starting, I'd like to acknowledge special thanks to Aman ma'am and Khushbu ma'am for guiding us for the same. And these are the few points we'll be discussing in this presentation, where I'll let you know what we actually did. So first question everyone will ask about is what is autism, why autism? And that is a very common question to ask before beginning. So autism is a neurodevelopmental disorder. It is very common. In India, we actually have approximately in 1 out of 500 people. So autism spectrum disorder is a complex neurological development disorder that affects a wide range of cognitive and social abilities. So in simple words, it affects social and communication abilities. Person with autism have repeated behavior and sensitivities, and each person with ASD have its own unique qualities and specifications. Why autism is, I mentioned earlier, like autism is like very common. Like in US, the ratio is very, enlarged. Every one particular out of 36 have autism in US. So what are the symptoms of autism? Delayed or impaired acquisition of words, deflects in use and understanding of non-verbal and verbal communication, vocal developments, deflects and symbolic plays of deflects, conversational defects, and literacy defects. These are some common symptoms we see in particular having autism. How can it be diagnosed? The condition is mostly diagnosed in early childhood. However, in certain cases, it does not show any symptoms until much later. According to research, 12 to 8 months old infants start showing signs of ASD. There is currently no cure to ASD, but there are many interventions that can help individuals with ASD. For example, there are behavior and communication therapies, there are educational therapies and family therapies, and there are many ways which we can not cure them, but actually help them to cope up with that. So how we did the implementation of autism detection. Obviously, if we are talking about autism, we need to first see how we detect it, what ways we use. So we
approach. We took an approach where we screen individuals for autism using recognized screening tools, conducted a comprehensive evaluation by a healthcare professional or who specializes in autism, make a diagnosis of autism using standardized diagnostic criteria, provide treatment options that address the specific needs of the individual. These are following ways which we use to detect autism in a particular. What can be the causes? There can be various causes like genetic risk factors, neurobiological factors, environmental factors. There are many ways. So I am a student of artificial intelligence and machine learning, the most, like a popular topic nowadays. So we implemented a machine learning criteria, or what we can say is machine learning objectives on the same, and we did a particular performing where we okay, so let me make it more short. We followed a particular steps where we started collecting data for the same. We took the particular data of autism, people having autism. We took the data, we did the data cleaning, what we say in machine learning, and that data cleaning was also known as data pre-processing. Then we created a model where we wanted to follow a particular steps of taking things. In model creation, we used particular libraries we have in machine learning, which are Keras CNN structure, also known as. So we are talking further. Model training was done, model evaluation. Then there was two main objectives used for the same was CNN, which is also convolutional neural networks. DenseNet, we followed the same structure to detect autism, and implementing the same, we came to know about autism detection, and the model of ours was 92% accurate. So we use these three factors to check our accuracy, which were mean square error, root mean square error, and mean absolute error. Concluding my paper, or what we can say, what research we did, using CNN structure, it can be detected up to with accuracy of 92%. These are the following references which helped us in the following. And thank you. That will be all. If anyone have any questions.
Thank you, Aviral. Means it is the very striking problem and very serious problem indeed nowadays. So we have two online oral presenters now. Aviral, I'll take your number. It's very good, interesting topic. So we have our oral presenters in online mode. So one is Sumit. If Sumit is here. No? Okay, and that Trishala Rawat. So I think Trishala Rawat is connecting with us for her presentation. Please, Trishala, unmute yourself first.
Morning, ma'am.
Yes, very good afternoon, Trishala.
Yes.
This is 5 minutes time to given to you, and just utilize it in your way.
Is my screen sharing, ma'am?
Yes, please share your screen. It's perfectly visible. Please start your presentation.
Okay. So good evening to all of you. First of all, my research topic, it is a rapid SARS-CoV-2 detection using electrochemical Apta sensor. So I've done this research under Dr. Ankur Kaushal. So I want to thank him. I want to thank my university, which has provided me the platform for present my work. So coming to the COVID. So what is a coronavirus? Coronavirus are the positive sense non-segmented single-stranded RNA lies in a diameter range of 60 nanometer to 140 nanometer. Belongs to the coronavirus family, and it is divided into the 4 separate genera, that is the alpha, beta, gamma, and delta. So the SARS-CoV-2, it belongs to the beta genera. Now, if you talk about the origin of the COVID-19, so it is originated from Wuhan, Hubei province, China, in late December 2019. So till now, more than like 600 million COVID cases have been found globally, and 44 million have been found in India. So coming to the components of the SARS-CoV-2, so we have 4 components, that is a spike protein, envelope protein, membrane protein, and a nucleocapsid protein. Now, what is the mechanism of transmission of SARS-CoV-2? So how the virus used to enter the host cell? So there is a RBD domain, which is a receptor binding domain of the SARS-CoV-2 virus, which is used to bind with the angiotensin converting enzyme that is present on the pneumocytes. So after that, the conformational changes will be happen in the S-glycoprotein of the coronavirus. As a result, there is a cleavage and release of a protein by the transmembrane protein, which is a host protein. So further, this is how it will enter the host cell. After entering the host cell, another protein, that is a cathepsin protein, which further cleaves the S protein. There is a fusion of a viral envelope with the phospholipid membrane of the endosomes. Because of this fusion, the viral genome will be released into the cytoplasm and it will get incorporated into the ribosome for translation. So after translation, the non-structured proteins, it will form, and they further form the replicase transcriptase complex, which will favor the genomic transcription and translation of the nucleocapsid spike membrane and envelope protein of the virus. Further, these proteins will enter into the endoplasmic reticulum, then move to the Golgi bodies. On the other hand, this replication of the RNA genome of virus, it will just package inside the nucleocapsid protein, which is moved to the Golgi bodies. After that, they'll combine with the same protein. This is a spike envelope membrane proteins, and finally, they'll form a mature virus particles, which is then released out from the host cell by the process of the exocytosis. So now coming to the biosensor topic. So what is a biosensor? Biosensor is an analytical device basically used for the detection of a chemical substance that combines a biological component with a physiochemical detector. So what are the components of biosensor? So there are 3 components. That is the biorecognition element. It can be anything. It can be the antibody, peptides, enzymes, DNA. Transducer is it's a component, which convert one form of energy into the another. So it is basically producing a signal. A processor, what it does, it just amplify and display the signal. Now, on the basis of the transducer, the 3 types of biosensors are there: optical, piezoelectric, and electrochemical. So as I've worked on the electrochemical biosensor. So what it does, it just convert the biochemical reaction, the chemicals which we used. So that chemical reaction it used to convert into the electrochemical signals. So this sensor is based on the Ohm's law, which is a V equals to IR. Putting the voltage constant, the I will be indirectly proportional to the resistance. So if the current will increase, the resistance will obviously it will decrease. So now how we do the electrochemical detection? So as we have chosen the paper-based electrochemical biosensor, so it consists of 3 electrodes. As you can see there, there's 3 electrodes. Middle one is the working electrode, the right one is the counter electrode, and the left one, it is a reference electrode. So the counter and working electrode, it is made up of carbon, whereas the reference electrode, it is a silver metal coated with a layer of a silver chloride. So now for the detection, we have used 3 techniques. So that is a cyclic voltammetry, differential pulse voltammetry, and electrochemical impedance spectroscopy. So cyclic voltammetry consists of cycling the potential of an electrode and measuring the resulting current in the form of P, which is proportional to the concentration of analyte. DPV, what it does, the current is monitored in this before and after a pulse of potential is applied, and the output come as a slope of a curve. And EIS, it is basically a characterization technique which is used for the characterizing the surface modification. It is used to detect the binding events on the electrode surface, like for a wide range of chemical and biological analyte. Now, coming to the nanoparticles, as the nanoparticles have achieved its importance in biotechnology, for example, in drug delivery, gene delivery, magnetic separation of biomolecules, bioimaging, etc. So what are the properties that make it so important? That is, it increases the surface area to volume ratio, it increases the electrical conductance, solubility, surface functionality, it exhibits low toxicity, high biocompatibility. So now in this nanoparticles, there are so many nanoparticles, but we have chosen the GQDs because of its key advantages. That is the non-toxicity, it's photostable, it exhibits the chemical stability, better surface grafting, And the synthesis process is also easy and consume less time. Now, the current methods for detection of SARS-CoV-2. So I have 4 methods. That is a computer tomography, CRISPR, RT-PCR, ELISA, but they have few limitations. As the computer tomography, it has limitation that it is expensive, poor sensitivity, and excessive radiation exposure. CRISPR technology is used to it used to qualify the it used to just check the quality of the desired nucleic acid content. It is unable to quantify that. The third is the RT-PCR. RT-PCR, the limitation is it requires a high instruments, require trained personnel, high proportion of false negative result it used to give. Fourth one, it is the ELISA one. It is a good method, to detect the SARS-CoV-2 virus, but the only limitation is that it is unable to find out the infection at early stage. That's why the researchers have come up with novel technologies, that is a biosensor. And in this only, we are just working on the electrode that is a simple and sensitive for the detection of the SARS-CoV-2. Now, here are some objectives of detection of the SARS-CoV-2 virus using electrochemical aptar sensor. First is the synthesis of specific aptamer against nucleic acid protein of SARS-CoV-2 using Selix process. That is a systematic evolution of ligands by exponential enrichment. It based on the principle of selection and amplification. Second is a synthesis of a graphene quantum dot space particle. Third is a characterization of nanoparticles and their fabrication onto the electrode surface. Then we do the characterization using CV-DPV impedance. And we study about the specificity. And then finally, we calculate the limit of detection and sensitivity. Coming on to the synthesis of graphene quantum dots, so we have adopted a method which is a hydrothermal method. So what is the protocol? So first we have prepared a 1.8% solution of potato starch.
Sorry, Trishala, to interrupt in between. We are running short of time and you are already been crossed your limits. That I'm sorry, it has been 8 minutes over.
Okay. Just
So please bind up in next 30 seconds.
Okay. So with the help of the hydrothermal method, we have synthesized the GQDs. So here is the characterization of GQDs. So first we have taken the FTIR. FTIR, we can see the functional group, which is expressing that, the GQDs have nanoparticles and it is functional. With the same UV spectroscopy is also used, and the DLS is also used for the nanoparticles. This is a schematic diagram. Like we have first drop casting the GQDs onto the working electrode. After that, we have fabricated unlabeled aptamer onto the working surface, followed by the fabrication of the nucleic acid protein. And then we have added the methylene blue as a redox indicator to analysis to have done the analysis of the electrochemical like CV, DPV, EIS we have done. So these are my results of the CV and DPV. So in this, as you can see, as we are increasing the concentration of the nucleocapsid protein, the current is increasing. Same goes with the DPV also. And in EIS, as we are doing the characterization, the we can see that the nucleocapsid protein, the current the resistance is increasing as we are forming the layer. So it is due to the steric hindrance, the resistance is increasing as we are increasing the concentration. For specificity, we have taken two proteins, that is a C-peptide and IL-2 protein. So it is not showing, it is not specific to that two proteins because it is showing is specific towards the nucleocapsid. As you can see with the help of curve, the violet one, it is the highest peak. So it is denoting that, that aptamer which we have synthesized, it is specific to the nucleocapsid and not to that proteins. So here's my conclusion. So this is how we have developed an electrochemical aptar sensor, which is paper-based, as it gives a quick response, cost-effective, biodegradable, specific, and stable. Graphene quantum dots also we have synthesized just to increase the surface area. Characterization we have done using FTIR, UV Spectromex, and a particle size analyzer. Later on, then we use the N10 aptamer, that is unlabeled, for biorecognition, which is specific for the nucleocapsid 10 protein. And the sensitivity and limit of detection we have found out. The sensitivity is 8.31 milliampere per millimeter square per nanogram, and the limit of detection was found out to be 0.17 nanogram per microliter. So this is how this electrochemical active sensor probe its importance for detection of the nucleic acid.
So thank you very much, Trishala. It's very good presentation indeed. And with her presentation, we are in the process to conclude our second consecutive day of our conference. That is National Conference on Multifunctional Advanced Materials. Thank you, everyone. Thank you. My sincere regards to our evaluators and judges and all the experts over here who have for the patient hearing of all our scholars and enlighten them with your presence and blessings. So we are looking forward, a great good evening to all of you first, and we are looking forward to gather here again by tomorrow for the third and last day of our event. Thank you. Thank you very much.